Maybe you had a long day. Maybe your mind is still spinning with thoughts that won't quite settle. That's okay. Tonight, we're going somewhere those thoughts can't follow. Somewhere so far removed from the surface world that even light itself gives up trying to reach it. We're descending into the deep sea. Not the ocean you know from beaches and documentaries. Not the sun-dappled shallows where dolphins play and coral reefs bloom in technicolor. No, we're going deeper, past the last rays of sunlight, past the point where familiar creatures dare to venture, into a realm so vast, so mysterious, that we've explored more of the moon's surface than we have of this dark frontier on our own planet. The deep sea is a place of eternal twilight, then eternal darkness, a place where the pressure could crush a car like a tin can. Yet life not only survives but thrives in ways that seem to defy everything we thought we knew about biology. It's a world of bioluminescent creatures that make their own light, of hot springs on the ocean floor that harbour ecosystems independent of the sun, of mountain ranges taller than the Himalayas that have never known a human footprint. Tonight, we'll drift through this realm together, slowly, gently, learning its secrets as we go. There's no rush. The deep sea has been there for eons, patient and unchanging, and it will still be there long after we've drifted off to sleep. If you're enjoying this journey into the unknown, consider subscribing to the channel. It helps us continue exploring these quiet corners of science together, one sleepy fact at a time. Now let's begin. The deep sea begins at 200 meters below the surface, so where sunlight starts to fade into perpetual twilight. This marks the boundary of the largest habitat on Earth, a realm that covers more than half our planet's surface. Imagine standing at the edge of this boundary if you could. Above you, the last traces of blue-green light filter down through the water, growing dimmer with every meter. Below you, darkness gathers like a soft blanket being pulled across the world. 200 meters doesn't sound like much, about the height of a 60-story building, or 2 football fields stood on end. But in the ocean, it's the difference between day and night, between the familiar and the utterly alien. At this depth, even the brightest sunlight becomes a faint memory. Red light with its longer wavelength vanished long ago, absorbed by the water in the first few meters. Orange followed, then yellow. Like by the time you reach 200 meters, only the faintest hints of blue remain, and even those are dying. The creatures that live here exist in a world of perpetual dusk, where seeing is measured not in colours, but in gradients of shadow and murk. And here's what makes it even more remarkable. This twilight zone, this boundary region, is just the beginning. It's the gateway to something much larger. Below this line lies a habitat so immense it dwarfs every terrestrial ecosystem combined. More than half of Earth's surface, think about that for a moment, more than half of our entire planet exists in this state of permanent darkness. Forests, deserts, tundras, grasslands, cities, all of human civilization occupies just a fraction of Earth's surface compared to the vast dark ocean that begins at this 200-meter mark. We live on a deep-sea planet, and we just happen to occupy the thin, bright skin of it. More than 80% of the ocean has never been mapped, explored, or even seen by human eyes. We have more detailed maps of Mars than we do of our own ocean floor. There's something quietly humbling about this, isn't there? We can send rovers to Mars, capture images of galaxies billions of light years away, map the surface of distant moons with incredible precision. But here, on our own planet, in the waters that cover most of our world, vast territories remain completely unknown. Not poorly understood, actually unknown. Blank spaces on the map in an age when we thought blank spaces no longer existed. The ocean floor is hidden not by distance but by water itself. Every meter of depth absorbs light, scatters sonar, and makes seeing progressively harder. Yet mapping the ocean requires ships moving slowly across the surface, sending sound waves down and waiting for them to bounce back. It's painstaking work. It takes time. And the ocean is so incomprehensibly vast that even with modern technology, we've barely scratched the surface, or rather barely mapped the bottom. Meanwhile, Mars sits naked in space, its entire surface exposed to satellites and telescopes. We've mapped it in such detail that you could, in theory, plan a hiking route across Valles Marineris. But try to plan a route across the abyssal plain of the Pacific? You'd be guessing. Much of it exists only as rough estimates derived from satellite measurements of the ocean surface, which bulges ever so slightly over underwater mountains and dips over trenches. In a sense, we live on two planets, the one we've explored and the one we've barely glimpsed. And every time we send a submersible down into those unknown depths, we're not just exploring. We're making first contact with a world that's been there all along, silent and patient, waiting beneath the waves. The deepest point in the ocean, the Challenger. Deep in the Mariana Trench reaches down nearly 11,000 meters, deep enough to swallow Mount Everest with a mile to spare. At that depth, the pressure is over 1,000 times what we experience at sea level. Let's try to comprehend this depth, though perhaps comprehension isn't quite possible. Nearly 11 kilometers straight down. If you could drain all the water away and stand at the bottom of the Mariana Trench, you'd be standing in a canyon deeper than Everest is tall. You could take the highest mountain on Earth, turn it upside down. I'd drop it into this trench, and its peak would still be more than a mile underwater. The numbers are staggering, but numbers alone don't capture what it's really like down there. So let's talk about pressure instead. At sea level, the atmosphere presses down on you with a force of about 14.7 pounds per square inch. You don't notice it because you evolved in it, because your body is filled with fluids and gases that push back with equal force. But in the ocean, every 10 meters you descend adds another atmosphere of pressure. By the time you reach Challenger Deep, the pressure is crushing, literally. Over 1,000 atmospheres, about 8 tons per square inch. The weight of a fully loaded semi-truck pressing down on every inch of your body. And yet, this isn't an empty wasteland. Life exists there. Small amphipods scuttle across the sediment. Fish with translucent bodies drift through the darkness. Sea cucumbers process the mud. They've adapted in ways that seem almost impossible. Bodies made mostly of water which doesn't compress. Protein structured to function under immense pressure. Metabolisms tuned to an environment that would kill most life on Earth instantly. The Challenger Deep is as close to another planet as you can get without leaving Earth. A place of crushing darkness and cold, where the rules are different, where life found a way anyway. The term Hadal Zone refers to ocean depth below 6,000 meters, named after Hades, the Greek underworld. It's a fitting name for a place so extreme that scientists once thought nothing could survive there. There's something poetic about this naming, isn't there? The ancient Greeks imagined Hades as a realm beneath the earth, a place of darkness where the dead went, separated from the living world by an uncrossable boundary. And in a way, the Hadal Zone is exactly that. A realm beneath the ocean, dark and seemingly lifeless, separated from the sunlit surface by thousands of meters of water that might as well be an uncrossable gulf. For a long time, scientists believed this comparison was literal. They thought the deep ocean was azoic, without life, a dead zone. The pressure was too great, they reasoned. The darkness too complete. The cold too extreme. Nothing could possibly survive in such conditions. It made sense in a way. Life as we knew it required sunlight for energy, moderate temperatures for chemical reactions, and pressures that allowed cells to function normally. The Hadal Zone had none of these things, but life, as it turns out, he doesn't particularly care what we think is possible. When the first expeditions to the deep ocean returned with samples from Hadal depths, they found something that should have been impossible. Living creatures. Not just bacteria clinging to existence, but thriving ecosystems. Animals moving, feeding, reproducing. Life had found the Hadal Zone long before humans did, and it had settled in quite comfortably. The name stuck though, Hadal Zone, the underworld, a reminder that even when we've proven a place isn't lifeless, it still feels otherworldly, alien, a realm that exists by different rules, where the normal laws of biology bend in strange and beautiful ways. In 1960, 2 men descended to the bottom of the Challenger Deep in a bathyscaphe called Trieste, a journey not repeated until 2012. Fewer people have visited the deepest ocean than have walked on the moon. Picture this. January 23, 1960. 2 men, Jacques Picard and Don Walsh, climbing into a small metal sphere attached to a massive float filled with gasoline. The craft was called Trieste, and it was essentially a submarine designed for one purpose: to sink. Not elegantly, not quickly, but inexorably, down through layer after layer of ocean until it touched the deepest point on Earth. The descent took nearly 5 hours. 5 hours of sinking through darkness, the pressure building with every meter, the hull of the bathyscaphe groaning and creaking as it compressed. There were no windows to speak of, just a small porthole made of plastic several inches thick. Outside, blackness. Inside, 2 men, and the sound of their own breathing, wondering if the sphere would hold, or if they would make it back. They touched bottom at 10,911 meters, the deepest anyone had ever been, the deepest anyone would go for another 52 years. And what did they see through that tiny porthole? A flat fish, lying on the sediment. Proof that life existed even here, in the most extreme environment on Earth. Then they came back up, and for half a century nobody followed. Think about that. We went to the moon 6 times between 1969 and 1972. 12 people walked on lunar soil. But the bottom of our own ocean? Just 2 people, once, in 1960. It wasn't until 2012 that filmmaker James Cameron made the second solo descent, followed by a handful of others in the years since. The deep ocean isn't just unexplored, it's harder to reach than space, and perhaps that's fitting. Perhaps some frontiers should remain difficult. Perhaps some places should demand our very best efforts just to glimpse them, even once. The ocean contains approximately 321 million cubic miles of water, with the deep sea making up the vast majority. If you could drain all that water, the Earth's surface would reveal mountain ranges taller than the Himalayas. Try to visualize 321 million cubic miles of water. You can't, really. The human brain didn't evolve to comprehend volumes that large, but perhaps we can approach it sideways through comparison. If you took all that water and spread it evenly across the United States, it would be over 90 miles deep. The entire country drowned under an ocean so deep that airplanes couldn't fly high enough to escape it. Most of that water, the vast, overwhelming majority, is deep ocean water. The bright and warm surface layer that we think of when we picture the ocean is just a thin skin on top of an immense cold reservoir. Imagine the ocean as a layer cake. The top centimetre is the sunlit zone where most visible life exists. The rest, meters and meters and meters deep, is the deep sea. Cold, dark, and so massive it dwarfs everything else. Now imagine draining it all away. Picture the water disappearing, lowering meter by meter, revealing the hidden landscape beneath. First, the continental shelves emerge, gentle slopes that would look almost familiar, like submerged coastal plains. Then the shelf edge, where the ocean floor suddenly drops away into the abyss. The true ocean floor begins here, a vast plain studded with seamounts, underwater volcanoes rising thousands of meters from the seabed, and then the mid-ocean ridges. These would be revealed as mountain ranges longer and taller than any on land. The mid-Atlantic ridge alone would dwarf the Rockies. Parts of it rise higher than Mount Everest rises above sea level. These are young mountains, still growing, forged by volcanic activity as tectonic plates pull apart. The Earth without oceans would be unrecognizable. A planet of extreme topography, of canyons deeper than any on land, of mountains taller than we ever imagined. A landscape that's been there all along, hidden under a blanket of water. Water temperature in the deep ocean hovers around 2 to 4 degrees Celsius year-round, creating one of the most stable environments on Earth. While surface temperatures fluctuate with seasons, the deep remains in eternal cold. There's something almost peaceful about this constancy, isn't there? On the surface. We live in a world of change, summer heat, winter cold, spring warming, autumn cooling. The temperature swings by tens of degrees, sometimes in a single day. We dress in layers, adjust thermostats, plan our lives around seasonal variation, but sink down into the deep ocean, past the thermocline, that boundary layer where warm surface water meets cold deep water, and you enter a realm where temperature becomes almost meaningless. Not because it's absent, but because it never changes. 2 degrees Celsius, 3 degrees, 4 at the most. Day after day, year after year, century after century, the temperature holds steady. This is cold, yes, just above freezing. Cold enough to numb human skin in minutes. Cold enough to slow chemical reactions to a crawl. But it's a gentle cold somehow. A cold without malice. It's just the way things are. The way they've always been. The way they'll continue to be long after we're gone. For the creatures that live there, this stability is everything. They've evolved in an environment where temperature is a constant, not a variable. Their proteins are tuned to function at this precise temperature. Their metabolisms are calibrated for eternal cold. They don't need the ability to adapt to seasonal changes because there are no seasons in the deep sea, no summer to prepare for, no winter to survive. Just the endless, unchanging present. In a way, the deep ocean is timeless, not because time doesn't pass, it does slowly, measured in the drift of sediment and the growth of deep-sea corals, but because time doesn't bring change. The deep sea yesterday was the same as the deep sea today will be the same as the deep sea tomorrow. Such a rare pocket of permanence on a planet defined by flux. The deep sea is divided into zones, the mesopelagic, twilight zone, bathypelagic, midnight zone, abyssopelagic, abyssal zone, and hadopelagic, hadal zone. Each layer has its own distinct community of creatures adapted to increasingly extreme conditions. The ocean, it turns out, is layered like an atmosphere in reverse. On land, we divide the air above us into troposphere, stratosphere, mesosphere, layers defined by temperature and pressure. The ocean has its own layers, its own zones, each with its own character, its own inhabitants, its own rules. The mesopelagic zone, from 200 to 1,000 meters, is the twilight zone. This is where the last traces of sunlight fade away completely. It's a realm of dim blues and greys, where light exists but barely. These animals here have enormous eyes to capture every photon, or bioluminescent organs to create their own light. This is the most densely populated part of the deep sea, home to more fish biomass than all the rest of the ocean combined. They rise toward the surface at night to feed, then descend again before dawn in the largest migration of animals on Earth. Below 1,000 meters lies the bathypelagic zone, the midnight zone. Here, darkness is absolute and permanent. No trace of sunlight ever reaches this depth. The only light comes from living things, the flash of a hunting dragonfish, the glowing lure of an anglerfish, the bioluminescent clouds left by startled shrimp. It's a dark canvas occasionally lit by biological fireworks, then dark again. Deeper still, below 4,000 meters, the abyssopelagic zone stretches across vast plains of sediment. This is the abyssal zone, covering more of Earth's surface than all the continents combined. Here, the pressure is enormous, the cold complete, the darkness total. Life becomes sparse, scattered, patient. Sea cucumbers crawl across the mud, amphipods scavenge. Everything moves slowly, conserving energy in an environment where food is precious and rare. And finally, below 6,000 meters, the hadal zone, the trenches, the deepest pockets of the ocean. This is life at its absolute limit, clinging to existence under conditions that seem impossible. And yet, even here, life persists. Each zone a world unto itself, each a chapter in the story of how life adapts, survives, and thrives in the deep. At 1,000 meters deep, the pressure is about 100 times atmospheric pressure, equivalent to having 50 jumbo jets stacked on top of you. Yet soft-bodied creatures thrive there because their bodies are mostly water, which doesn't compress. Let's sit with this pressure for a moment. 100 atmospheres. If you try to descend to 1,000 meters in a normal submarine, the hull would need to be incredibly thick, reinforced with the strongest materials we can manufacture. Even then, you'd hear it creak and groan, the metal compressing slightly under the immense weight of water above. Now imagine experiencing that pressure directly. 50 jumbo jets, or picture an elephant standing on a postage stamp, or the weight of an entire skyscraper compressed down onto your body. Any of these comparisons should result in instant catastrophic failure, crushing, pulverizing, obliterating whatever unfortunate object bears that weight. And yet, a jellyfish drifts through 1,000 meters as if it's the most natural thing in the world. A squid swims gracefully. A translucent fish hovers in place, utterly unbothered. How? The answer is almost elegant in its simplicity. They're made of water. Their bodies are gelatinous, fluid-filled, with very little in the way of gas-filled cavities that might compress. Water itself is nearly incompressible. You can squeeze it all you want, but its volume barely changes. So when these creatures exist at depth, the water in their bodies pushes back against the pressure with equal force. There's no crushing because there's nothing to crush. They're part of the pressure, in equilibrium with it. It's a beautiful solution, really. The deep sea doesn't fight against pressure. It accepts it, becomes one with it. These creatures don't need armor or reinforced structures. They're soft, flexible, almost ethereal. And in that softness lies their strength. The deep ocean is not silent. It's filled with the sounds of clicking shrimp, singing whales, and groaning ice shelves. Sound travels faster and farther underwater than in air, creating an acoustic landscape we're only beginning to understand. For the longest time, we called it the Silent Deep. Jacques Cousteau's documentary was titled The Silent World. It made sense. No air to carry sound, no wind to create noise, just water and darkness and presumed stillness. But we were wrong. Profoundly, beautifully wrong. The deep ocean is alive with sound. Whales sing across thousands of miles, their low-frequency calls travelling through water like voices across a canyon. Snapping shrimp create crackling symphonies so loud they can stun small fish. Ice shelves groan and crack as they carve into the sea. Underwater volcanoes rumble. Tectonic plates grind against each other in slow, geological groans. Even tiny copepods make sound as they swim, too faint for human ears but detectable with sensitive hydrophones. Sound moves differently underwater. In air at sea level, sound travels at about 343 meters per second. In water, it's faster, roughly 1,500 meters per second. And in the ocean, there's something even more remarkable. This SOFAR channel, a layer of water where sound travels the farthest. Temperature and pressure create a horizontal channel where sound waves get trapped, allowing them to propagate for thousands of kilometers with barely any loss. Whales discovered this channel long before humans did, using it to communicate across entire ocean basins. Close your eyes and imagine it. Not silence, but a soundscape of clicks, groans, songs and rumbles. A living acoustic environment where information travels not through light, but through vibration. Where creatures call to each other across distances we can barely comprehend. Where the ocean itself, the ice, the earth, the water, contributes its own voice to the chorus. The deep is not silent. We were just listening wrong. Bioluminescence, the ability to produce light, is found in about 90% of deep-sea creatures. In a world without sunlight, life learned to make its own light through chemical reactions. There's something almost magical about this, though the science is firmly rooted in chemistry. Imagine being a creature in absolute darkness. Not the darkness of a moonless night, where your eyes might adjust and pick out shapes. Not even the darkness of a cave where a distant entrance might offer a faint glow. This is total, complete darkness, the kind that would drive surface dwellers mad, and so life invented light. The process is called bioluminescence, and it's remarkably widespread in the deep sea. Some estimates suggest that 9 out of every 10 deep-sea organisms can produce light in some form. They create it through a chemical reaction, usually involving a molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it produces light. No heat, just cold, pure photons. It's one of the most efficient light-producing reactions known to science. But why make light at all? In the deep sea, bioluminescence serves dozens of purposes. Some creatures use it to hunt, like the anglerfish with its glowing lure. Others use it for camouflage, counter-illumination they call it, creating light on their undersides to match the faint glow from above, erasing their silhouette. Some use it for communication, flashing patterns to potential mates or warning rivals. Others use it as a defense, creating sudden bright flashes to startle predators or squirting glowing clouds to confuse attackers. In the deep sea, light is currency. It's language, it's weapon and shield, beacon and disguise. Life took the one thing the deep ocean lacked, light, and made it themselves. A small rebellion against the darkness, written in blue-green photons that flicker and fade and light up again in patterns we're only beginning to decode. The anglerfish dangles a bioluminescent lure above its mouth, in attracting prey in the darkness like a living fishing rod. The light comes from symbiotic bacteria living in the lure, a partnership forged in the deep. The anglerfish might be the most iconic creature of the deep sea, and for good reason. It's a study in predatory efficiency taken to almost absurd extremes. Picture a fish that's mostly mouth. Enormous jaws lined with translucent needle-like teeth that angle inward, ensuring that anything caught cannot escape. The body is small, bulbous, dark, and extending from the head, growing from a modified dorsal fin, is a long, flexible filament tipped with a glowing bulb. This is the esker, the lure. It glows with a soft greenish-blue light in the darkness, waving gently back and forth like a tiny lantern on a fishing pole. To a small fish or shrimp in the deep sea, it must look like food. Perhaps it resembles bioluminescent plankton or a tiny glowing organism worth investigating. So they swim closer, closer, and then... The anglerfish doesn't chase. It doesn't need to. It simply waits, mouth open, lure glowing, perfectly still. When prey comes within striking distance, the attack is sudden and final. Those enormous jaws snap shut in milliseconds. Game over. But here's what makes it even more remarkable. The anglerfish doesn't produce that light itself, not directly. The glow comes from bioluminescent bacteria living inside the esker in a specialized chamber. The anglerfish provides the bacteria with nutrients and a safe home. In return, the bacteria produce light. It's a symbiotic relationship, a partnership between two forms of life, each benefiting the other. The anglerfish can even control the light to some degree. You are using muscles to constrict blood flow to the lure or cover it with dark tissue, effectively turning the lamp on and off. In the deep sea, even the simplest things, like having a light, require collaboration, chemistry, and evolution's patient tinkering across millions of years. Some deep-sea fish have eyes that point upward, scanning for the silhouettes of prey against the faint light filtering from above. This upward gaze strategy is so effective that multiple species evolved it independently. Evolution, given similar problems, often arrives at similar solutions. It's called convergent evolution, when unrelated species independently develop the same adaptation because it solves a common challenge. And in the twilight zone of the deep sea, one of the most common adaptations is this: eyes that look up. These aren't normal eyes. They're tubular, barrel-shaped, sometimes telescopic. They point straight upward, locked in place, unable to move or swivel. The fish can't look left or right, can't glance down at the sea floor. Their entire visual world is the water column above them, and they're watching for one thing: silhouettes. In the mesopelagic zone, where the last traces of sunlight penetrate, there's still a faint glow from above. It's dim, incredibly dim, but it's there. And against that faint backdrop, anything swimming overhead casts a shadow, a darker shape against slightly less dark water. For a predator waiting below, that silhouette is everything. It reveals the size, shape, and position of potential prey. It's like watching shadow puppets on a screen, except the screen is the entire ocean above you, and the puppets are your dinner. So these fish, hatchetfish, barrelies, various lanternfish species, evolved eyes designed for exactly this purpose. Large lenses to gather as much light as possible, highly sensitive retinas packed with rod cells, and that characteristic upward orientation fixed and unwavering, because down here, looking up, is all that matters. It's a reminder that vision isn't universal. What we think of as seeing is just one way to gather information about the world. In the deep sea, seeing means watching for shadows. It means staring into the faint glow above and waiting for something, anything, to break the pattern of the light. The giant squid, once thought to be mythical, can grow up to 13 meters long and lives in the deep mesopelagic zone. Despite their size, they remain elusive. Most of what we know comes from dead specimens or brief camera glimpses. For centuries, sailors told stories of enormous squid rising from the depths, creatures with tentacles long enough to wrap around ships, eyes the size of dinner plates, beaks strong enough to cut through rope. The stories were dismissed as fantasy, exaggeration, the kind of tall tales that sailors are famous for. Surely nothing that large could exist in the ocean without being seen, documented, studied. Except they did exist. They do exist. The giant squid is real, and it's every bit as remarkable as the legend suggested. They can reach lengths of 13 meters or more, with tentacles that stretch out like living cables tipped with hundreds of suction cups ringed with tiny teeth. Their eyes are indeed enormous, among the largest in the animal kingdom, designed to capture light in the dim mesopelagic zone where they hunt. Their beaks are made of chitin, hard and sharp, capable of tearing through flesh. And yet, despite their size, despite living in our ocean, on our planet, we've barely seen them alive. Most of what we know comes from dead specimens that wash ashore or are found in the stomachs of sperm whales, which hunt them in deep diving battles we can only imagine. It wasn't until 2004 that scientists captured the first photographs of a living giant squid in its natural habitat. Video footage followed in 2012, grainy, brief, tantalizing glimpses of a creature that has lived in our ocean for millions of years, but remained hidden from human eyes until the 21st century. They live too deep for casual observation, move too quickly to track, and seem to avoid the lights and noise of submersibles. The giant squid keeps its secrets, and perhaps that's fitting. Perhaps some creatures should remain mysterious, known to us only in fragments and fleeting encounters, reminders that the ocean still holds wonders we've barely begun to understand. The colossal squid is even larger than the giant squid, with eyes the size of dinner plates, the largest in the animal kingdom. Those enormous eyes gather every photon of light in the deep darkness, possibly to spot the silhouettes of predators. If the giant squid is impressive, the colossal squid is extraordinary. Larger, heavier, more robust. It's built like a tank compared to the giant squid's more streamlined form. Where the giant squid has tentacles lined with suction cups, the colossal squid has rotating hooks, as sharp, swiveling hooks that can grasp and hold struggling prey even as it fights to escape. But it's the eyes that truly astound. Imagine an eye 27 centimeters across, nearly 11 inches, larger than a dinner plate, the largest eye of any known animal living or extinct. Each eye weighs several pounds and contains a lens the size of an orange. Why so large? The answer, scientists believe, has to do with the nature of vision in the deep sea. In near total darkness, the size of your eye determines how much light you can gather. A larger lens, a larger pupil, a larger retina, all of these mean more photons captured, more information extracted from the faint glow filtering down from above, or the bioluminescence of other creatures. But there's another reason, perhaps more urgent: predator detection. The colossal squid's primary predator is the sperm whale, which hunts in complete darkness using echolocation. But whales are large, and when they move through water, they disturb bioluminescent plankton, creating a faint glow around their bodies, a bioluminescent wake. Those enormous eyes might be tuned to detect exactly this, the subtle glow of disturbed plankton revealing the approach of a predator. Imagine it. In the deep darkness, a colossal squid hovering, those massive eyes scanning the water, and then a faint glow growing brighter, the telltale signature of something large moving through the deep, and the squid, warned by its enormous eyes, has seconds to flee. Evolution built the largest eyes in the world to solve one problem. See the whale before the whale's sonar finds you. Deep-sea creatures often move in slow motion, and conserving energy in an environment where food is scarce. A meal might come once a month, so every calorie counts. There's a rhythm to life in the deep sea, and it's slower than anything we're accustomed to on the surface. Creatures don't dart and chase, they don't rush, they drift, hover, glide with minimal effort. Every movement is deliberate, economical, measured against the energy it costs. Food in the deep sea is unpredictable, scarce. Most of it comes from above, the slow rain of marine snow, the occasional carcass sinking from the surface, a rare encounter with prey. A deep-sea fish might go weeks or even months between meals. When you don't know when your next meal is coming, you can't afford to waste energy on unnecessary movement, so they've adapted, metabolism slow to a crawl. Muscle tissue reduces. Why maintain energetically expensive muscles when you're not sprinting after prey? Bones thin or disappear entirely, replaced by cartilage or jelly-like tissue. Some fish are neutrally buoyant, hanging motionless in the water column, waiting. Others sink slowly, letting gravity do the work, only swimming when absolutely necessary. It's life in energy-saving mode. Everything optional has been stripped away. What remains is the bare minimum needed to survive, to sense the environment, to reproduce when the opportunity arises, to snap up food when it appears. There's an elegance to this minimalism, a kind of enforced simplicity. Watch footage of deep-sea creatures and you'll see it. They move like they're underwater, which they are of course, but more than that, they move like they're conserving something precious. Every fin stroke deliberate, every turn slow and considered. They exist in a different temporal frame than surface creatures, operating on deep-sea time, where patience isn't a virtue but a requirement for survival. The gulper eel has a mouth larger than its body, capable of swallowing prey bigger than itself. Its stomach can expand dramatically, turning its body into a living storage tank. The gulper eel is a study in desperation and adaptation. Or maybe it's better to say it's a study in taking advantage of every opportunity, no matter how rare. In the deep sea, where food is scarce and unpredictable, you can't afford to be picky. You can't afford to let a meal pass by just because it's a bit larger than you normally eat. So the gulper eel evolved a solution that seems almost absurd, a mouth that's enormous relative to its body. Not just large, enormous. The mouth can open wide enough to engulf prey larger than the eel itself. Imagine if you could unhinge your jaw and swallow something the size of a refrigerator. That's the proportional equivalent of what the gulper eel can do. Its jaws are lined with tiny teeth, but they're not for biting or chewing. They're more like guides, preventing prey from escaping once it's inside. The eel doesn't bite, it engulfs. It swims forward with its mouth open like a living net, or it waits with jaws agape, hoping something blunders in. And once prey is inside, the stomach expands. The eel's body stretches, accommodating the meal no matter how large. It becomes essentially a swimming stomach. A thin ribbon of tail trailing behind a grotesquely distended midsection. It might look uncomfortable, but in the deep sea, discomfort is irrelevant. What matters is that the eel has food. Perhaps enough food to last weeks or months. One successful meal can sustain it through long periods of fasting. It's not elegant, it's not graceful, but it works. In an environment where meals are rare and unpredictable, the gulper eel's strategy is simple. Be ready to eat anything, no matter how big, and store it for later. Survival through opportunism and a really, really big mouth. Some deep-sea fish are mostly water and gelatinous tissue, with minimal bones or muscle. This ghostly construction requires little energy to maintain and makes them neutrally buoyant in their high-pressure world. If you were designing a fish for the deep sea, you'd face several constraints. Energy is precious, so the fish can't afford to maintain heavy, metabolically expensive tissues. Pressure is enormous, so anything compressible, like gas-filled swim bladders, is a liability. Movement must be efficient because food is scarce, and there's no light, so visual displays are pointless. What would you build? You'd probably arrive at something like the deep-sea jelly-nose fish, or the rat tail, or any number of species that seem more ghost than animal. They're translucent or semi-transparent, their bodies made mostly of water and gelatinous tissue. Bones are reduced to a minimum, sometimes just a notochord, the most basic skeletal structure. Muscles are thin, weak, barely present. They drift more than swim, carried by currents, using minimal energy to maintain position. This isn't weakness, it's optimization. Water is nearly incompressible, so a body made mostly of water doesn't need to fight against pressure. The gelatinous tissue requires very little energy to maintain compared to muscle or bone, and with reduced density these fish achieve neutral buoyancy. They neither sink nor float but hover in the water column, expending almost no energy to stay in place. They're ghosts in a way, barely there. If you tried to grab one, it might slip through your fingers like jelly. If you brought one to the surface too quickly, it might fall apart, its delicate tissues unable to support themselves without the pressure of the deep pressing in from all sides. But in their environment, they're perfectly suited. Minimal maintenance costs, minimal energy expenditure, maximum efficiency. They've shed everything unnecessary and kept only what's essential. Enough nervous tissue to sense the environment, enough reproductive organs to pass on genes, and enough mouth and gut to process the rare meals that come their way. Nothing more, nothing less, just enough to be alive. The barrel-eye fish has a transparent head, allowing it to look upward through its own skull. Its tubular eyes rotate inside this clear dome, tracking prey with eerie precision. The barrel-eye fish is one of those creatures that seems too strange to be real, the kind of animal that makes you question whether evolution was being entirely serious when it designed it. And yet, it exists. It swims in the mesopelagic zone, perfectly adapted, doing exactly what it was designed to do. Its most striking feature is its head, or rather, the fact that you can see right through it. The skull is transparent, like a clear dome or a fighter jet canopy filled with fluid, and inside this dome pointing upward are two tubular eyes, green, cylindrical, unlike any eyes you've probably seen before. They're not fixed to the skull, they can rotate. The fish can look straight up, then shift its gaze forward, all while keeping its head perfectly still. For years, scientists didn't know the eyes could rotate. Most barrel-eye specimens were dead, netted from the deep, and in death the transparent dome collapsed. It wasn't until 2004 that researchers at the Monterey Bay Aquarium Research Institute observed living barrel-eyes and discovered the truth. The eyes are mobile, the dome is intact, and the whole structure is an elegant solution to a specific problem. The problem is this: how do you track prey above you while also being able to see forward when you're ready to eat it? The barrel-eye solution is that transparent dome. The eyes look up, scanning for silhouettes of prey against the faint light from above. When the fish spots something, it tilts its body and rotates its eyes forward, bringing its mouth into position. The dome protects the delicate eyes from the stinging cells of jellyfish, one of its primary prey items, while allowing unobstructed vision in any direction. It's bizarre, it's beautiful. It's a reminder that evolution doesn't care about looking normal. It cares about solving problems. And if the solution involves a see-through head and rotating eyes, so be it. Vampire squid can turn themselves inside out by pulling their webbed arms over their body when threatened. Despite the ominous name, they're actually gentle drifters that eat marine snow, falling debris from above. The vampire squid has one of the most misleading names in the ocean. Vampire suggests something menacing, predatory, dangerous, and when you first see one, the name seems appropriate. It's dark red or black, with webbed arms that connect like a cape. Its eyes are proportionally the largest of any animal, glowing red or blue depending on the light, and it has photophores, bioluminescent organs, scattered across its body that can flash in patterns. But the vampire squid isn't a predator. It's not hunting fish or attacking prey. It's doing something far more humble, eating garbage. Well, not garbage exactly. Marine snow, the constant rain of organic debris that falls through the water column. Dead plankton, fecal pellets, bits of dead organisms, mucus nets abandoned by other filter feeders. It all drifts down from the surface in a gentle, endless snow, and the vampire squid catches it. Yeah, it has two retractile filaments covered in sticky cells that it extends into the water like fishing lines. Marine snow sticks to these filaments, and the squid periodically retracts them, wiping the collected debris into its mouth. It's a peaceful existence. Quiet. Efficient. And when threatened, the vampire squid doesn't fight or flee. It performs what scientists call a pineapple posture, or pumpkin defense, pulling its webbed arms up and over its body, inverting itself into a spiky ball. The underside of its arms are covered with fleshy spines called cirri, which stick out when the arms are inverted, making the squid look larger and more intimidating than it actually is. Then it drifts, arms covering its body, photophores flashing in confusing patterns, waiting for the threat to pass. No aggression, no attack. Just a gentle creature trying to survive in the deep, unfairly saddled with a name that suggests darkness and predation, when really it's just trying to collect falling snow and stay safe. Marine snow is the constant rain of dead organisms, fecal matter, and organic debris that drifts down from the surface. It's the primary food source for much of the deep ocean, a gentle blizzard of nutrients that never stops. If you could see the deep ocean clearly, you'd notice something strange happening all around you. Things falling, not quickly, not dramatically, but constantly. A slow, perpetual descent of tiny particles drifting down through the water column like snowflakes in a silent storm. This is marine snow, and it's the foundation of almost all deep-sea life. Each flake of this snow is different. Some are the tiny shells of dead phytoplankton, microscopic algae that live near the surface, photosynthesizing in the sunlight before dying and beginning their long fall. Others are fecal pellets from zooplankton or fish, packed with partially digested organic matter. Still others are bits of dead jellyfish, fragments of molted exoskeletons, abandoned mucus nets from salps, clumps of bacteria stuck together. It's a mixture of death and waste, rendered beautiful by its purpose. Most of this material doesn't make it to the seafloor, it's eaten on the way down. A copepod filters it from the water. A jellyfish trails its tentacles through the falling snow. A fish snaps up a larger particle. Each consumption extracts a bit more energy from the original surface productivity, passing it down the food chain, down the depth gradient, until what finally reaches the bottom is depleted, picked over but still valuable. The rate of fall varies. Smaller particles drift slowly, taking weeks or months to descend thousands of meters. Larger clumps, especially fecal pellets, which are denser, fall faster. And occasionally something much larger sinks. A dead fish, a jellyfish bloom, a whale carcass. These are windfalls, bonanzas, events that can sustain bottom-dwelling communities for months or years. Marine snow is proof that the surface and the deep are connected. Energy captured by photosynthesis at the surface, where sunlight is abundant, eventually makes its way down into the darkness. The deep sea depends on the surface. It's not independent. It's supported, fed, sustained by the constant gentle rain of organic material from above. A blizzard of nutrients that falls forever, feeding an ecosystem built on leftovers. A single whale carcass that sinks to the ocean floor can sustain a complex ecosystem for decades. Scientists call these whale falls, and they're like oases in an underwater desert. Imagine you're a scavenger living on the abyssal plain. You spend your days, or more accurately your months and years, crawling across sediment, sifting through marine snow, eating the sparse organic matter that drifts down from above. Food is scarce. Energy is precious. And then, one day, something extraordinary happens. A whale dies at the surface and sinks to the seafloor right in front of you. This is a whale fall, and it's one of the most significant events that can occur in the deep ocean. A single large whale, say a grey whale or a sperm whale, represents tens of tons of organic matter. Flesh, blubber, bone, all sinking down through the water column and landing on the seafloor like a gift from the heavens. The feast begins immediately. Sleeper sharks and hagfish are often the first to arrive, tearing into the soft tissue. Crabs and amphipods swarm the carcass by the thousands, picking at flesh, fighting over scraps. Isopods burrow into the blubber. Within weeks, much of the soft tissue is gone, but that's just the beginning. Once the flesh is consumed, bone specialists take over. Zombie worms, ossidacs they're called, attach to the whale skeleton and drill into the bones with root-like structures, dissolving the lipid-rich matrix inside and absorbing the nutrients. Bacteria colonize the remaining organic matter, breaking it down chemically. and around the skeleton the seafloor becomes enriched with nutrients, supporting dense mats of bacteria and an entire community of animals that wouldn't normally survive in such numbers on the abyssal plain. This can last for decades. A single whale fall can go through multiple ecological stages, supporting different communities as the resource changes from fresh flesh to decomposing blubber to bare bone. Scientists have found whale skeletons on the seafloor that are still supporting specialized communities 50 years after the whale died. In the deep sea, where food is scarce and life moves slowly, a whale fall is a treasure, an oasis, a temporary abundance that allows life to flourish in concentrated, unexpected ways. And when the whale is finally completely consumed, the community disperses, returning to the sparse existence of the abyssal plain, waiting for the next fall. Over 400 species have been found living on whale falls, including bone-eating zombie worms that drill into skeletons. Some of these species are found nowhere else on Earth, entirely dependent on these rare events. The ecology of whale falls is so rich, so complex, that scientists consider them distinct ecosystems, isolated islands of abundance in the vast desert of the deep sea floor. And like islands, they've developed their own endemic species, creatures found nowhere else, animals that evolved specifically to exploit this particular resource, dead whales. The zombie worms, Osedax, are perhaps the most remarkable. They have no mouth, no stomach, no gut. They're basically roots and reproductive organs. The roots burrow into whale bone, secreting acid to dissolve the bone matrix and absorb the fat stored inside. The reproductive organs extend above the bone surface, releasing eggs into the water. Males are microscopic, living inside the female's tubes, reduced to little more than sperm-producing sacs. Then there are the muscles. Not the kind you find in tide pools or rivers, but specialized deep-sea mussels that grow on whale bones, farming bacteria in their gills. The bacteria perform chemosynthesis, converting chemicals released by the decomposing whale into energy. The mussels provide the bacteria with a home and access to both chemicals and oxygen. In return, the bacteria feed the mussels. It's a partnership, like the one found at hydrothermal vents, but built on a different resource, the slow decay of a whale. Snails, limpets, crabs, clams, worms, the diversity is staggering, and many of these species are specialists. They can't survive on the normal seafloor. They need whale falls. They're entirely dependent on the occasional death of a large marine mammal in just the right place, at just the right depth. This raises a fascinating question. How do these populations survive? Whale falls are rare and unpredictable. A given patch of seafloor might not see a whale fall for thousands of years. How do whale fall specialists find new carcasses? How do they maintain populations when their resource is so scattered across space and time? The answer is still being worked out, but scientists think these species may also live at other chemosynthetic environments, hydrothermal vents, cold seeps, sunken wood, hopping between these scattered oases, maintaining genetic connectivity across vast distances. The deep sea, it turns out, is connected not by continuity but by rare, isolated patches of abundance. And life has learned to navigate between them, waiting, dispersing, colonizing when opportunity arises. Hydrothermal vents are underwater geysers that spew superheated water, sometimes over 400 degrees Celsius, from cracks in the ocean floor. They were only discovered in 1977, revealing ecosystems that don't rely on sunlight at all. February 1977. The submersible Alvin is exploring the Galapagos Rift, a volcanic ridge deep in the Pacific Ocean. The scientists aboard are looking for hydrothermal activity, theoretical hot springs on the ocean floor predicted by geologists but never actually seen. They're expecting, at best, to find some interesting geology, maybe some warm water seeping from cracks in the rock. What they find instead changes biology forever, are clustered around cracks in the seafloor, where shimmering water rises in visible plumes. They see life, not just scattered bacteria but massive, dense communities. Giant tube worms, their red plumes waving in the current, clusters of white clams the size of dinner plates, crabs, shrimp, fish. A thriving ecosystem in complete darkness, at crushing pressure, thousands of meters from the surface. This shouldn't be possible. All life on Earth, as scientists understood it, ultimately depends on photosynthesis. Plants and algae capture sunlight and convert it into chemical energy. Herbivores eat the plants, carnivores eat the herbivores. Even the deep sea with its whale falls and marine snow depends on energy that originated at the surface through photosynthesis. But here, at these vents, something different was happening. Yeah, the water gushing from the seafloor was superheated, sometimes over 400 degrees Celsius, hot enough to melt lead. It was laden with chemicals, hydrogen sulfide, methane, various metals dissolved from the rocks below. And bacteria had figured out how to use these chemicals as an energy source through a process called chemosynthesis. They oxidized hydrogen sulfide, extracting energy just as surface plants extract energy from sunlight. These bacteria form the base of an entire food chain. Some lived freely in the water or on surfaces. Others formed symbiotic relationships with animals, living inside their tissues and producing food directly. The giant tube worms had no mouth or gut. They didn't need them. They were essentially vessels for chemosynthetic bacteria, providing the bacteria with access to both chemicals and oxygen, receiving nutrients in return. It was proof that life doesn't need the sun. Their ecosystems can exist powered entirely by Earth's internal chemistry. And it raised a profound question. If life can exist here, independent of photosynthesis, in such extreme conditions, where else might it exist? In Earth's crust, on other planets, in the ice-covered oceans of Jupiter's moons. The discovery of hydrothermal vents didn't just reveal a new ecosystem, it expanded our understanding of where and how life can exist. Life around hydrothermal vents is powered by chemosynthesis, bacteria converting chemicals from the vents into energy instead of using photosynthesis. This discovery fundamentally changed our understanding of where and how life can exist. Let's sit with this concept for a moment because it's genuinely revolutionary. For the entire history of biology, scientists believed that all complex life on Earth ultimately depended on the sun. Photosynthesis was the gateway. Light energy converted to chemical energy, passed up food chains, supporting everything from plankton to whales to humans. Even chemosynthetic bacteria, which had been known for a while, were considered oddities, minor players in ecosystems dominated by photosynthesis. But hydrothermal vents proved this wasn't just a minor alternative pathway. It was a complete self-sustaining system, an entire ecosystem, not just bacteria, but complex animals, predators and prey, symbiotic relationships, competition and cooperation, all built on chemistry instead of light. The process itself is elegant. Chemosynthetic bacteria take simple inorganic molecules. Hydrogen sulfide is the most common, although some use methane, hydrogen or iron, and oxidize them, combining them with oxygen or other electron acceptors. This releases energy, which the bacteria use to fix carbon dioxide into organic molecules, building their bodies from the raw materials dissolved in the vent water. It's the same basic principle as photosynthesis, taking inorganic carbon and turning it into organic compounds, but using chemical energy instead of light energy. The bacteria don't need chlorophyll or sunlight. They need access to both the chemicals from the vents, the reduced compounds, and oxygen or other oxidants from the seawater. They live at the interface, where vent fluid mixes with cold, oxygenated seawater, and they harvest the energy released when these chemicals meet. And from this foundation, an entire ecosystem emerges. Some animals graze directly on the bacterial mats, others filter bacteria from the water, still others host bacteria in their tissues, becoming walking farms. Predators eat the grazers and filter feeders. Scavengers clean up the dead. It's a complete ecological community, as complex and interconnected as any on the surface, but with a fundamentally different energy source. This discovery reshaped astrobiology. Before 1977, when thinking about life elsewhere in the universe, scientists focused on planets with liquid water and sunlight. After 1977, the requirements expanded. You don't need sunlight. You need liquid water, chemical disequilibrium, mixing of reduced and oxidized compounds, and time. Suddenly, places like Europa, Jupiter's ice-covered moon, become not just possible but plausible habitats for life. If chemosynthetic ecosystems exist in Earth's dark ocean, why not in Europa's dark ocean, kept liquid by tidal heating, fed by chemicals from the rocky seafloor below? Hydrothermal vents taught us that life is more versatile, more resourceful, more independent than we thought. And they taught us to look for life in unexpected places. Giant tube worms living near hydrothermal vents can grow up to 2.4 meters long and have no mouth, stomach, or gut. They survive entirely through symbiotic bacteria living inside them that produce food from vent chemicals. The giant tube worm, Riftia pachyptila, is one of those organisms that makes you reconsider what an animal can be. It's a worm, yes, but not like any earthworm or marine worm you've encountered. It's massive, up to 2.4 meters long, about as tall as a basketball player. It lives in dense clusters around hydrothermal vents, their white tubes packed together like an underwater forest, their red plumes waving in the current. The plume is the only part you can see from outside the tube. It's bright red, filled with hemoglobin-rich blood that captures both oxygen and hydrogen, sulfide from the water, two chemicals that normally can't coexist because they react with each other. But the tube worm's hemoglobin is specially adapted to bind both simultaneously and keep them separated until they reach the trophosome, the organ where the symbiotic bacteria live. And here's where it gets strange. The adult tube worm has no mouth, no gut, no anus, no digestive system whatsoever. It can't eat in any conventional sense. So how does it survive? Entirely through bacteria. Then inside the tube worm's body is an organ called the trophosome, which can make up more than half the worm's body weight. This organ is packed, absolutely filled with chemosynthetic bacteria, billions of them. The tube worm provides the bacteria with a stable environment, protection, and access to the raw materials they need: oxygen and hydrogen sulfide from the plume, carbon dioxide from the seawater. The bacteria in turn perform chemosynthesis. They oxidize the hydrogen sulfide, extract energy, and use that energy to fix carbon dioxide into organic molecules, sugars, amino acids, lipids. The tube worm absorbs these compounds directly from the bacteria. It's not digestion. It's more like farming. Or maybe it's more accurate to say the tube worm is a mobile bioreactor housing bacteria that produce food internally. And this relationship is so intimate, so essential, that the tube worm literally cannot survive without its bacteria. And the bacteria are transmitted from parent to offspring. Baby tube worms actually have a brief stage with a rudimentary gut, during which they acquire bacteria from the environment. Once colonized, the gut degenerates. The mouth closes. From that point on, the worm and its bacteria are one integrated system. It's a reminder that individuality is sometimes an illusion. The tube worm isn't really one organism. It's a partnership. A collaboration between animal cells and bacterial cells, each contributing what the other lacks, together creating something that neither could be alone. The water around black smoke vents is so mineral rich that it looks like dark smoke billowing from underwater chimneys. These minerals precipitate out as the hot water meets cold seawater, building towering structures over time. Black smokers are among the most dramatic geological features in the ocean floor. Imagine chimneys, tall, dark structures rising from the sea floor like industrial smokestacks, belching clouds of black smoke into the water. The smoke isn't actually smoke, of course. It's minerals, dissolved metals and sulfides that precipitate out of solution when superheated vent fluid meets near-freezing seawater. The vent fluid comes from deep within the Earth's crust. Cold seawater seeps down through cracks in the ocean floor, descending kilometers into hot rock near magma chambers. The water heats up, sometimes exceeding 400 degrees Celsius, and as it does, it becomes extremely corrosive, dissolving metals and minerals from the surrounding rock. Iron, zinc, copper, sulfur all leach into the water, creating a chemical-rich fluid under enormous pressure. This superheated fluid rises back toward the seafloor, driven by convection. When it finally erupts from the seafloor, it encounters seawater at 2 degrees Celsius. The temperature difference is shocking, over 400 degrees in an instant, and in that instant the dissolved minerals precipitate. They fall out of solution as solid particles, creating that characteristic black cloud. But the precipitation doesn't just create smoke, it also builds structures. As the minerals fall out of the vent fluid, some of them stick to the vent opening. Over time, particle by particle, they build up. A chimney forms. The chimney grows taller, sometimes reaching heights of tens of meters. It's like a geological 3D printer, in us building rock structures from the bottom up through chemical deposition. These chimneys are fragile and temporary by geological standards. They grow quickly, sometimes centimeters per day, but they're also unstable. They can collapse, clog, or be abandoned when vent activity shifts to a new location. Scientists have found vent fields littered with dead chimneys, toppled structures, and inactive vents slowly being buried by sediment. But while they're active, they're spectacular. Black clouds billowing into the darkness, heat shimmering the water, structures growing before your eyes, and life clustered around the edges where the mix of hot and cold creates a habitable zone. Black smokers are Earth's internal chemistry made visible, the mineral-rich fluid from the planet's interior meeting the cold ocean in a continuous chemical reaction that builds landscapes and sustains ecosystems far from the sun. Some vent bacteria can survive in water above the boiling point, making them among the most heat-tolerant organisms known. They thrive in conditions that would instantly destroy most life on Earth. There's a species of bacteria called Methanopyrus candeleri that was discovered living in sediments near hydrothermal vents. Its optimal growth temperature is around 98 degrees Celsius, just below the boiling point of water at sea level, but it can survive and even reproduce at temperatures up to 122 degrees Celsius. At the pressures found in the deep ocean, water doesn't boil at 100 degrees Celsius. It can remain liquid at much higher temperatures. These bacteria are living in water hot enough to sterilize medical equipment. Think about what this means. The proteins in most organisms denature, unfold and lose their function at temperatures well below 100 degrees Celsius. That's why cooking an egg changes its texture. The heat denatures the proteins. Most life on Earth functions within a relatively narrow temperature range, roughly 0 to 50 degrees Celsius. A few extremophils can handle higher temperatures, but nothing like what vent bacteria endure. So how do they do it? The answer lies in adaptation at every level. Their proteins are structured differently, with extra chemical bonds that keep them stable at high temperatures. Their membranes are made of special lipids that remain intact when most fats would melt. Even their DNA has unique characteristics that prevent it from falling apart in the heat. These organisms are called hyperthermophils, lovers of extreme heat, and they're not just surviving at these temperatures, they're thriving. For them, 120 degrees Celsius isn't extreme. It's optimal. It's comfortable. They would die in what we consider room temperature. Our environment would freeze them into inactivity. The existence of hyperthermophils has profound implications. For one, it suggests that early life on Earth might have originated in hot environments, maybe at hydrothermal vents, rather than in sunlit shallow ponds. Heat-loving bacteria are found deep in the tree of life, suggesting that the last common ancestor of all life might have been thermophilic. It also expands the range of environments where we might expect to find life elsewhere. If life can exist at 122 degrees Celsius on Earth, could it exist in the hot subsurface oceans of icy moons, or in the scorching underground aquifers of Mars? The universe of habitable environments keeps expanding the more we explore Earth's extremes. Cold seeps are areas where methane and other hydrocarbons leak from the seafloor, supporting their own unique ecosystems. Unlike the dramatic vents, these seeps are quiet and slow, but just as alive. If hydrothermal vents are the dramatic, explosive cousins of chemosynthetic ecosystems, cold seeps are the quiet, patient relatives. There's no superheated water, no black smoke, no towering chimneys, just a slow, steady leak of methane and other hydrocarbons from sediments into the overlying water. It's gentle, almost unnoticeable, but it's enough. Cold seeps occur in places where organic-rich sediments are buried deep enough to generate methane through microbial decomposition or thermal processes. This methane migrates upward through cracks and porous sediments, eventually reaching the seafloor. As it seeps out, bacteria in the sediment consume it through a process called anaerobic methane oxidation. They use sulfate from seawater as an electron acceptor instead of oxygen, producing hydrogen sulfide as a byproduct. Other bacteria then use that hydrogen sulfide, oxidizing it with oxygen from the water and extracting energy. The same basic process as at hydrothermal vents, just slower and colder. These bacteria form the base of the cold seep ecosystem, and around these seeps life gathers. Mussels cluster at the sediment surface, their gills packed with chemosynthetic bacteria. Tube worms extend from the sea floor, though different species than those at vents. Clams burrow into the sediment, positioning themselves where they can access both sulfide from below and oxygen from above. Bacterial mats spread across the sediment like white or orange carpets, visible evidence of the chemical activity beneath. The pace is slower than at vents. Vent communities can develop within years or even months after a vent becomes active. Seep communities develop over decades or centuries. The flow of chemicals is steady but gentle. There's no dramatic temperature gradient, no shimmering water, just a quiet, continuous supply of methane and the slow, patient bacteria that have learned to use it. Cold seeps are widespread, far more common than hydrothermal vents. They occur along continental margins in areas where sediment accumulation is high and organic matter is abundant. Some have been continuously active for thousands of years supporting stable communities that persist across geological timescales. They're proof that chemosynthetic ecosystems don't require volcanic activity or extreme temperatures. They just require chemical disequilibrium, a source of energy in the form of chemicals that aren't yet in equilibrium with their environment. And wherever that exists, life finds a way. Methane ice, also called methane hydrate, forms in deep-sea sediments where pressure is high and temperature is low. There's so much frozen methane in the ocean that it could potentially hold more energy than all known fossil fuel reserves. Beneath the ocean floor, in sediments at certain depths where the water is cold and the pressure is high, something remarkable exists. Ice that burns. Is methane hydrate, sometimes called methane ice or fire ice, is a solid crystalline structure where methane molecules are trapped inside cages of water molecules. It looks like dirty ice. It exists in vast quantities, locked in marine sediments around the world. The conditions for methane hydrate formation are specific. You need pressure high enough and temperature low enough that the water methane structure is stable. Too warm, and it melts, releasing methane gas. Too low pressure, and the structure breaks down. But within a certain window, typically at depths between a few hundred and a few thousand meters, in polar regions or deep ocean, the conditions are perfect. And the quantities are staggering. Estimates vary, but some suggest there could be more organic carbon locked up in methane hydrates than in all other fossil fuels combined. We're talking thousands of gigatons of methane frozen in sediments, representing an enormous potential energy source, but accessing it is extraordinarily difficult. Methane hydrate is stable only under specific conditions. If you try to extract it, you change the pressure and temperature, and it destabilizes, turning from solid to gas. This can cause sediment collapse, submarine landslides, even tsunamis. And methane is a potent greenhouse gas, far more effective at trapping heat than carbon dioxide over short time scales. Releasing large amounts of methane from hydrates could have severe climate consequences. In fact, there's evidence that past climate events may have been triggered by methane hydrate destabilization. The Paleocene-Eocene thermal maximum, a period of rapid warming about 56 million years ago, may have been caused or amplified by methane release from hydrates as ocean temperatures rose. It's a reminder that the ocean holds vast amounts of energy and material, not all of which we can or should try to access. Methane hydrates are there, stable for now, locked in the cold pressure of the deep sea, but they're sensitive to change. A time bomb, some scientists call it, that could be triggered by warming oceans or shifting pressure conditions. For now, they remain frozen, quietly representing both a potential resource and a potential danger, depending on how the future unfolds. The deep ocean floor is covered in a layer of sediment called ooze, made from the microscopic shells of countless dead organisms. This soft, muddy layer can be hundreds of meters thick, a geological library recording millions of years of ocean history. The word ooze doesn't sound particularly scientific, does it? Sounds like something you'd find in a swamp, or perhaps something a child would gleefully squish between their toes. But in oceanography, ooze is a technical term for a specific type of sediment, and it covers vast expanses of the deep sea floor. There are different types of ooze, classified by what they're made of. Calcareous ooze consists primarily of calcium carbonate shells from foraminifera and coccolithophores, microscopic organisms that lived in the surface ocean, died and sank. Silicious ooze is made of silica shells from diatoms and radiolarians, other tiny organisms with glass-like skeletons. The type of ooze you find at any given location depends on depth, temperature, and what organisms lived in the water above. These sediments accumulate incredibly slowly. In some parts of the deep ocean, the rate is just a few millimeters per 1,000 years. A centimeter of sediment might represent tens of thousands of years of continuous deposition, and yet, over geological time, these tiny increments add up. In some places, the ooze is hundreds of meters thick, a soft, muddy archive stretching back millions of years. Scientists drill cores into this ooze, extracting long cylinders of sediment that can be analysed layer by layer. Each layer is a snapshot of the ocean at a particular moment in time. The chemical composition of the shells tells us about ocean temperature and chemistry. The species present tell us about climate and ocean circulation. The ratio of different isotopes tells us about ice volume and global temperature. It's like reading tree rings, but instead of trees, we're reading the accumulated remains of countless microscopic organisms. Each one lived briefly, died, and settled to the bottom, contributing its tiny shell to the growing archive. Generation after generation, species after species, through ice ages and warm periods, through mass extinctions and radiations, they fell and accumulated and preserved a record of Earth's climate history. The deep ocean floor isn't just a place, it's a library, a quiet repository of information about our planet's past, written in the language of microscopic shells, waiting patiently for anyone willing to read it. Manganese nodules, potato-sized rocks rich in valuable metals, carpet large areas of the abyssal plain. They grow incredibly slowly, perhaps a few millimeters per million years, making them older than most mountains. Scattered across the abyssal plains, particularly in the Pacific and Indian Oceans, lie fields of strange dark rocks. They're roughly spherical or lumpy, about the size of potatoes, sitting on or partially buried in the sediment. Pick one up if you could reach that far down, and you'd find it surprisingly heavy, rough-textured, layered like an onion. These are manganese nodules, and they're one of the ocean's most curious geological features. They're composed primarily of manganese and iron oxides, but they also contain significant concentrations of valuable metals, nickel, copper, cobalt, rare earth elements. The exact composition varies, but in general they're metal-rich rocks just lying on the seafloor in vast quantities waiting. How do they form? That's a question scientists are still working to fully answer. The basic process seems to be chemical precipitation. Metals dissolved in seawater or released from sediments precipitate around a nucleus, maybe a shark tooth, a piece of bone, a rock fragment. Layer by layer, over immense periods of time, the nodule grows, And when we say immense periods of time, we mean it. Growth rates are measured in millimeters per million years. Some estimates suggest rates as slow as 1 to 10 millimeters per million years. At that pace, a potato-sized nodule might be tens of millions of years old, older than the Himalayas, older than many mountain ranges. These rocks have been sitting on the seafloor, slowly accumulating metal since the age of dinosaurs or earlier. Why don't they get buried by sediment? That's another mystery. The abyssal plain does accumulate sediment, albeit slowly. Yet somehow, the nodules remain at the surface. Perhaps bottom currents occasionally expose them. Perhaps bioturbation, the churning of sediment by organisms, keeps them from being buried. Or perhaps they grow just fast enough to stay at the sediment surface as new layers accumulate beneath them. In recent years, there's been increasing interest in mining manganese nodules. They contain valuable metals in concentrations higher than many land-based ores. Mining companies and some governments see them as a potential resource for electronics, batteries, and green energy technologies. But harvesting them would mean disturbing the deep sea floor on a massive scale. The nodules themselves may host specialized organisms. The sediment between them supports communities we barely understand, and removing them would erase geological features that took millions of years to form, destroying an archive of ocean chemistry we haven't fully studied. They sit there still, scattered across the abyss, ancient and patient, waiting while we decide what they mean to us, a resource to be exploited or a wonder to be protected. The mid-ocean ridge system is the longest mountain range on Earth, stretching over 65,000 kilometers beneath the waves. It's where tectonic plates pull apart, creating new ocean floor in a process called seafloor spreading. If you could drain the ocean and look at Earth's true topography, the most dramatic feature wouldn't be the Himalayas or the Andes. It would be the mid-ocean ridge, a continuous mountain range that winds through all the ocean basins like the seam on a baseball. It runs down the center of the Atlantic, separating the Americas from Europe and Africa. It curves around Africa and through the Indian Ocean. It stretches across the Pacific, branching and connecting in a global network. In total, it's over 65,000 kilometers long, more than 1.5 times the circumference of the Earth at the equator. It's the longest mountain range on the planet, and most people have never heard of it. The mid-ocean ridge isn't built by compression or folding like terrestrial mountains. It's built by separation. At the ridge axis, tectonic plates are pulling apart. As they separate, magma from the mantle rises to fill the gap. The magma cools and solidifies, forming new oceanic crust. This process, seafloor spreading, is continuously creating new ocean floor. It happens slowly. The Atlantic, for instance, is widening at about the rate your fingernails grow, a few centimeters per year. But over geological time, this adds up. The Atlantic Ocean didn't exist 200 million years ago. It formed as the Americas separated from Europe and Africa, and it's still growing today, millimeter by millimeter, year by year. The ridge itself is volcanically active. Lava erupts from fissures along the axis, forming pillow basalts, rounded blobs of rapidly cooled lava that pile up cushions. Hydrothermal vents cluster along the ridge, fed by seawater circulating through the hot, fractured rock. Earthquakes are common as the crust cracks and shifts. In some places, the ridge rises high enough to breach the surface. Iceland sits atop the mid-Atlantic ridge, a rare place where you can stand on the ridge itself, feeling it pull apart beneath your feet. The island is literally being torn in two as the North American and Eurasian plates diverge, but mostly the ridge is hidden, a vast active geological feature, building new seafloor, supporting unique ecosystems, reshaping ocean basins, and we only discovered it in the mid-20th century. It's a humbling reminder of how much we didn't know, and still don't know, about the planet we live on. Underwater volcanoes called seamounts number in the tens of thousands and create isolated habitats for unique species. Many remain unexplored, each potentially harbouring life found nowhere else. Scattered across the ocean floor, rising from the abyssal plain like islands that never quite made it to the surface, are tens of thousands of seamounts. These are underwater volcanoes, some extinct, some dormant, a few still active. They vary enormously in size. Some rise just a few hundred meters above the surrounding sea floor. Others climb thousands of meters, their peaks still far below the surface. The exact number is uncertain, because we haven't mapped most of the ocean floor in detail. Estimates range from 30,000 to over 100,000 seamounts taller than 1,000 meters, and that's not counting the smaller ones, hills and knolls and volcanic bumps that might number in the millions. Each seamount is, in a sense, an island. Not in the literal sense, they don't break the surface, but ecologically. They rise above the surrounding plain, disrupting ocean currents, creating upwellings that bring nutrients from deep water toward the surface. These upwellings support increased productivity. Plankton blooms, fish aggregate, coral grows on the hard substrate of the volcanic rock. Because seamounts are isolated from each other, separated by expanses of abyssal plain, populations on different seamounts can evolve independently. You get what biologists call endemism, species found on one seamount but nowhere else on Earth. A fish species that lives only on a particular seamount in the Pacific. A coral that grows on one volcanic peak and has never been found anywhere else. This makes seamounts biodiversity hotspots, but also makes them vulnerable. If you damage the ecosystem on a seamount, through bottom trawling, mining, or other disturbances, you might drive species extinct before we even knew they existed. And we've only explored a tiny fraction of seamounts. Most have never been visited by a submersible. We know they're there from sonar mapping, but what lives on them, how their ecosystems function, and what unique species they harbour, all of that remains largely unknown. It's a reminder that exploration isn't finished. Discovery isn't over. There are tens of thousands of underwater mountains we've barely looked at, each one potentially hiding species, ecosystems, geological features we've never encountered. The ocean still holds that kind of mystery. Not distant, not in exotic locations, but scattered throughout the ocean, waiting for anyone with the resources and curiosity to visit. The deep ocean has its own weather systems, underwater currents and storms that move sediment and nutrients across the seafloor. These invisible rivers can be stronger than surface currents and shape the deep ocean landscape. When we think of ocean currents, we usually picture surface currents, the Gulf Stream, the Kuroshio, the Antarctic Circumpolar Current. These are the rivers of the surface ocean, driven by wind and the rotation of the Earth. But the deep ocean has its own circulation, its own currents, and in some ways they're even more powerful. Deep ocean currents are driven primarily by density differences. Cold, salty water is denser than warm, fresh water. When water becomes dense enough, it sinks, and when it sinks, it has to go somewhere. It flows along the seafloor following the contours of the ocean bottom, sometimes channeled through gaps between underwater mountains, sometimes spreading out across abyssal plains. These deep currents can be surprisingly strong. In some places, they flow at speeds comparable to surface currents, tens of centimeters per second or faster. They transport enormous volumes of water. The Antarctic bottom water, for instance, flows northward from Antarctica, spreading across the floors of the Atlantic, Indian and Pacific Oceans, carrying cold, oxygen-rich water that ventilates the deep sea. And occasionally there are events that oceanographers call benthic storms. These aren't storms in the surface sense, no wind, no waves, but sudden increases in current speed near the seafloor. They can be triggered by eddies descending from above, by tides interacting with underwater topography, or by other complex oceanographic processes we're still trying to understand. When a benthic storm occurs, the increased current speed can resuspend sediment, creating underwater clouds of suspended particles. It can transport nutrients across the sea floor. It can affect the organisms living there. Some may burrow deeper, others may take advantage of the increased food availability. The deep ocean floor, which seems so still and unchanging, is actually dynamic. There's flow, movement, variability. The sediment we talked about earlier, the ooze that accumulates so slowly, doesn't just fall straight down and stay in place. It gets redistributed by currents. It accumulates in drifts and deposits shaped by the flow of deep water, creating features called sediment waves, underwater dunes that can be hundreds of meters long. The deep sea has weather. Not weather we'd recognize from the surface, but weather nonetheless. Currents that vary in strength and direction. Events that reshape the landscape. A hidden atmospheric layer at the bottom of the ocean, invisible from above but constantly in motion. Thermohaline circulation, sometimes called the ocean conveyor belt, moves water through all the world's oceans over a cycle lasting about 1,000 years. Deep cold water sinks at the poles and slowly travels through the abyss before rising again in warmer regions. Picture the ocean not as separate bodies of water, Atlantic, Pacific, Indian, but as a single interconnected system. Water circulates through this system in a grand loop that touches every ocean basin, from the surface to the abyss and back again. This is thermohaline circulation, driven by differences in temperature, thermo, and salinity, haline. It begins in the polar regions. In the North Atlantic, near Greenland and Iceland, surface water cools dramatically during winter. As it cools, it becomes denser. Sea ice formation makes it even denser because when seawater freezes, it leaves most of its salt behind, making the remaining water saltier. Eventually, this cold, salty water becomes dense enough to sink, a process called deep water formation. The sinking water descends to the ocean floor and begins a long journey. It flows southward through the Atlantic as North Atlantic deep water, slides under warmer water masses, spreads into the Southern Ocean, and eventually makes its way into the Indian and Pacific Oceans. This journey takes centuries. A parcel of water that sank near Greenland might not return to the surface for 1,000 years. Eventually the deep water rises. Upwelling occurs in various places, along the coasts of continents, in the Southern Ocean, in the tropical Pacific. The water warms, becomes less dense, flows back toward the poles at the surface, completes the loop, and sinks again. This circulation is crucial for Earth's climate. It transports heat from the tropics toward the poles, moderating temperatures globally. It distributes oxygen to the deep ocean. Without it, the deep sea would become anoxic, lifeless. It moves nutrients from deep water, where they accumulate, back to the surface, where they support photosynthesis and the entire marine food web. But thermohaline circulation is sensitive to change. If too much fresh water enters the polar oceans from melting ice sheets, increased rainfall, it can reduce the salinity of surface water, making it less dense, potentially slowing or even shutting down deep water formation. There's evidence this has happened in the past, triggering rapid climate shifts. The ocean conveyor belt is a global system operating on timescales of centuries to millennia. It's slow, patient, enormous in scale, and it connects the surface ocean, where we live and see, to the deep ocean, hidden and vast, creating a circulation that has shaped Earth's climate for millions of years and will continue to do so for as long as the ocean exists. The deep ocean stores about 50 times more carbon dioxide than the atmosphere. This makes it a crucial regulator of Earth's climate, absorbing excess CO2 over centuries. The ocean is Earth's largest carbon reservoir, not the forests, not the atmosphere, the ocean. And most of that carbon is in the deep sea, dissolved in water that hasn't seen the surface in centuries. Carbon enters the ocean in several ways. CO2 from the atmosphere dissolves directly into surface water. The ocean absorbs about a quarter of all CO2 emitted by human activities each year. Marine organisms take up carbon through photosynthesis and incorporate it into their shells and tissues. When these organisms die, they sink, carrying carbon down into the deep ocean. Once in the deep ocean, carbon can stay there for a long time. The water masses at depth are isolated from the atmosphere by the thermocline and by slow mixing rates. A carbon atom in deep water might not return to the atmosphere for hundreds or thousands of years, depending on where and when it eventually upwells. This long-term storage is critical for climate regulation. Without the ocean absorbing CO2, atmospheric concentrations would be much higher and the greenhouse effect would be more intense. The ocean acts as a buffer, slowing the rate at which CO2 accumulates in the atmosphere. But this buffering has limits. As the ocean absorbs more CO2, the chemistry of seawater changes. CO2 reacts with water to form carbonic acid, which lowers the pH, a process called ocean acidification. This makes it harder for organisms to build calcium carbonate shells and skeletons. Corals, mollusks, some plankton, all are affected. An ocean acidification happens everywhere, but the effects are felt in the deep sea too. Deep water already has naturally lower pH than surface water because it has been accumulating CO2 from decomposing organic matter for centuries. Adding more CO2 from the surface pushes it closer to levels that could dissolve calcium carbonate structures. The deep ocean is absorbing our carbon emissions, storing them, keeping them out of the atmosphere for now. But it's a slow process and it comes at a cost. The ocean's chemistry is changing in ways we're only beginning to understand, and the deep sea, that vast reservoir that has buffered Earth's climate for so long, is being asked to absorb more than it ever has before. Oxygen minimum zones are layers of ocean where oxygen levels drop to nearly zero, creating dead zones where few animals can survive. Yet even here, specialized bacteria thrive in conditions most life would find suffocating. At certain depths in the ocean, usually between 200 and 1,000 meters, oxygen levels plummet. These are oxygen minimum zones, or OMZs, and they're among the most inhospitable environments in the ocean for animals that breathe oxygen. The formation of OMZs is a matter of supply and demand. Oxygen enters the ocean at the surface through gas exchange with the atmosphere and through photosynthesis. As water descends, it carries this oxygen downward, but at intermediate depths, respiration and decomposition consume oxygen faster than it can be replenished. Bacteria decompose sinking organic matter, using oxygen in the process. Animals respire, consuming more oxygen. And if the water mass is isolated from surface contact for long enough, oxygen levels drop. In the most extreme OMZs, oxygen concentrations fall to less than 2% of saturation. Most fish and mobile invertebrates can't survive in such conditions. They flee if they can, or die if they can't. The result is a layer of ocean that's nearly devoid of animal life, but not devoid of life entirely. Bacteria adapted to low oxygen conditions thrive in OMZs. Some are anaerobic, able to live without oxygen altogether. Others are microaerophilic, requiring only trace amounts. They perform unusual metabolic processes, denitrification, sulfate reduction, anaerobic ammonium oxidation, using alternative chemical pathways to extract energy. These bacteria play crucial roles in nutrient cycling. They transform nitrogen compounds, releasing nitrogen gas back into the water. They cycle sulfur, phosphorus, and other elements. In some ways, OMZs are microbial hotspots, places where bacteria dominate and drive the chemistry of the water, and OMZs are expanding. As the ocean warms due to climate change, water holds less dissolved oxygen. Warmer water also strengthens stratification, the layering of water masses, which reduces mixing and makes it harder for oxygen to reach intermediate depths. Models predict that OMZs will grow larger and more intense in the coming decades. This has consequences for marine ecosystems. Then animals that can't tolerate low oxygen will be squeezed into smaller habitable zones. Fisheries could be affected. The ocean's ability to store carbon and cycle nutrients could change. The deep ocean isn't uniform. It has layers, zones, regions with different characteristics. And the oxygen minimum zones, the suffocating layers where most animals can't survive, are a reminder that the ocean's habitability varies dramatically with depth, chemistry, and circulation. Some deep-sea bacteria can survive on a caloric intake so low it's almost undetectable, entering a state of near stasis. They represent life at its absolute minimum, barely metabolizing, waiting for nutrients that may not come for years. There's a concept in biology called the maintenance energy, the minimum amount of energy an organism needs just to stay alive. For most organisms, this is substantial. You need energy to repair damaged proteins, to maintain cell membranes, to power the molecular machinery that keeps cells functioning. Starve an organism below its maintenance energy, and it dies. But some deep-sea bacteria have pushed this limit to an almost unimaginable extreme. Studies of bacteria in deep ocean sediments, not just on the seafloor but buried meters below it in ancient sediment layers, have found cells that are alive but barely active. Their metabolic rates are so low that they might divide once every 1,000 years. They consume so little energy that it's difficult to measure. How low? Some estimates suggest energy intakes on the order of a few zeptawatts per cell. A zeptawatt is 10 to the power of minus 21 watts. Such a tiny amount of power that it's almost meaningless to human intuition. These bacteria are operating at the absolute thermodynamic minimum needed to maintain cellular integrity and occasionally repair damage. They're not exactly dormant. They're not spores or cysts. They're alive, metabolically active, but so slowly that the word active seems inappropriate. They exist in a state of near stasis, maintaining themselves on a trickle of energy derived from chemical reactions in the sediment around them, and they wait. For what? Perhaps for a change in conditions that will bring more nutrients. Perhaps for nothing in particular. They simply persist because they can, because they've evolved the ability to survive on almost nothing, and because the deep ocean sediments provide stable conditions where this ultra-slow lifestyle is viable. These bacteria challenge our understanding of what life needs. We usually think of life as requiring energy input, growth, reproduction, but these organisms might go thousands of years between divisions. They don't grow in any conventional sense. They just persist, maintaining themselves, waiting in the dark and the cold and the pressure, representing life reduced to its barest essentials. It's strangely beautiful in a way. Life clinging to existence not through abundance or competition or rapid growth, but through patience and minimalism, existing at the edge of what's possible, proving that life doesn't always need to be vibrant and dynamic. Sometimes life is just quietly being, almost undetectably, in the deep sediments beneath the ocean floor. The Dumbo octopus, named for its ear-like fins, is the deepest living octopus, found at depths exceeding 7,000 meters. It flaps its fins like an elephant flaps its ears, drifting gracefully through the Hadal darkness. In the Hadal zone, where pressure exceeds 600 atmospheres and darkness is absolute, where few creatures can survive and even fewer thrive, there lives an octopus. Not a typical octopus. No crawling across rocks, no squeezing into crevices, no rapid colour changes. This is the Dumbo octopus, and it's unlike any octopus you've seen. It's named for its fins, ear-like protrusions extending from the sides of its mantle that look undeniably like the ears of Disney's Dumbo the elephant. And it uses these fins the same way Dumbo used his ears, to fly. Well, to swim. The octopus flaps these fins in a slow, graceful motion, propelling itself through the water like some kind of benthic angel. They're small, most species. They're rarely larger than 30 centimeters, soft, gelatinous, nearly translucent. They drift above the seafloor, searching for prey, small crustaceans, worms, anything they can catch. When they find food, they pounce, spreading their webbed arms over it like a blanket, engulfing it whole. No beak biting or wrestling with struggling prey, just a gentle capture and consumption. Everything about the Dumbo octopus is adapted for the Hadal zone. Its body is soft and compressible, offering no resistance to pressure. It has no ink sac. What would be the point in total darkness? Its metabolism is slow, efficient, tuned for an environment where meals are scarce. Even its reproductive strategy is unusual. Females brood multiple clutches of eggs at different developmental stages, ensuring that at least some offspring might survive even if food availability fluctuates. There's something almost endearing about Dumbo octopuses. They look gentle, almost cartoonish, with their fins and soft bodies and slow movements. They don't seem like creatures of the extreme deep. They seem too delicate, too whimsical. And yet they live deeper than almost any other octopus, thriving in conditions that crush most life. Watching footage of a Dumbo octopus, and we have footage now thanks to deep-sea cameras, is mesmerizing. It drifts through the water with a kind of effortless grace, fins flapping slowly, arms trailing, moving through the darkness like it's the most natural thing in the world. Which, for the Dumbo octopus, it is. Deep-sea creatures often have enlarged livers filled with low-density oils, helping them maintain neutral buoyancy without a swim bladder. These oils keep them suspended in the water column without expending energy to swim. Buoyancy is a challenge in the deep sea. At the surface, many fish use a swim bladder, a gas-filled organ that can be inflated or deflated to control depth. It's elegant, efficient, and works beautifully in shallow water. But in the deep sea, gas-filled structures become problematic. The pressure is so intense that maintaining a gas bubble requires enormous amounts of energy, and if a fish with a swim bladder rises too quickly, the gas expands, potentially rupturing the bladder or even forcing the stomach out through the mouth. So deep-sea fish evolved a different solution. Oils. Specifically, they accumulate large amounts of low-density lipids in their livers. A squalene is common, the same oily compound found in shark livers. Wax esters are another favourite. These lipids are less dense than seawater, providing lift without the need for gas. The liver in some deep-sea fish is enormous, sometimes making up 20% or more of the animal's body weight. It's essentially a flotation device made of fat, carefully calibrated to make the fish neutrally buoyant at its preferred depth. The fish neither sinks nor floats, but hovers effortlessly in the water column, conserving energy. This strategy has trade-offs. A huge oil-filled liver is metabolically expensive to grow and maintain, though less expensive than constantly swimming to stay aloft. And unlike a swim bladder, which can be adjusted relatively quickly, changing your buoyancy through liver lipids is slow. You can't rapidly ascend or descend. You're committed to a particular depth range, but for life in the deep sea, where energy conservation is paramount and rapid depth changes are rarely necessary, it's an effective solution. The fish drifts, liver keeping it suspended, expending minimal effort, waiting for prey or slowly searching the darkness. It's buoyancy through biochemistry, a reminder that evolution finds solutions using whatever materials are available, in this case, turning the liver into a living life jacket made of oil. Many deep-sea fish have lost their eyes entirely over evolutionary time, since sight offers no advantage in total darkness. They navigate instead through vibration sensors, chemical detection, and bioluminescent signals. In the deeper parts of the ocean, below where even bioluminescence provides useful information, the eyes become not just useless but a liability. They're complex organs that require energy to build and maintain. They're vulnerable to damage, and if they provide no benefit, if there's literally nothing to see, then evolution tends to eliminate them. And so, many deep-sea fish are blind. Not because their eyes have been damaged, but because they never develop eyes in the first place, or their eyes are reduced to tiny, non-functional remnants. The cavefish that live in underground lakes show the same pattern. Complete darkness leads to eye loss over evolutionary time, but losing eyes doesn't mean losing the ability to sense the environment. Deep-sea fish have evolved other sensory systems to navigate and hunt. Now, many have elaborate lateral line systems, rows of pressure-sensitive cells running along their bodies that detect vibrations and movements in the water. They can sense the subtle pressure waves created by swimming prey, tracking them through the darkness with remarkable precision. Chemical senses are enhanced. Olfaction, smell essentially, becomes crucial. Deep-sea fish can detect incredibly low concentrations of dissolved chemicals, following scent trails through the water to find food or mates. Some have barbels, whisker-like projections covered with taste receptors that they drag through the sediment or wave through the water, literally tasting their environment. And in the zones where bioluminescence is still common, fish have evolved to detect light without using traditional eyes. Yeah, some have simple photoreceptors on their skin or specialized light-detecting organs. They're not seeing in the way we think of vision, but they're sensing patterns of bioluminescence, flashes, glows, the presence or absence of light. There's something liberating about this in a way. We're so dependent on vision that it's hard to imagine navigating without it. But deep-sea fish prove that vision is just one way to sense the world, and not necessarily the best way in all environments. In total darkness, vibration and chemistry provide richer information than eyes ever could. Evolution isn't sentimental about complexity. If something doesn't help, it gets discarded. Eyes in the deep sea are evolutionary baggage, and over time they're simply let go, and what remains is a fish perfectly adapted to its environment, as a navigating darkness through senses we can barely imagine. The cookie cutter shark is a small deep-sea predator that takes circular chunks out of much larger animals, including whales and submarines. Its teeth form a saw-like ring that can bite through rubber and flesh with equal ease. The cookie cutter shark is only about 50 centimeters long, small for a shark, hardly intimidating by size alone, but it has developed one of the strangest feeding strategies in the ocean. It doesn't hunt fish its own size, it doesn't scavenge. Instead, it attacks animals much, much larger than itself, whales, dolphins, large fish, even submarines, and takes bite-sized chunks out of them. The technique is as clever as it is gruesome. The shark approaches its target, often attracted to the silhouette against faint light from above, as it attaches to the victim's body using its suction cup-like lips and modified pharynx. Then it sinks its teeth in. The upper teeth are small, providing grip, but the lower teeth are large, triangular, razor-sharp, arranged in a continuous cutting edge like a saw blade. With teeth embedded, the shark twists its body, using its entire muscular frame as a lever. The teeth cut in a circular motion, carving out a plug of flesh and blubber. The wound left behind is distinctive. A perfectly circular or oval crater, clean-edged, about the diameter of a cookie cutter, hence the name. For the victim, this is painful and damaging but rarely fatal. A whale can survive multiple cookie cutter shark bites. The wounds heal, leaving circular scars. Marine biologists examining whales often find dozens of these scars, and evidence of encounters with cookie cutter sharks over the years. But the shark gets a substantial meal from each bite. A chunk of energy-rich blubber or muscle that can sustain it for days. It's parasitism in a sense, or perhaps kleptoparasitism, stealing a piece of someone else's body. The shark doesn't need to kill, it just needs to bite and escape. Cookie cutter sharks have even bitten submarines. Military submarines returning from deep patrols have been found with mysterious circular damage to their rubber coating and sonar equipment. It took a while to figure out what was causing it. Surely not a shark. But yes, a shark. A small, innocuous-looking deep-sea shark with a very specialized and very effective feeding strategy. They're most active in the mesopelagic zone, migrating vertically with the deep scattering layer. During the day, they stay deep. At night, they rise toward the surface following their prey, and all the while they're looking for targets, anything large enough to be worth biting, anything slow enough to catch. It's an unusual life, not a predator in the traditional sense, not quite a parasite either, just a small shark in a big ocean, taking what it needs, one circular bite at a time. Some jellyfish in the deep sea can live for years without eating, surviving on stored energy during long periods of famine. They drift in a state of suspended animation, waiting for food to literally bump into them. Jellyfish are simple creatures in some ways. No brain, no centralized organs, just a radial body plan with tentacles, a gastric cavity, and not much else. But this simplicity is also a kind of efficiency. With so little to maintain, our jellyfish can survive on remarkably little energy. In the deep sea, where food is scarce and unpredictable, some jellyfish have taken this efficiency to an extreme. They can enter a state of reduced metabolism, slowing their life processes to near stasis. During these periods, they survive on stored energy, lipids accumulated during better times, and weight. They drift. Tentacles extended, trailing through the water, passive and patient. If something swims into those tentacles, a copepod, a small fish, a lavacean, the nematocysts fire, injecting toxin, paralyzing the prey. The tentacles contract, pulling the food toward the mouth. The jellyfish feeds, absorbs the nutrients, stores what it doesn't need immediately, and continues drifting. But if nothing comes, if weeks pass, months pass with no contact, the jellyfish doesn't panic. It doesn't search frantically for food. It just keeps drifting, metabolism slowed, burning its reserves as slowly as possible, waiting. Some species can survive years like this, years without eating. Their bodies shrink slightly as they metabolize their own tissues, but they remain alive, functional, capable of feeding again if prey appears. They're in a kind of suspended animation, though not dormant, still alive, still sensing, still capable of capturing prey, just operating on minimal power. It's a strategy well suited to the deep sea's unpredictability. You can't control when food arrives. You can't hunt effectively when prey is sparse and your mobility is limited. But you can be patient. You can reduce your needs to almost nothing and wait. And in the deep sea, patience is often rewarded. A jellyfish in the deep don't fight against the scarcity of their environment. They accept it, adapt to it, become creatures that can exist on almost nothing for years at a time. They're survivors in the truest sense, not through strength or speed, but through endurance and the ability to wait. The deep sea is home to the longest living vertebrates, Greenland sharks that can live over 400 years. They grow so slowly and live so long that some swimming today were born before Shakespeare wrote his plays. Time moves differently for the Greenland shark. While most sharks live decades, the Greenland shark lives for centuries. The oldest confirmed specimen was estimated at 392 years old, though the uncertainty in the dating means it could have been over 500 years old. Think about that timeline. A Greenland shark alive today might have been born in the 1600s. It would have been swimming in Arctic waters when European explorers first charted northern seas. It would have grown through the entire Age of Enlightenment, through the Industrial Revolution, through 2 world wars. It would have been middle-aged when humans first split the atom, and still swimming when we landed on the moon. They grow incredibly slowly, about 1 centimetre per year. Sexual maturity doesn't come until they're around 150 years old, a century and a half just to reach reproductive age. Their metabolism is sluggish, tuned to the cold Arctic and subarctic waters where they live, where temperatures hover near freezing year-round. Most Greenland sharks are partially or completely blind, parasitized by a species of copepod that attaches to their eyes. The copepod damages the cornea, creating cloudiness and eventual blindness. But the sharks don't seem particularly bothered. In the dark, cold depths where they spend much of their time, vision may not be especially useful anyway. They're scavengers and predators, eating fish, seals, carrion, whatever they can find or catch. They move slowly. They're among the slowest swimming sharks known, but they're patient. In a life measured in centuries, there's no need to rush. Scientists are still trying to understand how they live so long. Is it the cold water, which slows metabolism and aging? Is there something unique about their genetics, some mechanism that repairs damage more efficiently or resists senescence? We don't know yet. But the Greenland shark stands as a reminder that longevity is possible, that some animals measure their lives not in years but in centuries, moving through time at a pace so different from ours that it's almost incomprehensible. They're living connections to the past, swimming archives of ocean history, creatures that have witnessed changes we can only read about in books. Deep-sea corals can live for thousands of years, growing at a rate of millimeters per year in the cold, dark depths. Some deep coral colonies are older than the pyramids, quietly filtering water in the same spot for millennia. When most people think of coral, they picture tropical reefs, colourful, sunlit, teeming with fish. But corals exist in the deep sea too, and they're nothing like their shallow water cousins. These are cold water corals growing in complete darkness, filtering food from passing currents, and building structures that can persist for thousands of years. They grow slowly, agonizingly slowly. A bamboo coral might grow a few millimeters per year, a black coral even slower. At these rates, a coral colony a meter tall might be hundreds of years old. Large colonies, the ones that form significant structural features on seamounts or deep reefs, can be thousands of years old. Radiocarbon dating of deep-sea corals has revealed colonies over 4,000 years old. 4,000 years. That means some corals alive today began growing when humans were just developing writing, when the Great Pyramids of Egypt were being constructed. They've been filtering the same water in the same location through the rise and fall of civilizations, through climate shifts and ocean changes for longer than recorded human history. They're not photosynthetic. There's no light in the deep sea. Instead, they're filter feeders, extending polyps to catch particles drifting past in the current. They extract nutrients from marine snow, from zooplankton, from whatever organic matter the current brings them, and they grow, one microscopic layer at a time, building calcium carbonate or protein skeletons that accumulate over centuries. These corals create habitat. Their branching structures provide substrate for other organisms, sponges, crinoids, brittle stars, fish. Deep-sea coral communities can be remarkably diverse, supporting hundreds of species in areas that would otherwise be relatively barren. But they're fragile, because they grow so slowly they can't recover quickly from damage. Near a fishing trawl that scrapes across a deep coral reef can destroy colonies that took millennia to grow. They don't regenerate on human timescales. The damage is, for practical purposes, permanent. It's humbling to think about these corals. They exist in a time frame so different from ours. We live decades. They live millennia. We rush through life. They grow slowly, patiently, building structures that outlast empires, quietly witnessing the passage of deep ocean time. Glass sponges build intricate skeletons from silica, creating structures that look like delicate frozen lacework. Some have been found living in the same location for over 10,000 years, making them among Earth's oldest animals. Glass sponges are among the most beautiful and bizarre organisms in the deep sea. They're sponges, yes, but unlike the soft, fleshy sponges you might find in shallow water, glass sponges build elaborate skeletons from silica, essentially glass. The result is a structure that looks impossibly delicate, like someone wove a basket out of spun glass fibres. The skeletons are intricate lattices, geometric patterns of silica spicules fused together at their tips. Light passes through them. They're translucent, fragile-looking, beautiful in an alien way. And yet they're functional. These structures provide support, create chambers and channels through which water flows, house the living tissues of the sponge. Glass sponges are filter feeders. They pump water through their bodies, extracting bacteria and tiny organic particles. A single large glass sponge can filter thousands of litres of water per day. The water enters through tiny pores, flows through internal channels and exits through a large opening at the top. A living water filtration system built from glass, and they're old, incredibly old. Individual glass sponges can live for thousands of years. One species, the Antarctic glass sponge Scolomastra jubini, has been estimated at over 10,000 years old based on growth rates and size. 10,000 years. That's older than agriculture, older than the oldest pyramids, older than any tree alive today. They grow slowly, sometimes fractions of a millimetre per year. At that rate, a large sponge represents millennia of continuous growth. They sit on the seafloor, filtering water, growing imperceptibly, accumulating mass so slowly that it's almost geological. There are even glass sponge reefs in some locations, living reefs built by colonies of sponges growing together, creating three-dimensional structures that can be meters high and kilometers long. These reefs were thought to be extinct, known only from fossils, until they were rediscovered off the coast of British Columbia in the 1980s. Living fossils, building structures in the deep, quietly persisting while the world above changed beyond recognition. Glass sponges are proof that age isn't always about activity. You don't need to be dynamic, fast-growing, rapidly reproducing to persist across millennia. You can be slow, patient, filter feeding in the same spot for 10,000 years, build in a glass skeleton particle by particle, simply existing through vast stretches of time. The dragonfish has teeth so large they don't fit inside its mouth, giving it a permanently menacing appearance. But in the deep sea, my intimidation is visible only when its bioluminescence switches on. The dragonfish looks like something from a nightmare. Long, eel-like body, enormous jaws lined with teeth that are comically oversized, fangs that stick out even when the mouth is closed because they literally don't fit inside, a chin barbell that dangles below its head, tipped with a bioluminescent lure. It's all teeth and darkness and menace. But here's the thing, in the deep sea, appearance doesn't matter unless you can see it. And in complete darkness, the dragonfish is invisible. Those terrifying teeth, that elongated body, the overall nightmare aesthetic, none of it is visible until the dragonfish chooses to light up. Many dragonfish species have photophores, bioluminescent organs, scattered along their bodies. They can control these, flashing them on and off, creating patterns of light. Some use this for communication, signaling to potential mates or rivals. Others use it for hunting, creating sudden flashes to startle or confuse prey. And here's where it gets interesting. Some dragonfish produce red bioluminescence. Most deep-sea creatures can't see red light. Their eyes are tuned to blue and green, the colours that penetrate deepest in water. But dragonfish have red sensitive vision. They've evolved the ability to see a colour most deep-sea animals can't detect. This gives them a private spotlight. They illuminate prey with red light, which they can see but the prey can't. It's like hunting with infrared goggles in a world where everyone else is colorblind. The dragonfish can track prey movements, judge distance, line up an attack, all while remaining invisible to its target. When it strikes, those enormous teeth make sense. They're hinged, allowing the jaws to open extraordinarily wide. The dragonfish can engulf prey nearly as large as itself, those teeth preventing escape, holding the struggling victim until it's to be swallowed. In footage of dragonfish, they often appear hovering in the water, barbel dangling, mouth slightly open, teeth jutting out at angles. They look menacing, yes, but also strangely patient. They're not rushing. They're waiting, invisible in the darkness, ready to light up and strike when prey comes within range. The deep sea rewards strange adaptations, and the dragonfish has them in abundance. Oversized teeth, red bioluminescence, private vision in a dark world. It's a predator sculpted by darkness, its appearance irrelevant except in the moments when light reveals it, and by then it's too late. Some deep-sea creatures produce red bioluminescence, which most deep-sea animals can't see, creating a private spotlight for hunting. It's like having infrared vision in a world where everyone else is colorblind. We've touched on this with the dragonfish, but it's worth exploring more deeply because it's such an elegant solution to a common problem. How do you find prey in complete darkness without alerting the prey to your presence? Most bioluminescence in the deep sea is blue or blue-green. This makes sense. Blue light penetrates seawater better than other colours, and most deep-sea eyes are sensitive to blue wavelengths. If you're going to produce light, you might as well produce light that can be seen. But producing visible light has a cost. When you illuminate something, you illuminate yourself. A flash of bioluminescence might reveal prey, but it also reveals you to predators. It's a trade-off, and evolution is constantly balancing the benefits against the risks. Some organisms found a workaround. Produce light that your prey can't see. Red light has longer wavelengths and is absorbed quickly by seawater, so it doesn't travel far. More importantly, most deep-sea animals don't have red-sensitive vision. Their eyes are tuned to detect blue light because that's what's available, either from bioluminescence or from the faint sunlight that penetrates the mesopelagic zone. But a few predators, dragonfish, loosejaw fish, some others, evolved both the ability to produce red light and the visual pigments to see it. They have private searchlights. They can illuminate their surroundings, hunting visually in the darkness, without their prey having any idea they're being watched. It's asymmetric information made literal. The predator has access to visual data that the prey doesn't even know exists. From the prey's perspective, it's still in total darkness. From the predator's perspective, the world is lit, dimly, briefly in red, but lit. This is evolutionary innovation at its finest. Not just developing bioluminescence, which many organisms did, but developing a specific wavelength of bioluminescence that creates a competitive advantage. It's the biological equivalent of night vision goggles in a world without artificial light. And it's a reminder that the deep sea isn't just dark, it's dark in complex ways. There are layers of visibility, wavelengths that some can see and others can't, thus private channels of information accessible only to those with the right adaptations. The darkness isn't uniform, it's structured, nuanced, full of hidden asymmetries that predators and prey navigate in a constant evolutionary arms race. The fangtooth fish has the largest teeth relative to body size of any fish in the ocean. Special pockets in its skull allow it to close its mouth without stabbing itself with its own teeth. The fang-toothed fish is a creature of extremes. It's not large. Most are only about 15 centimeters long, but its teeth are absolutely enormous, disproportionate to the point of absurdity. The two fangs on the lower jaw are so long that if the fish didn't have special accommodations, it would impale its own brain when it closed its mouth. Evolution provided those accommodations. On either side of the fish's skull, there are pockets, bony sockets, that the teeth slide into when the mouth closes. The fangs nestle into these pockets, passing harmlessly on either side of the brain. It's a precise fit, like a sword sliding into a scabbard. Without these sockets, the fish would be unable to close its mouth without killing itself. Why such enormous teeth? The fangtooth is a deep-sea predator, living in the bathypelagic zone where food is scarce. When it encounters prey, it needs to ensure capture on the first attempt. Those massive fangs serve as gates. Once something is between them, it's not escaping. The teeth angle inward, creating a cage that tightens as the victim struggles. The fangtooth has other adaptations for its harsh environment. Its body is dark, nearly black, making it invisible in the surrounding darkness. It has a compressed, deep-bodied shape rather than the elongated eel-like form of some deep-sea predators. Its eyes are relatively small. Vision is less important than other senses at the depths where it lives. Like many deep-sea fish, it undergoes vertical migration, moving up toward the mesopelagic zone at night to feed and descending to deeper, safer waters during the day. This migration can cover hundreds of vertical meters, a journey that requires careful regulation of internal pressure and buoyancy. Young fangtooth look completely different from adults, so different that they were originally classified as a separate species. The juveniles have long spines protruding from their heads, light-coloured bodies, and normal-sized teeth. As they mature, they transform, losing the spines, darkening, growing those characteristic fangs. It's a reminder that deep-sea fish often look strange because they're optimized for specific challenges. The fangtooth's enormous teeth aren't decorative or intimidating. They're functional, essential for capturing prey in an environment where every meal counts and missed opportunities could mean weeks or months of starvation. The teeth are so important that the fish's skull evolved special structures just to accommodate them. Form following function, taken to an extreme. Deep-sea amphipods, tiny crustaceans, have been found even in the deepest ocean trenches, thriving at depths exceeding 10,000 meters. They represent some of the most pressure-tolerant animals on Earth. Amphipods are small, shrimp-like crustaceans that you can find almost anywhere there's water. They scuttle through kelp forests, burrow in beach sand, swim in the open ocean. They're ubiquitous, adaptable, successful, but perhaps nowhere are they more remarkable than in the Hadal zone, where they live at pressures that would crush almost any other animal. At depths exceeding 10,000 meters, pressure reaches over 1,000 atmospheres. The weight of the entire water column presses down with a force of about 8 tons per square inch. Proteins denature, cell membranes become rigid. Biological molecules that function perfectly at surface pressure malfunction catastrophically in the deep. And yet, amphipods thrive there. They crawl across the sediment in the Mariana Trench, the Tonga Trench, the Kermadec Trench, the deepest places on Earth. They're scavengers, feeding on whatever organic matter reaches the bottom. Marine snow, dead fish, whale falls if they're lucky. Some species are quite large by amphipod standards, Yasi reaching several centimeters in length. How do they survive such pressure? The answer lies in cellular and molecular adaptations we're only beginning to understand. Their cell membranes contain special lipids that remain fluid under high pressure. Their proteins have unique structures with extra bonds and modified amino acid sequences that keep them functional when most proteins would collapse. Even their DNA has adaptations, protective molecules that stabilize the double helix under extreme conditions. These amphipods can't survive at surface pressure. If you bring them up too quickly, the drop in pressure is lethal. They're as adapted to high pressure as we are to atmospheric pressure. For them, the Hadal zone isn't extreme, it's home. Surface conditions would be extreme. Scientists have used baited cameras and traps to study these creatures, lowering equipment to the deepest trenches and waiting to see what arrives. Amphipods often appear within hours, sometimes in large numbers, attracted by the scent of bait. They swarm over food, feeding frantically, taking advantage of the rare windfall. These tiny crustaceans represent the edge of animal life on Earth. Below them, in the deepest parts of the trenches, we find primarily microbes. Amphipods are among the last complex animals, the final holdouts as you descend into the abyss. And they're there not just surviving, but thriving. Proof that life's tolerance for extreme conditions extends far beyond what we once thought possible. The Hadal snailfish holds the record for the deepest living fish, filmed at 8,178 meters in the Mariana Trench. It's a small, almost translucent creature that looks almost ghostly, perfectly adapted to crushing pressure. For decades, scientists wondered, what's the deepest a fish can live? Fish have skeletons, complex organs, sophisticated nervous systems, all structures that seemed like they might have depth limits. Surely there's a point where pressure simply becomes too much, where no fish, no matter how well adapted, can survive. The Hadal snailfish keeps pushing that limit deeper. In 2017, researchers captured footage of a snailfish at 8,178 meters in the Mariana Trench, the deepest fish ever filmed. It's a small creature, perhaps 20 centimeters long, with translucent, almost gelatinous flesh. You can see through its body to the organs inside. It has tiny eyes, mostly non-functional, vestigial. Its bones are minimal, barely calcified, giving it a soft, more flexible structure. It doesn't look like a typical fish. It looks fragile, delicate, like it might dissolve if you touched it. But this apparent fragility is actually strength. The snailfish has almost no hard structures to compress under pressure. Its body is mostly water and soft tissue, which don't compress significantly. It's built to yield to pressure rather than resist it. The snailfish feeds on tiny crustaceans, particularly amphipods. It's a predator of sorts, though not a fearsome one. More of a gentle hunter, moving slowly across the seafloor, occasionally lunging to capture prey. Its metabolism is slow. Its movements are economical. Everything about it is tuned for energy conservation in an environment where food is desperately scarce. There may be a depth limit for fish, though we haven't found it yet. Some scientists theorize that below about 8,500 meters, the protein trimethylamine N-oxide, TMAO, which fish use to protect their proteins from pressure, becomes unstable. TMAO helps stabilize proteins under high pressure, but at extreme depths, even TMAO might break down. If this is true, there may be a hard limit, a depth beyond which fish, regardless of adaptation, simply can't exist. But the Hadal snailfish lives right at that boundary, pushing against the theoretical limits of fish physiology. It's proof that evolution can find solutions to almost any problem, given time and pressure, both evolutionary pressure and literal physical pressure. And it's a reminder that we're still discovering the boundaries of life, still finding organisms in places we thought were too extreme for complex animals. The deepest fish, almost ghostly, moving through crushing darkness in the deepest trench on Earth. It's a fitting image for the frontier of life's adaptability. Many deep-sea creatures have gelatinous, watery bodies that compress very little under extreme pressure. They're built more like water balloons than solid structures, making them nearly immune to being crushed. There's a fundamental principle of physics at work in the deep sea. Water doesn't compress, not significantly anyway. You can apply enormous pressure to water, and its volume will decrease only slightly. This is why the ocean doesn't collapse under its own weight. Water at the bottom of the ocean is only about 5% denser than water at the surface, despite the tremendous pressure. And if you're a creature made mostly of water, if your body is 95% or more water, is with minimal gas spaces and few rigid structures, then you compress just as little as the water around you. Pressure becomes almost irrelevant. The water inside you pushes back with the same force as the water outside you. Equilibrium. This is why so many deep-sea creatures look gelatinous, translucent, almost insubstantial. They're not weak, they're optimized. A jellyfish at 1,000 meters experiences the same pressure inside and outside its body. There's no stress on its tissues because there's no pressure differential. It's the same principle that allows you to dive deep in water without feeling crushed. As long as your air spaces, lungs, sinuses, equalize with the surrounding pressure, you're fine. Deep-sea fish take this to an extreme. Their flesh is watery, almost jelly-like. Their bones are reduced or replaced with cartilage. Their bodies are soft, flexible, compressible, but only because there's nothing rigid to compress. They yield to pressure without resistance. This is why bringing deep-sea creatures to the surface can be fatal. It's not the pressure change itself that kills them. It's the release of pressure. Gas spaces that were compressed at depth suddenly expand. Tissues that were under equilibrium experience differential pressure. In some cases, the body ruptures. In others, the creature simply can't function. Its proteins and enzymes evolve to work under high pressure and fail at surface pressure. The deep sea favors softness over rigidity, flexibility over strength, water over air. It favors creatures that don't fight pressure but accept it, becoming one with their environment, and in doing so, why these creatures achieve something remarkable. They live in a place where pressure would crush almost anything else, and they do it effortlessly, their soft bodies in perfect equilibrium with the crushing depths around them. Bioluminescent bacteria sometimes live freely in the water, creating glowing clouds when disturbed. In these moments, the deep sea briefly sparkles like an underwater starfield. We've talked about bioluminescence in the context of symbiosis, bacteria living inside fish or squid, providing light in exchange for nutrients. But many bioluminescent bacteria live freely in the water column, unattached, drifting with the currents like any other plankton. These free-living bacteria don't glow constantly. That would waste energy. Instead, they use a system called quorum sensing. They detect the density of other bacteria around them and only activate their bioluminescence when enough bacteria are present. It's a form of bacterial communication, a way of coordinating behavior across a population. but from a human perspective, the result is beautiful. When something moves through water containing these bacteria, a submersible, a whale, a current, even a falling particle, the disturbance triggers bioluminescence. The bacteria light up in response to the physical agitation, and suddenly the water sparkles. It's not like surface bioluminescence, the kind you might see in a bioluminescent bay where dinoflagellates light up when you wave your hand through the water. Deep-sea bacterial bioluminescence is often dimmer, more diffuse, but in the complete darkness of the deep ocean, even a faint glow is dramatic. Imagine swimming through the abyss and leaving a trail of light behind you. Every movement of your fins creates glowing swirls. Every kick disturbs bacteria that respond with brief flashes. You're writing in light on the canvas of darkness, creating temporary constellations that fade as quickly as they appear. Some deep-sea animals use this to their advantage. When attacked, they release bioluminescent bacteria or trigger bioluminescence in the surrounding water, creating a glowing cloud that confuses predators or attracts larger predators to the scene, the biological equivalent of setting off a burglar alarm. The deep sea, we often say, is dark, but it's not uniformly dark. It's punctuated by moments of light, flashes, glows, clouds of bioluminescence created by bacteria responding to disturbance. In these moments, the darkness becomes a canvas, and life paints on it with light, creating brief, beautiful patterns before the darkness returns. The sperm whale can dive over 2,000 meters deep and hold its breath for up to 90 minutes while hunting giant squid. They're one of the few warm-blooded visitors to the cold, high-pressure depths. The sperm whale is a creature of two worlds. At the surface, it breathes air, socializes with other whales, basks in sunlight. But when it dives, it enters a realm completely foreign to most air-breathing life. The deep mesopelagic and bathypelagic zones, where pressure is enormous and darkness is complete. They dive deep, regularly exceeding 1,000 meters, sometimes reaching 2,000 meters or more. The deepest confirmed dive was over 2,900 meters. At those depths, the pressure is crushing. The cold is near freezing. There's no light, and the whale is holding its breath the entire time, hunting in darkness for one of its primary prey items, giant and colossal squid. How do they do it? Through a suite of remarkable adaptations. Their lungs collapse during deep dives, preventing nitrogen from dissolving into the blood, the same nitrogen that causes decompression sickness in human divers. Their muscles are packed with myoglobin, a molecule that stores oxygen, giving the muscles a dark red, almost black colour. A whale's muscles can store far more oxygen than human muscles, allowing extended periods without breathing. Their heart rate drops dramatically during a dive, from 60 to 70 beats per minute at the surface to as low as 3 to 5 beats per minute at depth. Blood flow is redirected away from non-essential organs and toward the brain and heart. The whale enters a state of controlled hypoxia, managing its oxygen budget with extraordinary precision, and they hunt. In complete darkness, using echolocation, clicking sounds that bounce off objects and return as echoes. The sperm whale has the largest brain of any animal on Earth, and much of it is devoted to processing these echoes, creating a sonar picture of the environment. They can locate squid in the darkness, track their movements, predict their escapes, and capture them despite the squid's size, intelligence, and defensive capabilities. The battles must be spectacular. Sperm whales often bear scars. circular marks from squid suckers, evidence of struggles in the deep darkness. Sometimes whales surface with squid beaks embedded in their jaws. The squid don't go quietly. After a deep dive, the whale returns to the surface and breathes dozens of breaths over several minutes, reoxygenating its blood and muscles, preparing for the next dive. It's an exhausting lifestyle, but the deep sea offers a food source that few other predators can access. This sperm whale bridges two worlds, bringing the sophistication of mammalian physiology into depths where few warm-blooded creatures dare to venture. Deep-diving whales may experience nitrogen narcosis, a dangerous condition for human divers, but seem unaffected due to special adaptations. Their bodies compress their lungs during descent, preventing nitrogen from dissolving in their blood. When human divers descend too deep while breathing compressed air, and they sometimes experience nitrogen narcosis, a condition caused by nitrogen dissolving into the bloodstream at high pressure. It causes euphoria, confusion, impaired judgment. Divers call it rapture of the deep. It's dangerous because it can lead to poor decision-making at depth, where mistakes are often fatal. Whales, breathing air at the surface and then diving to extreme depths, should theoretically experience this too. They have nitrogen in their lungs. They experience high pressure. So why don't they get nitrogen narcosis? The answer is elegant. Their lungs collapse. As a whale dives, increasing pressure compresses its flexible rib cage. The lungs collapse inward, pushing air into the upper respiratory passages, the trachea and bronchi, where gas exchange doesn't occur. The alveoli, where oxygen and nitrogen would normally diffuse into the blood, collapse and stop functioning. With the alveoli collapsed, no nitrogen can dissolve into the bloodstream. The whale has effectively isolated the gas in its lungs from its circulatory system. It's living on the oxygen already dissolved in its blood and muscles, the stores it built up during those dozens of breaths at the surface. This is why whales can dive so deep without suffering from nitrogen narcosis or decompression sickness. They're not breathing compressed air at depth like a human scuba diver. They're breath-hold diving, and their bodies have evolved to prevent nitrogen from entering the blood during the dive. It's a completely different strategy from what human divers do. We bring air with us and breathe it continuously at depth, which requires careful management of nitrogen levels and decompression schedules. Whales take a big breath, collapse their lungs to seal off the nitrogen, and live on stored oxygen. It's simpler in some ways, though it requires extraordinary oxygen storage capacity and metabolic control. Evolution found a solution to the nitrogen problem millions of years before humans even thought about diving deep. The whale's collapsing lung isn't a weakness. It's an adaptation that allows routine access to depths that remain challenging for humans even with modern technology. Elephant seals can dive to depths of 2,000 meters and spend up to 80% of their lives underwater. They sleep during these deep dives, descending into a half-conscious glide while holding their breath. Elephant seals are among the most accomplished divers in the mammalian world. They spend most of their lives at sea, coming ashore only to breed and molt. During their months at sea, they dive almost continuously, dive after dive, sometimes for hours at a time, descending to depths that would kill most air-breathing animals. Their dives regularly exceed 1,000 meters. Some reach 2,000 meters or more. They can hold their breath for over an hour, though most dives are 20 to 30 minutes. And they do this dozens of times per day, day after day, for months on end. They're hunting during these dives, primarily for deep-sea fish and squid. But here's what's remarkable. They also sleep while diving. Sleep is a biological necessity. All mammals need it. But how do you sleep when you're underwater, holding your breath, navigating in darkness? These seals have worked out a solution. Then, during what researchers call drift dives, the seal descends to depth, stops swimming, and enters a sleep-like state. Its body becomes limp. It drifts downward in a slow, spiraling glide, conserving energy, its brain showing the slow wave patterns characteristic of sleep. The seal is sleeping underwater while holding its breath, descending through hundreds of meters of ocean, eventually perhaps triggered by oxygen levels dropping below a threshold, or by proximity to the sea floor. The seal rouses slightly and begins swimming back to the surface. It might not even fully wake. It's operating on autopilot, following an ingrained program: dive, drift, sleep, return, breathe, repeat. This allows elephant seals to get the rest they need while remaining at sea. They don't need to haul out on ice or land every night. They can stay in the water continuously, sleeping in fragments during their dives, maximizing their time in the foraging grounds. The adaptations that make this possible are similar to those of whales: high myoglobin concentration in muscles, collapsing lungs to prevent nitrogen absorption, bradycardia, slowed heart rate, to conserve oxygen, blood flow redistribution. But the sleeping aspect adds another layer of complexity. The seal needs to maintain enough neural function to eventually wake up and surface, while shutting down enough brain activity to actually rest. It's a testament to evolution's creativity. The need to sleep and the need to dive don't conflict. They're integrated into a single behavior. The elephant seal turned a constraint into an opportunity. Sleeping through its dives, you're drifting through the darkness in a state between consciousness and unconsciousness, living a life split between the surface world of air and the deep world of pressure and cold. The ocean's twilight zone, 200 to 1,000 meters, contains more fish biomass than all the rest of the ocean combined. It's a vast, largely unharvested resource that migrates up and down daily in the largest animal migration on Earth. The mesopelagic zone, the twilight zone, is one of the least understood parts of the ocean, despite containing what may be the largest animal biomass on Earth. Estimates vary widely because the zone is difficult to study, but some suggest there are billions of tons of fish in the mesopelagic, more than all the fish we catch globally in a year, more than all the fish in surface waters, a vast, mostly unseen population occupying the dim waters between the surface and the deep. Most of these fish are small: lanternfish, bristlemouths, hatchetfish. Individually they're tiny, often just a few centimeters long, but collectively they represent an enormous reservoir of biomass, and every night they do something extraordinary. They rise. This is the Deal vertical migration. Deal meaning daily, vertical meaning up and down. As the sun sets and darkness falls, fish in the mesopelagic zone ascend hundreds of meters toward the surface to feed on zooplankton and small prey. They spend the night in the upper ocean, taking advantage of the abundant food there. Then, as dawn approaches, they descend back into the twilight zone, where the dim light provides some protection from visual predators. The scale of this migration is staggering, and billions upon billions of fish, moving vertically through hundreds of meters, twice per day, every day. It's the largest migration of animals on Earth in terms of biomass, far exceeding the famous migrations of wildebeest or caribou or any terrestrial animal. This migration has profound effects on ocean ecology. The fish feed near the surface and defecate at depth, transporting carbon and nutrients from surface waters into the deep ocean. They're a biological pump, moving organic matter downward, sequestering carbon that might otherwise remain in the atmosphere. In recent years, there's been increasing interest in harvesting mesopelagic fish as a resource. For fish meal, for omega-3 extraction, for various industrial purposes, the biomass is there, vast and largely untapped. But the potential ecological consequences are poorly understood. These fish play roles we're only beginning to appreciate. Removing them could disrupt carbon cycling, affect predator populations, alter the deep ocean's food web in unpredictable ways. For now, the twilight zone remains mostly unexploited. The fish rise and fall night after night in their ancient rhythm, carrying out the largest migration on Earth in the dim space between sunlight and darkness. Every night, billions of organisms rise from the deep ocean toward the surface to feed, then descend again before dawn. This vertical migration moves more biomass than any other daily movement of animals on the planet. We've mentioned this migration already, but it's worth dwelling on because it's so fundamental to how the ocean works. Every night as you're falling asleep, billions of creatures are rising through hundreds of meters of water, and every morning as you wake they're descending again. Why rise at night? The answer is predation risk. During the day, the surface ocean is well lit. Visual predators, fish, seabirds, marine mammals, can easily spot and catch small prey, but at night darkness provides cover. The small fish and zooplankton that live in the twilight zone can safely ascend to feed on the abundant plankton near the surface without being easily seen. Why not just stay near the surface? Because during the day, the risk is too high. Better to spend daylight hours in the dim twilight zone, where visual predators have a harder time hunting, than commute to the surface each night to feed. This creates a daily rhythm, a pulse in the ocean's vertical structure. At dusk, the ascent begins. Most sonar operators noticed this decades ago, a layer of echoes that rose from depth each evening. They called it the deep scattering layer, and for a while they thought it might be the seafloor. But the seafloor moved, rising hundreds of meters each night and sinking again each morning. Eventually they realized it was animals, countless small fish and zooplankton so numerous that they reflected sonar signals as if they were a solid surface. The energy expenditure is enormous, swimming hundreds of meters up then hundreds of meters down every single day. But the trade-off is worth it. Access to food at the surface, safety from predators during the day. It's a commute, essentially, the longest daily commute in the animal kingdom, and it connects the surface and the deep in a continuous cycle. Carbon fixed by photosynthesis at the surface is consumed by zooplankton, which are eaten by small fish, which defecate and die at depth, transporting that carbon into the deep ocean. The migration is an ecological conveyor belt, moving energy and nutrients vertically through the water column, linking ecosystems that would otherwise be separate. Every night, while we sleep, the ocean pulses, billions of small lives moving upward through darkness, feeding, then retreating before the sun returns. It's been happening every night for millions of years, a rhythm older than human civilization, as fundamental to the ocean as tides. The deep, scattering layer is a horizontal zone that appears on sonar, caused by countless small organisms reflecting sound waves. Early sonar operators thought they'd discovered the seafloor at 300 meters until it moved. Imagine you're operating sonar on a ship in the 1940s, exploring the ocean. You send sound pulses down into the water and wait for echoes. You expect to see the seafloor, a solid reflection from the bottom. But instead you see something strange. A layer of echoes at around 300 to 500 meters depth. A horizontal band that looks for all the world like a false seafloor. You record it, you note its depth, and then, as evening approaches, you notice something impossible. The layer is moving, rising, ascending through the water column. By nightfall it's reached 100 meters or shallower. Then, at dawn, it descends again. This was the deep scattering layer, and for a while it was a mystery. What could possibly create an echo strong enough to mimic the seafloor yet move up and down with the sun? The answer, eventually discovered, was life. The layer consisted of countless small organisms, fish, squid, shrimp, jellyfish, each individually too small to create much of a sonar echo, but collectively so numerous that they reflected sound waves as if they were a solid surface. These were the animals of the Deal vertical migration, rising to feed at night and descending during the day. Different organisms contribute to the scattering layer. Fish with gas-filled swim bladders are particularly good at reflecting sound. Squid, shrimp, and other creatures with hard structures or air spaces also contribute. Even some zooplankton, if dense enough, can create noticeable echoes. The discovery of the deep scattering layer was one of the first hints at just how much life exists in the ocean's twilight zone. Before this, scientists had underestimated the biomass at intermediate depths. They knew about surface plankton and about deep-sea communities at hydrothermal vents, but the mesopelagic zone was thought to be relatively sparse. The scattering layer proved otherwise. It was proof of a vast, unseen population living in the dim waters between surface and deep, moving daily in a migration that can be tracked with sonar. A layer of life so dense it looked like rock until it started moving. Deep-sea sediments contain a complete record of Earth's climate history, with layers documenting millions of years of ocean conditions. Scientists call these sediments like reading tree rings, ESA's revealing ancient temperatures and atmospheric composition. The deep ocean floor is more than a resting place for marine snow and manganese nodules. It's an archive, a library written in mud, recording millions of years of Earth's climate history, in layers so precise you can sometimes distinguish individual years. When scientists want to understand past climate, to know what temperatures were like during ice ages, what the atmosphere contained before humans industrialized, how ocean chemistry has changed over millennia, they go to the deep sea. They lower drill rigs from research vessels and extract cores, long cylinders of sediment pulled up from the seafloor, sometimes tens or even hundreds of meters long. Each layer in that core represents a moment in time. The deepest layers are oldest, deposited millions of years ago. The topmost layers are youngest, deposited recently. And in between, year after year, century after century, the sediments accumulated, preserving information about the ocean and atmosphere above. What information? All kinds. The species of Foraminifera, microscopic shelled organisms, present in each layer tell us about water temperature and salinity. Different species prefer different conditions, so their presence or absence reveals what the ocean was like when that layer was deposited. The chemical composition of their shells tells us even more. The ratio of oxygen isotopes in the calcium carbonate reveals ocean temperature and ice volume. More of the heavy isotope means colder temperatures and more water locked up in glaciers. Other measurements reveal atmospheric CO2 levels, ocean pH, primary productivity, and even wind patterns based on the distribution of wind-blown dust. The sediments record volcanic eruptions, asteroid impacts, the opening and closing of ocean gateways as continents shifted. They document the slow orbital variations that drive ice ages, the sudden warming events that punctuated glacial periods, the long-term trends spanning millions of years, and the resolution can be extraordinary. In some locations, where sedimentation rates are high and bioturbation, the churning of sediments by organisms, is low. Scientists can distinguish individual years. They can see the signal of historical events, industrial revolution, CO2 increases, nuclear weapons tested from the 1950s, even major volcanic eruptions that altered global climate for a season. The deep ocean floor is patient. It receives whatever falls from above and preserves it. Layer upon layer, year upon year, it builds a record more complete and more accurate than any written by humans. And when we drill into it and bring those cores to the surface, we're reading our planet's biography, written in the language of microscopic shells and chemical traces, telling stories that go back further than any oral tradition, any written record, any human memory. The deep ocean has lakes and rivers of its own, brine pools where super salty water is denser than surrounding seawater and collects in depressions. These underwater lakes have shores, waves, and are toxic to most animals that swim into them. Imagine diving in a submersible, descending through the water column and encountering a lake. Not a metaphorical lake, an actual lake, with a distinct surface, visible shores, even small waves rippling across its surface. Except this lake is underwater at the bottom of the ocean, filled with water so salty and dense that it doesn't mix with the seawater above it. These are brine pools, and they're among the strangest features of the deep ocean. They form in places where salt deposits, ancient evaporates from when ocean basins were isolated and partially dried up, are buried beneath seafloor sediments. Over time, seawater percolates down through cracks, dissolves the salt, becomes extremely concentrated, and then seeps back up. This brine is much denser than normal seawater, sometimes several times denser, so it doesn't rise and mix. Instead, it flows downhill along the seafloor like a heavy liquid and collects in depressions. The result is a lake at the bottom of the ocean. The interface between brine and seawater is sharp. You can see it clearly on video. It looks like a surface shimmering slightly from density differences. Objects can float on it. If you dropped something into a brine pool, it would sink through the normal seawater and then float on the denser brine, just like ice cubes floating in a drink. The brine itself is toxic to most marine life. The salinity is extreme, sometimes 8 or 9 times saltier than normal seawater. Oxygen levels are often low or absent because the dense brine doesn't mix with the oxygen-rich water above, and in some brine pools, dissolved gases like methane or hydrogen sulfide add to the toxicity. Animals that swim into brine pools often die. Their bodies accumulate at the shore or sink into the brine, creating eerie scenes of preserved carcasses, fish, crabs, eels, frozen in death by the toxic water. But life exists at the margins. Mussels cluster at the shore of brine pools, farming chemosynthetic bacteria that use the methane and sulfide seeping from the pool. Tube worms extend into the toxic zone, tolerating conditions that would kill most animals. Bacteria thrive in the brine itself, performing unusual metabolisms adapted to the extreme salinity. Some brine pools have currents, flows of brine from one depression to another, creating underwater rivers. The Gulf of Mexico has several large brine pools where these flows have carved channels in the sediment, creating riverine features complete with banks and meanders. It's surreal. Lakes under the ocean, rivers flowing across the seafloor, shores you can see from a submersible, waves on a surface that's already underwater. The deep ocean takes familiar concepts and reconstructs them in alien configurations, by creating landscapes that shouldn't exist but do. Hagfish produce slime that can expand to 10,000 times its volume when threatened, clogging the gills of predators. A single hagfish can turn a bucket of water into a thick gel in seconds. The hagfish is often dismissed as primitive, disgusting, the bottom feeder of bottom feeders. It's eel-like but not an eel, jawless, nearly blind, scavenging on dead and dying animals at the seafloor. It burrows into carcasses and eats them from the inside out, tying its body in knots to tear off chunks of flesh. It's not winning any beauty contests, but the hagfish has one of the most effective defense mechanisms in the ocean: slime. Extraordinary, physics-defying slime. When threatened, grabbed by a predator, handled by a researcher, just stressed in any way, the hagfish releases slime from glands along its body. At first, it's just a small amount of viscous material, but as soon as it contacts seawater, it expands dramatically. A teaspoon of slime can expand to fill several gallons of water, turning it into a thick, fibrous gel. The slime is made of mucus and protein threads, extremely fine fibers that uncoil and entangle when released, creating a network that traps water and forms a gel. It happens in seconds. One moment, a predator fish has a hagfish in its mouth. The next moment, its gills are clogged with thick, suffocating slime. The fish gags, releases the hagfish, tries desperately to clear its gills. The hagfish escapes, often having tied itself in a knot to wipe off the excess slime from its own body. The expansion factor is astonishing. Our estimates suggest the slime can expand up to 10,000 times its original volume. A small amount of slime material becomes a huge amount of gel. It's one of the most efficient defensive substances in nature. Minimal energy investment, maximum defensive effect. Researchers have tried to keep hagfish in aquariums. It rarely ends well. If the hagfish gets stressed, it releases slime. The slime expands, fills the tank, clogs filters, coats everything. You can't just rinse it off. It's persistent, sticky. You essentially have to drain the tank and start over. The hagfish itself seems unbothered by its own slime. It can tie itself in knots, using the knot to wipe slime off its body, sliding the knot from head to tail like a squeegee. Within minutes it's clean, ready to produce more slime if threatened again. Evolution equipped the hagfish with a simple but devastatingly effective defense. Turn the water around you into a suffocating gel. It's worked for hundreds of millions of years. Hagfish have existed largely unchanged since before the dinosaurs, defended by slime, scavenging the deep, survivors in the truest sense. Deep-sea worms have been found living in sediments 1.5 kilometers beneath the seafloor, in rock pores filled with water. Life persists even in the ocean's basement, in total darkness and crushing pressure. When we think about the ocean, we usually think about the water column, the space from surface to seafloor. But there's another dimension, depth into the seafloor itself. And life extends down into those sediments far deeper than most people realize. Scientists drilling into the ocean floor for research cores have found living organisms, bacteria, archaea, even multicellular worms, at depths of over 1 kilometer beneath the seafloor. These aren't fossils. They're alive, metabolically active, existing in the tiny pore spaces between sediment grains or in fractures in the underlying rock. The conditions are extreme in ways different from the water column. There's no light, of course. These organisms are buried under kilometers of sediment and water. Pressure is enormous. Temperature often increases with depth as you get closer to the Earth's interior, so organisms at depth can be living in near boiling conditions. Oxygen is usually absent. The only energy sources are chemical, dissolved minerals, organic matter buried millions of years ago, reactions between water and rock. And yet, life exists there. Bacteria perform chemosynthesis, extracting energy from iron oxidation, sulfate reduction, methanogenesis. They live incredibly slowly. Reproduction might occur once every 1,000 years or longer. Their metabolic rates are so low they're difficult to measure. The discovery of this deep subsurface biosphere, sometimes called the deep life or intraterrestrials, has fundamentally changed our understanding of where life can exist. The total biomass in the subsurface might rival or exceed the biomass in all surface ecosystems. It's a huge reservoir of life we didn't even know existed until recently. Some scientists speculate that life might have originated in the subsurface, in hydrothermal systems within the crust, rather than in surface oceans or tidal pools. The subsurface provides stable conditions, protection from surface catastrophes like asteroid impacts, and access to chemical energy from rock-water interactions. And if life can exist kilometers beneath the ocean floor on Earth, what about other planets? Mars, for instance, might have a subsurface biosphere even if its surface is barren. Europa's ocean likely has a rocky floor with similar conditions to Earth's deep ocean. Could there be life in the sediments or rock beneath Europa's ocean? The deep subsurface is literally the basement of the biosphere, and it's inhabited. Life doesn't stop at the seafloor, it continues down into the sediments, into the rock, existing in spaces so small and conditions so extreme that it challenges our definitions of habitability. The deep ocean is deep in more ways than one, and the deep biosphere, microbes living in seafloor sediments, may contain as much biomass as all surface ocean life combined. An entire invisible world exists beneath the ocean floor, barely metabolizing, possibly millions of years old. Let's sit with this concept for a moment. Beneath the ocean floor, in sediments and rock extending kilometers down, there exists a microbial ecosystem that might contain as much living matter as the entire ocean above it. All the fish, all the whales, all the plankton, all the coral, all of that might be matched or even exceeded by the biomass of bacteria and archaea living in the seafloor itself. This deep biosphere is nothing like surface life. The organisms live slowly, so slowly that terms like growth and reproduction barely apply. They might divide once every 1,000 years. They consume energy at rates so low they're at the thermodynamic limit of what's possible for life. They exist in what scientists call an energy-starved state, barely above dormancy, yet still alive, still metabolically active. Some of these microbes might be millions of years old, not the species, the individual cells. There's speculation that cells buried in sediments millions of years ago might still be alive today, having divided perhaps only a handful of times in all those eons. They would be the oldest living organisms on Earth, older than any tree, older than any animal, individual cells that have existed since before humans evolved. The energy sources for this deep biosphere are geological rather than biological. Radionuclides in the rock decay, releasing energy. Water reacts with minerals in a process called serpentinization, producing hydrogen and methane. Buried organic matter from ancient oceans slowly decomposes. These are trickles of energy, barely enough to sustain life, but enough. The volume of the deep biosphere is enormous. The sediments and porous rock beneath the ocean floor represent a habitat far larger than the ocean itself. If even a small fraction of that volume is inhabited, and evidence suggests much of it is, wherever there's liquid water in the pore spaces, then the total biomass is staggering. This raises profound questions. Is the deep biosphere the true dominant form of life on Earth, with surface life being just a thin, fast-living energetic layer on top of a massive, slow, ancient subsurface biosphere? Did life originate in the subsurface and only later colonize the surface? Could similar subsurface biospheres exist on other planets? Is hidden beneath surfaces that appear lifeless? The deep biosphere is a reminder that life doesn't need to be vibrant, fast-growing or energetic to be successful. It can be slow, patient, minimal, existing at the very edge of what's thermodynamically possible, in darkness, in isolation, for timescales that make civilization seem like brief flickers. And there might be more of it, by mass, than all the life we can see. Some deep-sea bacteria reproduce only once every 1,000 years, existing in a state so slow it barely qualifies as life. They challenge our very definition of what it means to be alive. What is life? It's a question philosophers and biologists have wrestled with for centuries. The usual answers involve metabolism, growth, reproduction, response to stimuli, homeostasis. Life is dynamic. Life is active. Life consumes resources and produces waste. Life changes, but deep-sea bacteria, particularly those in subsurface sediments, challenge these definitions. They metabolize, yes, but so slowly that their energy consumption is nearly undetectable. They grow, technically, but at rates measured in nanometers per year. They reproduce, but perhaps only once every 1,000 years or longer. They respond to stimuli, but so slowly that the response might take decades. Are they alive? By most definitions, yes. They maintain cellular integrity. They perform biochemical reactions. They can, under the right conditions, increase in number. But they exist in a state so removed from what we normally think of as life that it seems like a different phenomenon entirely. Imagine a bacterium that divided once when the Roman Empire fell and won't divide again until the next millennium. In the intervening centuries, it does almost nothing. It sits in a pore space in sediment at the bottom of the ocean, slowly repairing cellular damage as it accumulates, maintaining its membranes against slow degradation, performing the absolute minimum biochemistry necessary to remain viable. It's not dormant. Dormant implies the potential to wake up and become active. This bacterium is active. This is as active as it gets. Some scientists have proposed new terminology for this state: maintenance metabolism or survival metabolism. The organism isn't growing or reproducing, it's simply maintaining itself, preserving its integrity against the slow forces of chemistry and entropy that would otherwise degrade it into non-life. This has implications for how we search for life elsewhere. If we're looking for metabolic signatures, chemical signs of active life, these ultra-slow organisms might be undetectable. Their metabolism is so minimal, it could be mistaken for abiotic chemical reactions. We might be standing on a planet teeming with life in maintenance mode and not recognize it. It also raises philosophical questions. If an organism reproduces once every 1,000 years, is it really alive in any meaningful sense? Or is it in a state between life and non-life, a kind of biological stasis where the machinery of life is present but operating so slowly it's almost frozen? These bacteria don't answer our questions about life. They complicate them. They blur the boundaries. They exist in a grey zone between the clearly alive and the clearly not alive, challenging us to reconsider what life requires, what life can be, and how we recognise it when we find it. Deep-sea mining is being explored to extract rare earth metals from the ocean floor, but its impact on ecosystems remains poorly understood. We may destroy habitats we haven't even discovered yet. The deep sea floor contains valuable resources, manganese nodules rich in nickel, copper and cobalt, polymetallic sulfides near hydrothermal vents containing gold, silver and rare earth elements, cobalt-rich ferromanganese crusts on seamounts. These materials are used in batteries, electronics, renewable energy technologies, the infrastructure of modern civilization. And as land-based deposits become harder to access or politically complicated to extract, companies and governments are looking to the ocean. Deep-sea mining, once science fiction, is becoming a real possibility. Several companies have exploration licenses, some have tested prototype mining machines. Commercial extraction could begin within the decade. But here's the problem. We barely know what's down there. Most of the deep sea floor has never been visually surveyed. The ecosystems around manganese nodule fields, around seamounts, even around inactive hydrothermal vents, are poorly studied. We don't know what species live there, how they interact, how they would respond to disturbance. Deep-sea mining isn't like digging a hole on land. It involves dragging machinery across the seafloor, scraping up nodules or crust. You're creating massive sediment plumes that drift with currents and settle over wide areas, potentially smothering organisms kilometers away from the mining site. It might destroy hydrothermal vent communities, remove habitat for endemic species, disrupt food webs we don't understand, and the deep sea recovers slowly. A trawl mark on the abyssal plain can remain visible for decades. A removed nodule field won't regenerate in human timescales. Those nodules took millions of years to form. If we drive a species extinct through mining, it's gone, not depleted, not reduced. Extinct before we even knew it existed. There's a tension here. The metals are valuable. They're needed for green energy transitions, for technologies that could help address climate change. But extracting them might cause irreversible harm to one of the largest ecosystems on Earth, one we barely understand, that plays roles in global nutrient and carbon cycling we're only beginning to appreciate. Some scientists and environmental groups are calling for a moratorium on deep-sea mining until we understand the ecosystems better, until we can assess the risks properly. Others argue that with proper regulation and monitoring, mining can proceed sustainably. The international body regulating deep-sea mining, the International Seabed Authority, is still developing rules and environmental standards. We're at a decision point. Do we mine the deep sea for resources we need, accepting risks we can't fully quantify? Or do we wait, study, protect these ecosystems until we understand what we'd be sacrificing? The deep ocean doesn't have a voice in this decision. It's just there, vast and quiet and full of life we haven't discovered, waiting to see what we decide. Plastic has been found in the deepest ocean trenches, including single-use bags in the Mariana Trench. No place on Earth remains untouched by human activity, not even the most remote abyss. In 2019, a submersible descended to Challenger Deep. the deepest point in the ocean, nearly 11,000 meters down at pressures over 1,000 atmospheres, in a place farther from human civilization than almost anywhere on Earth's surface, the cameras captured something, a plastic bag. A single-use plastic bag, the kind you'd get at a grocery store, sitting on the seafloor of the Mariana Trench. Thousands of kilometers from the nearest city, in a place only a handful of humans have ever visited, in what should be the most pristine, most isolated environment on the planet. But it's not isolated. The ocean connects everything. Plastic enters the ocean from rivers, from beaches, from ships, from illegal dumping. It floats, initially. Surface currents carry it. Some sinks when it becomes fouled with biological growth or breaks into smaller pieces. It drifts down through the water column, through the twilight zone, through the midnight zone, into the abyss, and eventually settles on the sea floor. Even in the deepest trenches, even in places where pressure would crush a car, plastic accumulates. Bags, bottles, fishing gear, microplastics. Amphipods in the Mariana Trench have been found with microplastics in their guts. Deep-sea fish have ingested plastic fibers. Organisms that feed on marine snow are consuming plastic particles mixed with organic debris. We like to think of the deep ocean as separate from human influence, as a wild place untouched by civilization. But there's no such place anymore. Our plastics have reached the furthest depths. Our chemical pollutants are in the tissues of animals that never come near the surface. Our noise fills the acoustic environment. Our fishing gear litters seamounts and ridges. The plastic in the Mariana Trench is symbolic. It's proof that a way doesn't exist. When we throw something away, when we let plastic enter the ocean, it doesn't disappear. It goes somewhere, and that somewhere, eventually, is everywhere, including the most remote, most extreme, most alien-like place on our planet. The deep ocean is not separate from the surface world. It's connected by falling debris, by currents, by the simple fact that the ocean is one continuous body of water. What we do at the surface reaches the abyss, eventually, and the plastic bag in the Mariana Trench is a quiet reminder that our influence has no boundaries, no limits. We've marked even the deepest places with our waste. Deep-sea creatures that feed on surface-derived nutrients are now ingesting microplastics that rain down with marine snow. Pollution links the shallowest and deepest parts of the ocean in ways we're only beginning to understand. Marine snow, that constant rain of organic debris we've talked about, doesn't just contain dead plankton and fecal pellets anymore. It contains plastic. Tiny fragments of degraded plastic, microfibers from synthetic clothing washed into rivers, microbeads from cosmetics, and particles from larger plastic items that have broken down. These microplastics are similar in size to organic particles, and they're incorporated into marine snow aggregates, falling through the water column just like natural organic matter. Deep-sea filter feeders don't distinguish between organic particles and plastic particles. They can't. They filter indiscriminately, taking in whatever drifts past. So they ingest plastic. It accumulates in their guts. Sometimes it passes through. Sometimes it blocks digestive tracts. Sometimes it leaches chemicals, plasticizers, additives, absorbed pollutants into the organism's tissues. Studies of deep-sea amphipods, fish, and other organisms have found microplastics in alarming percentages. Sometimes 50% or more of individuals examined contain plastic. These are animals living thousands of meters deep, in trenches, in abyssal plains, in places about as remote from human activity as you can get, and they're full of plastic. The long-term effects are unknown. Microplastic ingestion might reduce feeding efficiency if it fills the gut without providing nutrition. It might cause physical damage to digestive tissues. The chemicals leaching from plastic might have endocrine-disrupting effects, interfering with reproduction or development. Or the effects might be subtle, sublethal, accumulating over generations in ways we can't yet detect. And plastic in the deep sea is effectively permanent. At surface levels, UV light from the sun can degrade plastic over time, though it just breaks it into smaller pieces rather than eliminating it. But in the deep sea, there's no UV light. Again, plastic that reaches the abyss will remain essentially unchanged for centuries, potentially millennia. It's a persistent pollutant in an environment where persistence is already the norm. The connection between surface pollution and deep-sea ecosystems is direct and immediate. Within weeks or months of plastic entering the ocean at the surface, it can begin its journey down. Within years, it can reach the deepest trenches. The ocean's vertical mixing, the biological pump that transports organic matter from surface to depth, it transports plastic too. We're conducting an unintended experiment. We're adding a novel material to the ocean faster than evolution can adapt to it, and we're seeing it appear in organisms throughout the water column, from surface to abyss. The full consequences won't be clear for decades. By then, the plastic will be entrenched, distributed, impossible to remove. The deep ocean, once pristine, is becoming a repository for our waste. The deep ocean absorbs sound from human activities, ship engines, sonar, seismic testing, creating noise pollution that affects marine life. What we think of as silent depths are becoming increasingly loud with human presence. We've talked about the deep ocean as a place of sound, whale songs, snapping shrimp, the groans of ice and earth. But increasingly, it's also a place of human-generated sound. And that sound travels far. Ship traffic creates a constant background noise. The low-frequency rumble of ship engines propagates for kilometers, even hundreds of kilometers under the right conditions. The ocean is crisscrossed by shipping lanes, and in those lanes, the sound level is dramatically higher than natural background. Military sonar, used for submarine detection and other purposes, creates intense pulses of sound. These pulses can be loud enough to damage hearing in marine mammals, cause stress responses in fish, potentially even harm invertebrates. There are documented cases of whale strandings coinciding with naval exercises, suggesting the sonar might disorient them or damage their acoustic navigation abilities. Seismic testing for oil and gas exploration uses air guns that create explosive sounds to map the seafloor structure. These guns fire repeatedly, creating a constant pattern of loud blasts that can continue for weeks or months during a survey. The sound reaches deep into the ocean, affecting organisms that rely on sound for communication, navigation, or hunting. For animals that use sound the way we use vision, like whales, dolphins, and many fish, this noise pollution is like living in permanent fog. It masks communication signals, making it harder to find mates or coordinate with group members. It interferes with echolocation, making hunting more difficult. It creates stress, potentially affecting health and reproduction. And it's getting worse. Global shipping traffic increases each year. Seismic exploration expands into new areas. Military exercises continue. Offshore construction, wind farms, platforms, adds new sources of noise. The ocean is getting louder, particularly at the low frequencies that travel farthest. There's no quiet refuge. Sound in the ocean travels so well that even the deepest trenches are affected by surface noise. A ship passing overhead can be heard at the bottom of the Mariana Trench. The acoustic environment of the deep ocean, which for millions of years was shaped only by natural sounds, is now dominated in many areas by human noise. Some scientists are calling for quieter ship designs, for regulations on seismic testing and sonar use, for marine protected areas where anthropogenic noise is minimized. But enforcement is difficult. The ocean is international, ships cross jurisdictions, and noise pollution is invisible, easy to ignore. The silent deep isn't silent anymore. It hums and rumbles and clicks with the sounds of human activity, a constant reminder that even in the most remote depths, our presence is felt or heard. Some deep-sea organisms have evolved to eat wood from sunken ships and trees washed out to sea. These wood-boring specialists can break down cellulose that most marine life cannot digest. Wood seems out of place at the bottom of the ocean. It floats, after all, unless it becomes waterlogged or heavy enough to sink. But wood does reach the deep sea floor. Trees wash out to sea during storms, carried by flooding rivers. Wooden ships sink. Driftwood, logs, entire tree trunks sometimes descend through the water column and come to rest on the abyssal plain or in deep trenches. And when they do, specialists arrive. Wood-boring bivalves, shipworms, though they're not actually worms, drill into the wood, excavating tunnels and chambers. They have specialized bacteria in their gills that help them digest cellulose, breaking down wood fibers into usable nutrients. It's a partnership similar to what we see at hydrothermal vents or whale falls. Animals providing bacteria with access to a resource, bacteria converting that resource into food the animal can use. These wood falls, as scientists call them, support their own distinct communities. Different species colonize wood than colonize whale bones or whale flesh. Some are specialists found only on sunken wood. Others are generalists that also inhabit vents or seeps. Over time, a progression of species colonizes the wood. First, the opportunistic borers, then specialists that live in the boreholes, then predators and scavengers that feed on the borers. A large log can sustain a community for decades. The wood borers slowly consume it from the inside, creating a honeycomb of tunnels. Bacteria decompose the wood fibers chemically. The structure slowly weakens, eventually collapsing into scattered fragments. By the end, little remains but sawdust and shells. The discovery of woodfall communities helped scientists understand how vent and seep organisms might disperse. Vents are ephemeral. They shut off, migrate, open in new locations. How do vent species find new vents when they're scattered across vast distances? One hypothesis is that they use intermediate habitats, whale falls, wood falls, any chemosynthetic environment, as stepping stones. A vent species might colonize a nearby woodfall, and from there, larvae disperse to find another vent or another woodfall, creating a network of connected populations across the deep ocean. Sunken wood is proof that organic material from land can support deep-sea ecosystems. The connection between terrestrial and marine environments extends even to the abyss. A tree that grew in a forest, nourished by sunlight and rain, can end up feeding wood-boring clams in the Hadal zone, its cellulose converted to energy by bacteria that never see light. The carbon cycle is global, connecting land and sea, surface and deep, in pathways we're still tracing. Chemosynthetic ecosystems have been found in underwater caves, in whale bones, and even in sunken wood, anywhere chemicals and bacteria can meet. Life finds a way to extract energy from the most unlikely sources. The discovery of chemosynthesis at hydrothermal vents in 1977 was revolutionary. But it was just the beginning. Once scientists knew what to look for, they started finding chemosynthetic ecosystems in unexpected places. It wasn't just hot volcanic vents. Chemosynthesis could happen anywhere the right chemicals met the right bacteria. Cold seeps, where methane and hydrogen sulfide leak from sediments, chemosynthetic bacteria and their symbiotic partners. Whale falls, where decomposing bones release sulfide, chemosynthetic bacteria, and tube worms and mussels farming them. Sunken wood, where bacteria in the wood produce hydrogen that other bacteria can use, chemosynthetic communities. Underwater caves where groundwater rich in hydrogen sulfide meets oxygenated seawater, bacterial mats performing chemosynthesis, even sewage outfalls, even sunken plant matter, even oil seeps. Anywhere there's a chemical gradient, a place where reduced compounds meet oxidized compounds, bacteria can exploit it, and where bacteria thrive, animals follow, and either feeding on the bacteria directly or hosting them symbiotically. The common thread is disequilibrium. Chemosynthesis requires chemicals that aren't in equilibrium with their environment. Hydrogen sulfide in the presence of oxygen, methane in the presence of sulfate, hydrogen in the presence of nitrate. These combinations represent stored energy. The chemicals want to react. They're thermodynamically favourable to react. Bacteria harness that reaction, capturing the energy as it's released, using it to build biomass. This means chemosynthetic ecosystems can exist almost anywhere in the ocean, as long as the right chemical conditions are present. They're not limited to vents or seeps. They're opportunistic, popping up wherever the chemistry is right, persisting as long as the chemicals flow, dispersing when the resource is exhausted. The diversity of chemosynthetic habitats suggests that early in Earth's history, before photosynthesis evolved, chemosynthesis might have been widespread. Anywhere volcanic or hydrothermal activity produced chemical gradients, life could have thrived. The early ocean might have been dotted with chemosynthetic oases, precursors to the vent and seep communities we see today. And it suggests that on other worlds without sunlight or with sunlight too dim to support photosynthesis, chemosynthetic ecosystems might be the norm. Life doesn't require light, it requires chemical energy. And chemical energy is available wherever geological or geochemical processes create disequilibrium. Chemosynthesis is a universal strategy, limited not by planetary conditions but only by the availability of chemicals and liquid water. Life finds a way. It's a cliché, but the proliferation of chemosynthetic ecosystems proves it. Given chemistry and time, life will figure out how to extract energy, how to build communities, how to persist in places that seem, by our surface-dwelling standards, utterly inhospitable. The discovery of hydrothermal vent life led scientists to reconsider where life might exist elsewhere in the solar system. If life can thrive without sunlight in Earth's ocean, perhaps it exists in the ice-covered oceans of Europa or Enceladus. Before 1977, when scientists imagined where life might exist in the solar system, they focused on planets with certain characteristics: liquid water, sunlight for photosynthesis, moderate temperatures. Mars, early in its history, might have had these. Venus, before its runaway greenhouse, maybe some moons with atmospheres. The discovery of hydrothermal vent ecosystem changed this calculus completely. Here was life thriving in complete darkness, independent of the sun, powered entirely by chemical energy from geological processes. If life could do this on Earth, Why couldn't it do this elsewhere? Europa, Jupiter's ice-covered moon, suddenly became a prime candidate. Beneath its icy shell lies an ocean, kept liquid by tidal heating as Europa flexes in Jupiter's gravitational field. That ocean is in contact with a rocky seafloor. Tidal heating might drive hydrothermal activity. If so, Europa's ocean could have vents, and if it has vents, it might have life. Enceladus, a small moon of Saturn, became even more interesting when the Cassini spacecraft discovered plumes of water erupting from cracks in its ice. The plumes contain organic molecules, salts, even molecular hydrogen, exactly what you'd expect from hydrothermal activity. Enceladus has an ocean, and that ocean might have chemistry suitable for chemosynthetic life. Even Titan, Saturn's largest moon, became a candidate, though a more exotic one. Titan has liquid on its surface, but it's liquid methane, not water. Could life use methane the way Earth life uses water? Could chemosynthetic processes work in liquid methane? It seems unlikely, but before we discovered vent ecosystems, we would have said life couldn't exist without sunlight either. The requirements for life, post-1977, became simpler. Liquid water, chemical energy, and time. Sunlight is optional. Surface environments are optional. You don't even need a stable surface temperature. Life can exist wherever water is liquid, whether that's near freezing or near boiling. Yeah, this expanded the habitable zone in the solar system dramatically. Instead of a narrow band around the sun where planets might have liquid water on their surfaces, we now consider anywhere with subsurface water potentially habitable. Moons of gas giants heated by tidal forces, dwarf planets in the outer solar system with subsurface oceans, even exoplanets far from their stars might harbour life in underground oceans. The search for life became less about finding another Earth and more about finding another hydrothermal vent. And the deep ocean, our own deep ocean, here on Earth, became not just a habitat to study, but a template for understanding what life might look like elsewhere in the universe. Some deep-sea fish have antifreeze proteins in their blood, preventing ice crystals from forming in near-freezing water. These molecular shields allow life to persist at temperatures that would kill most organisms. The deep ocean is cold. We've said this before, but it's worth emphasizing. In most of the deep ocean, temperature hovers around 2 to 4 degrees Celsius. In polar regions, it can drop below 0 degrees Celsius, yes, below the freezing point of pure water, and yet remain liquid because salt depresses the freezing point. For organisms living at these temperatures, there's a risk: ice formation. If ice crystals form inside cells, they puncture membranes, disrupt structures, kill the cell. Most organisms avoid this by staying in water that's above their body's freezing point. But some deep-sea fish in polar regions live in water that's cold enough to freeze them. Their solution is antifreeze. Not the chemical kind you put in a car, biological antifreeze. Proteins or glycoproteins that bind to tiny ice crystals as they begin to form and prevent them from growing. The proteins don't prevent water from freezing entirely, but they lower the freezing point of the fish's blood and tissues enough that the fish can survive in water at minus 1.9 degrees Celsius or colder. These antifreeze proteins are marvels of molecular engineering. They have structures that match the lattice structure of ice crystals. When a tiny crystal begins to form, the protein attaches to it, blocking the addition of more water molecules. The crystal can't grow. It remains too small to damage cells. The fish's blood remains liquid even though thermodynamically it should freeze. Different species evolved different antifreeze proteins independently. Arctic cod have one type, Antarctic fish have a different type. Either some invertebrates have glycoproteins. Evolution arrived at the same solution, molecular antifreeze, as multiple times, using different protein structures to achieve the same effect. It's a reminder that evolution is constrained by physics and chemistry, but endlessly creative within those constraints. The problem, surviving in water cold enough to freeze you, has a solution, and life found it. Multiple times, in different lineages, using different molecular strategies, but all achieving the same result: preventing ice from destroying cells. For humans, this is more than academic curiosity. Scientists are studying biological antifreeze proteins for potential applications, preserving transplant organs, improving frozen food quality, preventing ice formation in industrial processes. Nature solved the problem millions of years ago. We're just trying to learn from the solutions already out there, written in protein sequences, allowing fish to swim in water that should, by all rights, turn them into frozen statues. The deep ocean is one of the most thermally stable environments on Earth, with temperatures changing less than 1 degree Celsius over thousands of years. This stability has allowed deep-sea species to become highly specialized, unable to adapt to rapid change. Stability is a double-edged sword. In stable environments, organisms can specialize. They can evolve precise adaptations to exact conditions because those conditions don't change. There's no need for flexibility, no advantage to tolerating a wide range of temperatures or pressures or salinities. Specialization is rewarded. The deep ocean is extraordinarily stable. Yes, temperature varies by less than a degree across vast areas. Salinity is nearly constant. Pressure obviously is constant at any given depth. The environment has been essentially unchanged for thousands, even millions of years. No seasons, no day-night cycles, no weather. Deep-sea organisms evolved in this stability and became exquisitely specialized. Their enzymes work efficiently at 2 degrees Celsius, but denature at 10 degrees Celsius. Their membranes are structured for high pressure and lose integrity at lower pressure. Their metabolisms are tuned to specific chemical conditions and can't adjust to changes. This specialization makes them vulnerable. Climate change is altering the deep ocean slowly but measurably. Bottom water is warming, just fractions of a degree. But that's enormous for an environment that normally varies by fractions of a degree per millennium. Oxygen levels are changing as circulation patterns shift. Chemistry is changing as the ocean absorbs more CO2. For organisms adapted to absolute stability, even small changes can be catastrophic. A fish that evolved to function at 2 degrees Celsius might not survive at 3 degrees Celsius. It doesn't have the genetic flexibility to adapt quickly because its ancestors never needed that flexibility. Rapid change in the deep ocean, rapid by geological standards though slow by surface standards, could cause extinctions of species that can't adapt fast enough. And deep-sea species reproduce slowly, live long lives, have small populations. All of these traits make evolutionary adaptation slower. A surface fish species with short generation times and large populations can evolve in response to environmental change relatively quickly. A deep-sea fish that lives 100 years and reproduces only a few times can't. Stability created the diversity and uniqueness of deep-sea life, but that same stability makes deep-sea life fragile in the face of change. The deep ocean is shifting, warming, changing chemistry, and the organisms there, specialized over millions of years to exact unchanging conditions, are facing an environmental transformation they may not be equipped to handle. Deep-sea exploration vessels use syntactic foam, hollow glass spheres embedded in resin, to provide buoyancy without being crushed by pressure. It's one of the few materials that can withstand the extreme forces of the Hadal zone. When designing a vessel to reach the deepest ocean is an engineering challenge unlike any other. The pressure at 11,000 meters is over 1,000 times atmospheric pressure, about 16,000 pounds per square inch. That's enough to crush almost any structure, compress almost any material. You need buoyancy to rise back to the surface, but gas-filled floats would be crushed. Ordinary foam would compress into uselessness. Metal floats would work, but would be so heavy they'd negate their own buoyancy. What do you use? Syntactic foam. It's a composite material made of tiny hollow glass spheres, microspheres, embedded in a resin matrix. Each sphere is incredibly small, often less than a millimeter in diameter, with walls thin enough to keep weight down but thick enough to resist pressure. The resin holds them in place, distributes stress, prevents individual spheres from bearing too much load. When pressure increases, the resin compresses slightly, but the hollow spheres resist. Some might crack or implode, but the majority survive. The material as a whole maintains its volume and buoyancy even at extreme depth. It's lighter than water, providing lift, and strong enough to withstand Hadal zone pressures. Syntactic foam is used in deep-sea submersibles, in autonomous vehicles, in scientific instruments that need to be recovered from depth. It's shaped into floats, into fairings, into structural components. It's essential technology for deep-sea exploration. But it's also a reminder of how hostile the deep ocean is. We can't just use ordinary materials. We need engineered solutions, carefully designed composites, materials that push the limits of what's physically possible. Even then, failures happen. Spheres crack. Foam compresses more than expected. Equipment implodes. The deep ocean doesn't yield easily. It's a harsh environment, unforgiving of design flaws or material weaknesses. Every descent to Hadal depths is a test, not just of the science we're doing, but of the engineering that makes it possible. Syntactic foam, with its millions of tiny glass spheres, is part of what allows humans to visit the abyss. Without it, much of the deep ocean would remain not just unexplored, but unexplorable. The deepest diving submersible, DSV limiting factor, is made from titanium and can carry humans to any depth in the ocean. It has completed dives to all 5 of the ocean's deepest points, a feat called the 5 Deeps Expedition. For decades after the Trieste's descent to Challenger Deep in 1960, then only unmanned vehicles reached the deepest ocean. The technology for repeated, safe, crewed dives to Hadal depths didn't exist, but in the 2000s that changed. The DSV limiting factor is a 2-person submersible designed and built specifically to reach full ocean depth, anywhere in the ocean, repeatedly. Its pressure hull is made from titanium, shaped into a sphere to evenly distribute pressure. The viewports are thick conical sapphire, strong enough to withstand the crushing force without compromise in visibility. Between 2018 and 2019, the limiting factor completed the 5 Deeps expedition, dives to the deepest point in each of the 5 oceans: the Atlantic, the Southern Ocean, the Indian Ocean, the Pacific, Challenger Deep, and the Arctic. Each dive reached the deepest point in that ocean. It was an unprecedented achievement, proof that Hadal depths are now accessible, not just once in a lifetime, but routinely. The pilot, Victor Vescovo, has made dozens of dives below 10,000 meters. He's seen the deepest places on Earth multiple times, brought back samples, filmed species never before recorded, documented geological features hidden at the bottom of trenches. The limiting factor has found trash, plastic bags, candy wrappers at the bottom of the Mariana Trench. It's discovered new species. It's captured footage of hadal fish and amphipods in their natural habitat. This accessibility changes how we study the deep ocean. We're no longer limited to rare one-off expeditions. We can return to locations, take repeated samples, observe changes over time. The Hadal Zone is still extreme, still dangerous, still one of the least explored environments on Earth, but it's no longer unreachable. The limiting factor represents a technological milestone. Humans can now, in theory, visit any point on the ocean floor. The deepest trenches, once visited only twice in 60 years, can be explored regularly. It's the beginning of a new era in deep-sea exploration, not just sending robots and cameras, but going ourselves, seeing with our own eyes the places that were, for almost all of human history, completely beyond reach. Remotely operated vehicles, ROVs, have allowed scientists to explore depth far beyond human diving limits. These robots have become our eyes in the abyss, revealing creatures and landscapes never before seen. Not every dive requires humans. In fact, most deep-sea exploration is done by robots, remotely operated vehicles controlled from ships at the surface, or autonomous underwater vehicles programmed to carry out missions independently. ROVs are tethered to the ship by a cable that provides power and communication. They can stay submerged for hours or days, far longer than crewed submersibles. They carry cameras, lights, sampling tools, mechanical arms that can collect rocks, capture organisms, deploy instruments. An operator on the ship's surface watches video feeds and controls the vehicle in real time, navigating across the seafloor, investigating features, documenting life. These vehicles have made discoveries that changed our understanding of the ocean. The first footage of giant squid in the deep was captured by an ROV. The diversity of hydrothermal vent communities was documented largely by ROVs, underwater caves, seamounts, trenches. Most of what we know comes from ROV surveys. They can go places humans can't, into narrow crevices, under overhangs, close to active vent chimneys where the water is hot enough to melt metal. They can work in complete darkness, in crushing pressure, in environments where a leak or malfunction means loss of the vehicle, but not loss of life. AUVs, autonomous underwater vehicles, are even more independent. They're programmed with a mission, released from a ship, and operate on their own. They map the seafloor using sonar, photograph transects, measure water chemistry, all without human control. When their mission is complete or their batteries run low, they surface and signal for retrieval. These robots are force multipliers. A single research vessel with ROVs or AUVs can explore more seafloor in a week than decades of crewed submersible dives. They're cheaper to operate, safer, and increasingly sophisticated, but there's something lost too. Watching ROV footage is not the same as being there. The sense of scale, the immersion, the visceral understanding of the environment. These come from human presence. ROVs are tools, extensions of our senses, but they filter the experience through screens and controls. Still, they've opened the deep ocean in ways that wouldn't have been possible otherwise. Every major deep-sea discovery in the last few decades involved ROVs. They are, in a very real sense, our eyes in the abyss. seeing on our behalf, revealing a world that remains, for most humans, forever inaccessible. Some deep-sea creatures brought to the surface explode or dissolve due to the rapid pressure change. Studying them requires specialized equipment that maintains deep-sea pressure even as specimens are raised. Bringing deep-sea organisms to the surface is harder than it sounds. The pressure change is enormous, from hundreds or thousands of atmospheres to 1 atmosphere in a matter of minutes or hours. For organisms adapted to high pressure, this is catastrophic. Fish with gas-filled swim bladders experience the worst of it. The gas expands as pressure drops. If the fish ascends slowly, it can release gas through specialized valves. But when caught in a net and hauled rapidly to the surface, there's no time. The swim bladder expands, rupturing the body cavity, sometimes forcing the stomach out through the mouth. The fish arrives at the surface dead, distorted, damaged. Even organisms without gas spaces suffer. Proteins and enzymes structured to work under high pressure can denature at low pressure. Cell membranes change their properties. Metabolic processes fail. Many deep-sea creatures die simply from the pressure release, even if they're not physically damaged, and some dissolve. Gelatinous organisms, jellyfish, salps, certain fish, lose their structural integrity. They're held together partly by internal pressure equilibrating with external pressure. At the surface, they collapse into formless blobs, their delicate structures destroyed. Scientists studying deep-sea life have developed specialized equipment to avoid this. Pressure-retaining samplers are containers that seal at depth, as maintaining internal pressure as they're brought to the surface. The organism inside experiences no pressure change. It can be studied alive in controlled conditions at surface pressure if needed, but gradually allowing time to acclimate. These samplers are technically challenging. They need to seal perfectly under high pressure, withstand the stress of ascent, remain sealed through deployment on deck. Any leak, and the internal pressure drops, killing the specimen. Other approaches include in situ studies, bringing instruments to the deep ocean rather than bringing organisms to the surface. Cameras, respirometers, experimental chambers deployed at depth allow scientists to study organisms in their natural pressure environment without disturbing them. It's a reminder that the deep sea is not just far away, it's fundamentally different in ways that make it difficult to study. We can't simply collect samples and examine them in a lab. The act of collecting changes or destroys them. We need to either study them where they are or develop technology to bring them up intact, pressure and all. The deep ocean remains largely unexplored because it's expensive, dangerous, and technologically challenging to access. A single deep-sea expedition can cost millions of dollars for just a few hours on the ocean floor. Why haven't we explored the deep ocean more thoroughly? The answer is simple. It's hard, and it's expensive. A research vessel capable of deep-sea work costs tens of thousands of dollars per day to operate. Crew, fuel, equipment, insurance, it adds up quickly. An ROV or crewed submersible adds more cost. Specialized instruments, sampling equipment, data processing, more cost. A single expedition might spend weeks at sea and cost several $1 million. And what do you get for that investment? A few dives, a few sites examined. Maybe a few square kilometers of seafloor mapped in detail. It's nothing compared to the scale of the ocean. There are roughly 360 million square kilometers of ocean floor. We've visually surveyed less than 0.05% of it. Compare this to space exploration. A Mars rover costs billions but operates for years, exploring a different planet, capturing public imagination. Deep sea exploration is comparably expensive but gets less funding, less attention, less public support. It's harder to get people excited about robots exploring our own ocean than robots exploring another planet. The technical challenges are enormous. Pressure hulls must be perfectly manufactured. Any flaw could cause implosion. Electronics must be pressure resistant or housed in sealed containers. Batteries must provide enough power for hours or days of operation. Communication through water is difficult. Radio doesn't work, so tethered vehicles use cables, while autonomous vehicles operate blind, collecting data to be downloaded later. Navigation is challenging. GPS doesn't work underwater. Sonar provides positioning but is less precise than satellite navigation. Currents push vehicles off course. Visibility is limited. Even with lights, you can see only a few meters in the clearest water, less in areas with sediment or biological material. And it's dangerous. Equipment fails, tethers break, vehicles are lost. Crewed submersibles face the risk of catastrophic failure, implosion, entanglement, loss of power. It's safer than it used to be, but risk remains. For all these reasons, cost, difficulty, danger, lack of public interest, the deep ocean remains one of the least explored frontiers on Earth. We've sent 12 people to the moon, hundreds have been to space, but only a handful have reached the deepest ocean, and we've visually surveyed less area of seafloor than we've mapped on Mars. The deep ocean is close, right here on our planet, and yet it remains profoundly distant, separated from us not by the vacuum of space, but by thousands of meters of water and the enormous pressure that comes with it. Just strange sounds recorded in the deep ocean, like the bloop detected in 1997, often turn out to be natural phenomena like ice quakes. The deep ocean is full of mysterious sounds we're still learning to identify and understand. In 1997, underwater microphones deployed by the National Oceanic and Atmospheric Administration detected something unusual, an extremely loud, ultra-low frequency sound that rose rapidly in frequency over about 1 minute. It was loud enough to be detected by sensors over 5,000 kilometers apart. Researchers called it the bloop. For years it was a mystery. The frequency profile resembled sounds made by marine animals, but it was far louder than any known biological source. Could it be an unknown species? A massive creature living in the deep ocean, larger than any whale? The internet, predictably, ran with this idea. The bloop became evidence of sea monsters, of undiscovered megafauna, of creatures from mythology made real. The actual explanation, determined years later, was less dramatic but no less interesting. Ice. Specifically, ice quakes. The sound of large icebergs calving from Antarctic ice shelves and cracking as they break apart. The sound profile matched. The location matched. Sensors detected the bloop coming from the vicinity of Antarctica. And the volume made sense. Massive ice structures fracturing would produce incredibly loud sounds that could travel across ocean basins. The bloop is just one of many mysterious sounds recorded in the deep ocean. There's the train, a long, regular pattern of pulses. The whistle, a rising tone that sounds almost artificial. The upsweep, a seasonal sound that appears each spring in the Pacific and has been recorded for decades, still not definitively explained, though it's likely related to underwater volcanic activity or ice. Some sounds remain unidentified. We hear things we can't explain, patterns we can't attribute to any known source. The ocean is acoustically complex. Ice cracks and groans. Underwater landslides create rumbles. Earthquakes generate low-frequency waves. Volcanic activity produces hums and pulses. Marine mammals sing, click, whistle. Invertebrates create noise. Even the movement of water itself, currents flowing past obstacles, eddies forming and dissipating, creates sound. Listening to the deep ocean is like listening to a language you don't fully understand. You can pick out familiar words, whale songs, shrimp snaps, but much of it is mysterious, context-dependent, requiring interpretation. And occasionally you hear something that doesn't fit any known pattern, something that makes you wonder what else might be down there, making sounds we haven't learned to recognize yet. The deep ocean isn't silent. It's full of sound, much of it strange, some of it still unexplained, all of it a reminder that we're still learning to listen to a world that existed in acoustic richness long before humans developed the technology to eavesdrop on it. Deep-sea gigantism is a phenomenon where some species grow much larger than their shallow water relatives. Giant isopods, for example, can reach 50 centimeters long, about 100 times larger than a common pillbug. There's something unsettling about deep-sea gigantism, the tendency for some deep-sea organisms to grow far larger than their shallow water or terrestrial relatives. It's not universal, but it's common enough to be noticeable, and it produces creatures that seem almost mythological in their proportions. Giant isopods are perhaps the most famous example. On land, isopods are pillbugs or roly-polies, small crustaceans you find under rocks, maybe a centimetre long. In the deep sea, their relatives can reach 50 centimetres, half a metre, larger than a football. They're scavengers, crawling across the seafloor looking for carrion, eating slowly, living for years between meals. Giant squid and colossal squid dwarf their shallow water relatives. Giant tube worms near hydrothermal vents grow far larger than shallow water tube worms. Spider crabs in the deep can have leg spans exceeding 3 meters. Amphipods in Hadal trenches can reach sizes 10 or 20 times larger than surface amphipods. Why? The explanations are still debated. One hypothesis is related to temperature. Cold water slows metabolism, which can lead to longer lifespans and continued growth over those longer lifespans. Many deep-sea giants are cold water species, and cold temperatures might allow them to grow for decades or centuries. Another hypothesis involves food scarcity and the advantage of large body size in an environment where meals are rare. A larger body can store more energy reserves, allowing an animal to survive longer between feeding opportunities. It can also consume larger food items when they're available. A giant isopod can tackle a larger carcass than a small one. And pressure might play a role too. At high pressure, certain metabolic processes might favour larger body size, or perhaps the lack of predators in some deep-sea environments removes a constraint that limits size in shallower water. Or it might be life history. Deep-sea species often grow slowly and live long lives. If an organism keeps growing throughout its life, even slow growth over centuries could produce a giant. Whatever the cause, the result is creatures that look like they belong in science fiction. The first time you see footage of a giant isopod, eyes glittering in the submersible lights, legs moving slowly across the sediment, body the size of a small dog, it's hard to believe it's a relative of the tiny pillbug in your garden. But it is. Just adapted to a different environment, a different set of pressures, a different scale. But deep-sea gigantism is a reminder that size is relative, that the constraints shaping organisms in one environment don't apply in another. And in the deep ocean, where food is scarce but time is abundant, where pressure is crushing but predators are few, some creatures have grown to proportions that dwarf anything in the shallow seas above. The giant oarfish, which can grow over 11 meters long, lives in the deep mesopelagic zone and is rarely seen alive. When they wash ashore, their serpentine appearance may have inspired ancient sea monster legends. The oarfish is a creature of legend-made flesh. It's the longest bony fish in the ocean. Specimens over 11 meters have been recorded, though most are smaller. It's ribbon-like, compressed laterally, with a bright red dorsal fin running the entire length of its body. It has no scales. There's just silvery, iridescent skin, and it swims through the mesopelagic zone in a serpentine, undulating motion, vertical in the water column, looking for all the world like a sea serpent. For most of history, oarfish were known only from dead specimens that washed ashore, usually after storms, sometimes sick or dying. Their appearance caused a sensation. Enormous snake-like fish with horse-like faces and flowing red manes. In cultures around the world, sightings of oarfish likely contributed to sea serpent myths. Here was a real creature that looked mythological, rarely seen alive, occasionally appearing on beaches like a message from the deep. We still know very little about oarfish behaviour. They live too deep for casual observation, too scattered to encounter frequently. They don't survive in captivity. The few attempts to keep them alive have failed quickly. Our knowledge comes from dead specimens, occasional observations from submersibles, and very rare footage captured by divers or ROVs. They seem to be gentle giants, feeding on small plankton, krill, and jellyfish filtered from the water. They have small mouths with no teeth, incapable of biting or hunting large prey. They drift through the twilight zone, vertical, using their long dorsal fin for propulsion, occasionally encountered by deep-diving tuna or marlin, but mostly existing in solitude. There's a belief in Japanese culture that oarfish washing ashore presage earthquakes or tsunamis, messengers from the sea, God warning of disaster. There's no scientific evidence for this, and though it's possible that changes in ocean conditions before seismic events might affect deep-sea fish, bringing some closer to shore, more likely the association is coincidental, amplified by confirmation bias and the human tendency to find patterns. But the oarfish's connection to mythology is undeniable. For sailors centuries ago, encountering an oarfish at the surface, sick, dying, behaving abnormally, must have been startling. A creature 3 or 4 or 5 meters long, serpentine, undulating, with a crest like a mane. What else would you call it but a sea serpent? The oarfish is proof that sometimes legends have a basis in reality. Not every sea monster was invented from whole cloth. Some were real creatures, misunderstood, exaggerated perhaps, but real. The ocean held serpents. We just didn't recognize them as fish. Some deep-sea creatures are nearly transparent, making them invisible to predators and prey alike. In the dim light of the twilight zone, transparency is an effective form of camouflage. In the mesopelagic zone, where faint blue light still penetrates, being visible is dangerous. Predators scan the water for silhouettes. Any opaque object, any shape that blocks light stands out. But what if you didn't block light? What if light passed through you? Transparency is a common adaptation in the twilight zone. Jellyfish are nearly invisible, their bodies composed mostly of water, their tissue so thin that light passes through with minimal distortion. Certain fish, like juvenile eels and some larval forms, are transparent, their bodies clear, their organs visible through skin that barely scatters light. Musglass squid have transparent bodies with only their eyes and digestive system visible. Some have evolved ways to obscure even these. Their eyes are covered with light-filtering tissue, and their digestive systems are oriented in ways that minimize their silhouette. Salps, barrel-shaped tunicates that drift through the water filtering plankton, are almost perfectly transparent. You can see right through them, the ocean on one side visible through their gelatinous bodies, unchanged on the other side. They're there, occupying space, but visually almost absent. Transparency works because it's camouflage without pigment. In an environment where there's still light, faint light, but enough for visual predators to hunt, being invisible is the ultimate defense. You don't need to hide behind something. You don't need to match a background. You simply disappear, becoming part of the water itself. But transparency has costs. Tissues must be thin, which limits strength. Density must match water, which limits buoyancy control. And you can't have pigmented structures, no dark eyes, no coloured organs, without breaking the illusion. Some transparent creatures have evolved workarounds. Their eyes are on stalks, positioned to minimize the silhouette they create. Their digestive systems are lined with reflective tissue that mirrors the light, making them less visible. Some even have bioluminescent organs on their undersides that match the downwelling light, counter-illuminating themselves, creating light equal to what would have passed through them if they were truly transparent, eliminating their shadow. It's biological invisibility, not perfect, if you know what to look for, where you can see the slight distortions, the faint outlines. But in the dim, diffuse light of the twilight zone, a transparent organism is effectively invisible, drifting through the water unseen, hunting or fleeing without visual cues, existing in a state of near-perfect optical camouflage. The ocean's fossil water that hasn't mixed with surface water in over 1,000 years. This ancient water carries chemical signatures from a different climate era, trapped in the slow-moving abyss. Deep ocean water circulates slowly. We've talked about thermohaline circulation, the ocean conveyor belt that moves water through the ocean basins over centuries or millennia. But some water moves even more slowly, trapped in pockets or basins with minimal mixing, isolated from surface contact for 1,000 years or more. This is fossil water, not literally fossilized, but old enough that it carries chemical signatures from when it was last at the surface. Scientists can date deep water by measuring radioactive isotopes, particularly carbon-14, which decays over time. Water that sank from the surface 1,000 years ago has less carbon-14 than water that sank recently. By measuring the ratio of carbon isotopes, scientists can estimate the age of a water mass, how long since it last exchanged gases with the atmosphere. Some deep water in the North Pacific is over 1,000 years old. It sank in the North Atlantic during the medieval warm period, travelled through the deep Atlantic around Antarctica, into the Indian Ocean, and finally into the Pacific, where it's been circulating slowly ever since. It hasn't seen sunlight since before the Renaissance. And this ancient water carries information. The dissolved oxygen content tells us about surface conditions when the water sank. Warmer surfaces produce water with less dissolved oxygen. The carbon content reflects atmospheric CO2 levels from centuries ago. Trace metals, nutrients, even isotopic ratios of elements. All of these provide clues about past ocean chemistry and climate. And this water is part of the modern ocean. It's not separate or isolated. It mixes, slowly, with younger water. Eventually it will upwell somewhere, return to the surface, exchange gases with the atmosphere, and begin the cycle again. But until then, it's a time capsule, carrying chemical memories of a different era. The existence of fossil water also means that changes we make to the ocean today won't affect the deep ocean immediately. Any carbon we emit now will take decades to centuries to mix into the deep ocean. But once it does, it will stay there for centuries or millennia, slowly circulating, eventually returning to the surface in a future we can barely imagine. The ocean has a memory. Water that sank 1,000 years ago is still down there, carrying information from the past, moving slowly through the abyss, connecting us to climate conditions from an era long before industrial civilization, before global trade, before most of recorded history. Underwater avalanches called turbidity currents can travel hundreds of kilometers, reshaping the deep sea floor. These powerful flows can snap undersea cables and bury entire ecosystems under sediment. The seafloor isn't always stable. In places where sediment accumulates on steep slopes, along continental margins, on the sides of seamounts, at the heads of submarine canyons, the sediment can become unstable. A trigger, an earthquake, a storm, even the gradual accumulation reaching a critical threshold can cause the sediment to fail, to slump, to start moving. When sediment slides underwater, it doesn't just fall, it mixes with water, creating a turbulent, dense flow, a turbidity current. This is an underwater avalanche, a slurry of sediment and water that flows downslope at surprising speeds, sometimes tens of kilometers per hour, carving channels and depositing material across the deep sea floor. These currents can be massive. Some involve millions of cubic meters of sediment. They can travel hundreds of kilometers from their source, flowing down submarine canyons across abyssal plains, depositing layers of sediment that bury everything in their path. And they're powerful. Turbidity currents have snapped undersea telecommunications cables, steel-reinforced cables designed to withstand enormous tensions. In 1929, an earthquake on the Grand Banks triggered turbidity currents that snapped multiple cables in sequence as the flow raced down the continental slope. By timing the cable breaks, scientists reconstructed the speed of the current, over 60 kilometers per hour at its peak. For ecosystems on the seafloor, turbidity currents are catastrophic events. Organisms are buried under meters of sediment. Benthic communities are smothered. Structures built over centuries, coral colonies, sponge gardens, are destroyed in hours. But turbidity currents also create habitat. The sediment they deposit forms new sea floor. Nutrients are transported from shelf environments into the deep ocean. Organic matter buried in the sediment provides food for bacteria and burrowing organisms. Over time, new communities colonize the deposited sediment. Turbidity currents are also important geologically. They transport sediment from shallow water to the deep ocean, building structures called turbidites, layers of graded sediment, coarse at the bottom, fine at the top, each layer representing a single turbidity current event. Geologists study ancient turbidites on land, seafloor that has been uplifted and exposed, to understand past ocean dynamics and sediment transport. The deep ocean is dynamic, not just biologically, but physically. The seafloor shifts, slumps, flows. Sediment moves in avalanches, reshaping landscapes, burying and exposing, destroying and creating. It's a reminder that even in the deep, even in the cold and the dark and the stillness, change happens. Just on different timescales, in different ways than the surface world. The deep ocean produces almost no primary productivity. Nearly all energy comes from above in the form of sinking organic matter. It's a fundamentally dependent ecosystem, relying on the surface world for survival. Primary productivity, the creation of organic matter from inorganic carbon, is the foundation of most ecosystems. On land, plants perform photosynthesis. In the surface ocean, phytoplankton do the same. They capture sunlight, fix carbon dioxide, build biomass. Everything else, herbivores, carnivores, decomposers, depends on this primary production. But in the deep ocean, there's no light. Photosynthesis is impossible. The only primary production comes from chemosynthesis at vents, seeps, and other specialized environments. And while those communities are important, they're tiny compared to the vast expanse of the deep ocean. So where does energy come from? From above. The deep ocean is fundamentally heterotrophic. It consumes organic matter produced elsewhere. Marine snow falls from the surface. Carcasses sink. Fecal pellets drift down. Zooplankton migrate vertically, carrying energy from surface to depth. All of this is energy originally captured by photosynthesis at the surface, now sinking into the dark. The deep ocean is dependent on the surface in a way the surface isn't dependent on the deep. If photosynthesis stopped at the surface, the deep ocean would starve. Food would stop arriving. Communities would collapse. Only the chemosynthetic oases, vents and seeps would persist. And even those depend on geological activity, not biological production. This dependence means that changes at the surface affect the deep. If surface productivity declines due to warming, acidification, nutrient depletion, less organic matter sinks. Deep-sea communities receive less food, populations decline, ecosystems change, and climate change is affecting surface productivity in complex ways. Some regions are becoming more productive due to changes in nutrient availability. Others are becoming less productive as warming strengthens stratification, preventing nutrient-rich deep water from reaching the surface. The net effect on the deep ocean is uncertain, but any significant change in surface productivity will cascade down. The deep ocean is the largest ecosystem on Earth, but it's fundamentally dependent on the smallest, the microscopic phytoplankton at the surface that capture sunlight and fix carbon. Without them, the deep would be a barren wasteland. With them, it's a rich, diverse, complex ecosystem. The connection is absolute. The deep ocean lives on the leftovers from the surface, the scraps that drift down, the endless rain of organic matter that links the bright world above to the dark world below. Deep-sea corals can record ocean chemistry changes in their skeletons, providing climate records spanning centuries. They're living archives of ocean history, growing slowly in the dark and remembering conditions long past. We've talked about sediment cores as climate archives, but there's another source of paleoclimate information in the deep ocean, deep-sea corals. Unlike their shallow water relatives, these corals don't rely on photosynthetic symbionts. They're filter feeders, capturing food from the water, and as they grow, they incorporate chemicals from seawater into their calcium carbonate or protein skeletons. The chemistry of those skeletons reflects the chemistry of the surrounding water when they formed. The ratio of oxygen isotopes tells us about temperature. The ratio of carbon isotopes tells us about ocean circulation and carbon cycling. Trace elements, barium, cadmium, uranium, reflect nutrient levels and productivity. Radioactive isotopes provide absolute dating. Because deep-sea corals grow slowly and live for centuries or millennia, they provide long, continuous climate records. A single coral colony might record 500 years of ocean history in its skeleton, and by analysing the chemistry layer by layer, like reading tree rings, scientists can reconstruct past ocean conditions with annual or even seasonal resolution. These records have revealed changes in ocean circulation during the Little Ice Age, variations in deep water formation during medieval warm periods, shifts in carbon cycling before and after industrialization. They've shown that the deep ocean isn't as stable as we thought, that circulation patterns shift, that water masses change properties, that the deep responds to surface climate on decadal to centennial timescales. Deep-sea corals are living instruments, recording data about their environment continuously and accurately. They don't know they're doing it. They're just growing, incorporating whatever chemicals are available, following biological imperatives. But the result is an archive, encoded in calcium and protein, waiting for scientists to read it, to extract the information, to reconstruct the history of ocean conditions from centuries past. And these archives are vulnerable. Bottom trawling destroys coral colonies that took millennia to grow. Climate change is altering the chemistry they're recording, and potentially affecting their ability to grow at all, as ocean acidification makes it harder to precipitate calcium carbonate. We're simultaneously depending on these corals to tell us about past climate change and threatening their existence through current climate change. The deep-sea corals grow slowly, remember faithfully, and offer us a window into the past. They're witnesses to ocean history, recording changes we weren't around to observe, and preserving information in their skeletons that we're only now learning to decode. The deepest known volcanic vents are over 5,000 meters deep, yet they still support thriving communities of life. Life clings to these chemical oases even in the most extreme depths. Hydrothermal vents aren't limited to moderate depths. They exist wherever there's volcanic activity on the seafloor, and that includes the deepest parts of the ocean, in trenches and on abyssal ridges thousands of meters down. The deepest known active vents are in the Cayman Trough in the Caribbean, at depths exceeding 5,000 meters. At these depths, pressure is over 500 atmospheres. The water is near freezing. The distance to the surface is so great that marine snow arrives only in small amounts. These are extreme environments even by deep-sea standards. And yet, vent communities thrive there. Shrimp cluster around vent openings, their backs covered with chemosynthetic bacteria. Tube worms extend from cracks in the rock. Vent fish, species found only at vents, swim through the plumes of warm water. Mussels and snails colonize the periphery, where warm vent fluid mixes with cold seawater. The chemistry is the same as at shallower vents: hydrogen sulfide, methane, hydrogen, dissolved metals. Chemosynthetic bacteria oxidize these chemicals and form the base of the food web. The animals have the same strategies: symbiosis, filter feeding, grazing on bacterial mats, as their shallow vent counterparts. But the species are different. Deep vent communities have their own endemic species, adapted not just to vent chemistry but to extreme pressure. These organisms can't survive at shallower vents. They're pressure obligate, requiring high pressure for their proteins and membranes to function correctly. This means that vent ecosystems aren't uniform. A vent at 2,000 meters hosts different species than a vent at 5,000 meters, even if the chemistry is similar. Pressure creates barriers, isolating populations, allowing speciation. The global vent ecosystem is fragmented by depth as well as by geography, and it raises questions about the limits of vent life. How deep can vents support complex communities? Is there a depth beyond which even chemosynthetic ecosystems fail? We haven't found that limit yet. Every time we discover vents in deeper locations, we find life. It's possible that vents could exist and support life, even in the Hadal zone, though none have been discovered there yet. The deepest vents are proof that the combination of chemistry and biology can overcome almost any physical challenge. Pressure, temperature extremes, isolation, darkness. None of these prevent life from exploiting the energy available at vents. Where there's chemical disequilibrium, there's potential for chemosynthesis. And where there's chemosynthesis, there's life, even at the very limits of depth, clinging to chemical oases in the abyss. Some deep-sea creatures have metabolism so slow they may live for centuries without showing signs of aging. The cold, stable environment may dramatically slow biological processes, including aging itself. Aging is a biological process, the accumulation of cellular damage, the progressive failure of repair mechanisms, the eventual breakdown of systems that keeps an organism alive. But aging rates vary enormously across species. Some organisms age rapidly, living only days or weeks. Others age slowly, living decades or centuries. In the deep ocean, where temperatures are low and metabolic rates are correspondingly slow, aging may be dramatically slowed. Cold reduces the rate of biochemical reactions, including the reactions that cause cellular damage. Stable conditions mean organisms don't face environmental stresses that accelerate aging. Low metabolism means less oxidative damage from metabolism itself. The result is species that live extraordinarily long lives. We've already mentioned Greenland sharks, potentially over 400 years old, and deep-sea corals and sponges that can live for millennia. But even smaller organisms like certain deep-sea fish and invertebrates can live for decades or centuries, thus far longer than their shallow water relatives. Some show negligible senescence. They don't seem to age in the traditional sense. Their mortality rate doesn't increase with age. Their reproductive capacity doesn't decline. They simply persist, year after year, century after century, maintained by slow metabolisms and stable environments that minimize damage accumulation. This has implications for understanding aging as a biological process. Aging isn't inevitable. It's influenced by environment, metabolism, evolutionary pressures. In environments where living long is advantageous and possible, organisms evolve long lifespans. In the deep sea, where food is scarce and growth is slow, living a long time might be necessary just to reach reproductive size or to accumulate enough energy to reproduce successfully. Could humans learn something from deep-sea longevity? Perhaps. Understanding the cellular and molecular mechanisms that allow Greenland sharks or glass sponges to live for centuries might reveal strategies for slowing aging in other organisms. Some researchers are studying deep-sea species specifically for this reason, looking for antifreeze proteins, DNA repair mechanisms, antioxidant systems, anything that might explain their extreme longevity. The deep ocean is a place where time moves slowly. Not just geologically, organisms live slowly too, aging slowly, experiencing time at a pace so different from surface life that it almost seems like a different mode of existence. And in that slow time, in that cold and stable darkness, life has found ways to persist for centuries, resisting the aging processes that limit lifespan elsewhere. Bioluminescent displays in the deep sea can include complex patterns, flashes, waves, and pulses used for communication. In the darkness, light becomes language, signaling everything from courtship to warnings. We've talked about bioluminescence as a tool for hunting, for defense, for camouflage. But in the deep sea, light is also communication, and the messages being sent are surprisingly complex. Different species have different bioluminescent signatures, patterns of flashes, specific colours, rhythms and durations. A dragonfish might flash its photophores in a sequence that signals its species and sex to potential mates. A lanternfish might create a pattern that identifies it to others in its school, allowing coordination in the darkness. Even the timing matters. Slow pulses might mean one thing, rapid flashes another. Some deep-sea squid create waves of bioluminescence that ripple across their bodies, possibly signalling emotional states or intentions. Jellyfish create expanding rings of light when disturbed, a defensive display that might startle predators or attract larger predators to the scene, creating a burglar alarm effect. Certain fish have photophores arranged in species-specific patterns, like constellations. From a distance, you can identify the species by the arrangement of lights. It's visual identification in an environment where visual identification should be impossible, except that organisms make their own light specifically for this purpose. There's even evidence of what might be called deception. Some predators mimic the bioluminescent patterns of prey species, using false signals to lure victims close. It's the deep-sea equivalent of a lure, but instead of a physical structure, it's a light pattern, a message that says "I'm food" or "I'm a potential mate," when really the message should be "I'm about to eat you." The complexity suggests that deep-sea animals have sophisticated visual processing despite the darkness. They can distinguish between different flash patterns, different colours, different rhythms. They can interpret these signals and respond appropriately. Approach, flee, ignore, display in return. In the darkness, light becomes precious, not just for seeing, but for speaking. Bioluminescence is a visual language, evolved independently in countless lineages, allowing organisms to communicate across the darkness. Brief flashes of meaning in the perpetual night, messages written in photons, understood by those who know the code. The deep sea contains vast reserves of dissolved minerals, including gold, that dwarf all land-based deposits, but extracting them would require disturbing an ecosystem we barely understand. Seawater contains dissolved minerals, not just salt, sodium and chloride, but trace amounts of almost every element on the periodic table. Some are more abundant than others, but given the sheer volume of the ocean, even trace concentrations represent enormous total quantities. Gold, for instance. Seawater contains roughly 10 to 30 parts per trillion of dissolved gold. That's an incredibly low concentration. You'd need to process 1 billion litres of seawater to extract a few grams of gold. But the ocean contains roughly 1.3 billion cubic kilometres of water. Do the math. And the total amount of dissolved gold in the ocean is estimated at millions of tons, far more than all the gold ever mined on land. The same is true for other valuable elements. Uranium, lithium, rare earth elements all exist in seawater in quantities that dwarf terrestrial reserves. In theory, the ocean is an almost inexhaustible source of these materials. But extraction is another matter. The concentrations are so low that current technology can't extract them economically. You'd spend more energy processing the water than the extracted materials are worth. Some experimental systems have tried, using ion exchange resins or specialized membranes to selectively bind dissolved metals, but none have scaled to commercial viability. And there's a deeper problem: disturbing the ecosystem. Any large-scale extraction would involve processing enormous volumes of seawater, filtering or chemically treating it, potentially releasing altered water back into the ocean. The ecological effects are unknown. Would it disrupt planktonic communities? Change water chemistry in harmful ways? Create toxic byproducts? The deep sea's mineral wealth isn't just in the water, it's in the nodules on the seafloor, in the sulfide deposits at vents, in the crusts on seamounts. These are more concentrated, easier to extract, but extracting them means mining the seafloor, with all the consequences we've discussed. Habitat destruction, sediment plumes, species extinctions. We live on a planet where resources feel scarce. Land-based deposits are finite, concentrated in politically complex regions requiring destructive extraction methods. The ocean offers an alternative, vast quantities of minerals distributed globally, but accessing them requires technology we don't have and accepting ecological risks we don't understand. For now, the deep sea's mineral wealth remains largely theoretical, present, enormous, but protected by the simple fact that we can't yet extract it without costs that outweigh the benefits. It's a reserve perhaps for some distant future when technology or necessity make extraction viable. Or perhaps it should remain untouched, its minerals dissolved and dispersed, supporting the chemistry of the ocean rather than the economy of the surface world. Deep-sea trenches are among the most geologically active places on Earth, where tectonic plates collide and one dives beneath the other. These subduction zones can trigger massive earthquakes and are linked to volcanic activity. Trenches aren't just the deepest parts of the ocean, they're geological features of global importance. They form at subduction zones, where one tectonic plate dives beneath another, descending into the mantle. This is where ocean crust returns to the interior of the Earth, completing the cycle that began at mid-ocean ridges where new crust formed. The process is violent geologically speaking. The descending plate grinds against the overriding plate, building stress. Eventually the stress exceeds the strength of the rock and the fault ruptures. An earthquake. Some of the most powerful earthquakes ever recorded occurred at subduction zones. The 2011 Tohoku earthquake in Japan, the 2004 Indian Ocean earthquake that triggered the devastating tsunami, the 1960 Valdivia earthquake in Chile, all were subduction zone events. These earthquakes can trigger turbidity currents, underwater landslides and tsunamis. They reshape the seafloor, creating new faults, uplifting or subsiding sections of the trench. They're felt throughout the water column. Organisms experience the shaking, the sudden sediment movements, the pressure waves. As the subducting plate descends, it carries water and sediment down with it. At depth, pressure and temperature increase, driving water out of minerals in the crust. This water rises into the mantle wedge above the descending plate, lowering the melting point of rock. Magma forms. It rises, eventually erupting at the surface, creating volcanic arcs. Chains of volcanoes parallel to the trench. The Mariana Islands, running parallel to the Mariana Trench, are volcanic. So are the Aleutian Islands near the Aleutian Trench. So is the Andes mountain range along the Peru-Chile Trench. Trenches and volcanic arcs are linked. Two surface expressions of the same subduction process occurring deep below. For deep-sea ecosystems, this geological activity creates both risks and opportunities. Earthquakes and landslides can destroy habitats, bury organisms, reshape landscapes. But volcanic activity creates vents, seeps, chemosynthetic oases. The same geological processes that make trenches dangerous make them, in some ways, habitable. Trenches are where the Earth recycles itself. Old ocean crust, formed millions of years ago at mid-ocean ridges, returns to the mantle. Water, sediment, even organic material is carried down, processed, released, reincorporated into the geological cycle. It's planetary scale recycling, operating over millions of years, driven by convection in the mantle, expressed at the surface as the deepest trenches and the most powerful earthquakes. The ocean's aphotic zone, where no light penetrates, begins at about 1,000 meters and extends to the deepest trenches. This is the true deep sea, a realm of eternal night that covers most of our planet's surface. There's a boundary in the ocean, invisible but absolute. It's the depth where the last photon of sunlight is absorbed, where the faintest blue glow finally surrenders to darkness. Below this line, there is no natural light. None. Only the bioluminescence created by living things, brief and scattered, interrupts the blackness. This boundary, the bottom of the euphotic zone, the beginning of the aphotic zone, is typically around 1,000 meters. Though it varies with water clarity and latitude, below it lies the true deep sea, a realm of permanent night. And this realm is vast. The aphotic zone includes all of the bathypelagic, abyssopelagic and hadopelagic zones. It covers roughly 75% of the ocean by volume. It represents the majority of the living space on Earth. More than half of our planet's biosphere exists in permanent darkness. Think about that for a moment. Light, sunlight, is so fundamental to our experience that it's hard to imagine a world without it. But most of the biosphere exists without ever experiencing sunlight. Organisms are born, live, reproduce, and die without ever seeing the sun. Their entire world is darkness, punctuated occasionally by bioluminescence, brief flashes of biological light that are the only illumination they'll ever know. In the aphotic zone, and vision works differently. Eyes aren't for seeing landscapes or colours or detailed shapes. They're for detecting bioluminescence, flashes, glows, patterns, or for detecting the faint silhouettes of prey against the last traces of light filtering from above in the upper reaches of the zone, or they're absent entirely, useless in total darkness, replaced by other senses. The aphotic zone is not a dead zone, it's full of life. Swimming, drifting, crawling, hunting, hiding. But it's life adapted to darkness in ways surface organisms can barely comprehend. Life that uses sound, chemical cues, electrical fields, vibration, and its own biological light to navigate a world where the sun is not just absent but irrelevant. We live in the thin, bright skin of the planet. The aphotic zone is everywhere else. The deep, the dark. Yeah, the vast majority of living space on Earth. And it's been there, unchanged in its fundamental character, for hundreds of millions of years. A realm of eternal night covering most of the planet, home to more habitat and possibly more biomass than all the sunlit environments combined. Scientists estimate that 91% of ocean species remain undiscovered, with the deep sea holding the majority of these unknowns. Every deep-sea expedition returns with new species, hinting at the vastness of what we've yet to find. How many species live in the ocean? We don't know. We have names and descriptions for perhaps 250,000 marine species, but estimates of the true number range from 700,000 to over 2 million. The most commonly cited estimate is around 2.2 million species, meaning roughly 91% remain undiscovered, undescribed, unnamed. And most of those unknown species are in the deep sea, the surface ocean has been sampled extensively. Shallow reefs, coastal waters, continental shelves. We know these environments relatively well. But the deep ocean, the abyssal plains, the Hadal trenches, the mesopelagic twilight zone, these have been sampled only sporadically in tiny patches, insufficient to capture the true diversity. Every deep-sea expedition discovers new species, not one or two, dozens, sometimes hundreds. New fish, new crustaceans, new worms, new mollusks, entire genera previously unknown to science. In the Census of Marine Life, a decade-long project that concluded in 2010, scientists documented roughly 6,000 potentially new species, many from the deep sea. And these are just the species we've seen, collected, brought to the surface, and examined. How many more exist in areas we haven't sampled? How many live in environments we haven't explored? How many are so rare or so localized that we might never encounter them? The deep sea is a catalogue of unknowns. Every seamount might harbour endemic species. Every trench might contain unique communities. Every hydrothermal vent field has its own assemblage of organisms, some shared with other vents, some found nowhere else. We don't know what's down there. We know some of what's down there, the species we've documented, the ecosystems we've studied, but it's a fraction, a tiny sample of the true diversity. It's like trying to understand a library by reading 10 books randomly selected from millions. You learn something, yes, but you miss the vastness, the variety, the richness of what remains unexamined. The deep sea holds secrets not in the metaphorical sense. It literally contains species, ecosystems, even entire categories of life that we haven't encountered yet. And every time we send a submersible down, every time we trawl the deep, every time we deploy a camera or collect a sample, we pull up pieces of that unknown, naming them, studying them, adding them to our catalogue of known species. But the catalogue remains incomplete. The deep sea keeps its secrets willingly, not through malice, but through simple inaccessibility and vastness. It will take centuries of exploration, perhaps longer, to fully document what lives there. And by then, we might have already lost species to climate change, pollution, mining, before we even knew they existed. The deep ocean may play a crucial role in regulating Earth's climate over geological timescales through carbon sequestration. Carbon that sinks into the deep can stay locked away for thousands of years, slowly cycling through the Earth system. We've mentioned that the deep ocean stores carbon, but it's worth understanding just how important this is for climate regulation. The ocean is the largest active carbon reservoir on Earth. It contains roughly 50 times more carbon than the atmosphere, and most of that carbon is in the deep ocean, either dissolved or locked in sediments. Carbon enters the deep ocean in several ways. CO2 dissolves at the surface and is carried down when water sinks at high latitudes. Organic matter produced by photosynthesis at the surface sinks as marine snow, carrying carbon into the depths. Calcium carbonate shells sink and dissolve at depth, releasing carbon. All of this carbon accumulation in the deep ocean represents carbon removed from the atmosphere, at least temporarily. Once in the deep ocean, carbon can remain there for a long time. Deep water takes centuries to millennia to circulate back to the surface. Organic carbon buried in sediments can remain there for millions of years, only returning to the active carbon cycle if the sediments are uplifted and exposed, or subducted and released through volcanic activity. This slow cycling means the ocean acts as a buffer for atmospheric CO2. When atmospheric CO2 increases, the ocean absorbs some of it, reducing the rate of warming. But this absorption is slow. It takes time for surface water to mix with deep water, time for the deep ocean to equilibrate with new atmospheric conditions, and there are feedbacks. Warming surface water holds less CO2, reducing the ocean's ability to absorb atmospheric carbon. Changes in circulation can alter the rate at which carbon is transported to depth. Ocean acidification, the result of absorbing too much CO2, can affect the calcium carbonate cycle, changing the rate at which shells form and dissolve. Over geological timescales, millions of years, carbon cycling through the ocean and atmosphere is balanced by tectonic processes. Carbon is buried in sediments, subducted into the mantle, and eventually released through volcanism. But on human timescales, decades to centuries, the ocean's carbon uptake is crucial for moderating climate change. The deep ocean is absorbing our emissions, slowly, partially, but significantly. It's buying us time, buffering the worst of the warming we would otherwise experience, but it's not a permanent solution. The carbon doesn't disappear, it's just moved, delayed, redistributed. Eventually, much of it will return to the atmosphere as deep water upwells, and the ocean's capacity to absorb more is finite, declining as the water becomes saturated. The deep ocean is a climate regulator, a massive reservoir cycling carbon on timescales of centuries to millennia, connected intimately to atmospheric processes, playing a role in Earth's climate that we're only beginning to fully understand and quantify. Deep-sea sediments contain clues about ancient ocean circulation patterns, helping scientists understand past climate changes. By studying the deep past, we can better predict our climate future. The sediments at the bottom of the ocean are more than geological features. They're records, archives of ocean conditions, climate states, biological productivity, atmospheric composition. Each layer is a page in Earth's history book, and scientists are learning to read that book with increasing sophistication. One of the things sediments reveal is ocean circulation. The chemical composition of sediments varies depending on the water mass that deposited them. Deep water formed in the North Atlantic has different properties than deep water formed in the Antarctic. By analysing sediment chemistry at different locations and depths, scientists can reconstruct where water masses formed, where they flowed, how circulation patterns have changed over time. These reconstructions have revealed that ocean circulation is not constant. Yeah, during glacial periods, circulation was different than during interglacials. The strength of the Atlantic meridional overturning circulation, the conveyor belt that brings warm water north and cold water south, has varied dramatically. At times, it may have slowed or even shut down, triggering rapid climate changes. The Younger Dryas, a cold period about 12,000 years ago that interrupted the warming at the end of the last ice age, may have been caused by a shutdown of Atlantic circulation. Fresh water from melting ice sheets flooded into the North Atlantic, reducing surface water density, preventing deep water formation. The circulation slowed or stopped. Heat transport to the North Atlantic ceased. Temperatures in Europe and North America plummeted even as the rest of the world continued warming. Sediments recorded this event. Scientists can see the change in sediment chemistry, the shift in water mass properties, the evidence of reduced circulation, and they can see the recovery, circulation restarting, deep water formation resuming, the climate returning to its warming trajectory. Understanding these past changes helps us predict future changes. We're adding fresh water to the North Atlantic right now, melting Greenland ice, increased rainfall. Is this enough to slow circulation? The sediment record suggests that circulation is sensitive to freshwater forcing, that relatively modest changes can have large effects. Models predict that Atlantic circulation will slow this century as a result of climate change. Some predict significant weakening. A few suggest possible shutdown, though most consider this unlikely in the near term. The sediment record provides context. It shows what happened in the past under similar conditions, giving us clues about what might happen in the future. The deep past informs the future. By studying sediments deposited thousands or millions of years ago, we learn how the ocean and climate system responds to changes in forcing. We identify tipping points, feedbacks, mechanisms that don't operate on human timescales but become important over centuries or millennia. The deep-sea sediments are patient teachers. They've recorded every climate change, every circulation shift, every major event for millions of years. We're finally learning to listen to what they're telling us. The deep ocean's darkness and pressure create an environment where evolution takes different paths than in shallow water. It's almost like studying life on another planet, but one that exists beneath our own seas. The deep ocean is so different from the surface that evolution has produced organisms that look and function unlike anything in shallow water. The constraints are different. The opportunities are different. The solutions that work at the surface don't work in the deep, and vice versa. Take body structure. In shallow water, many animals have rigid skeletons for support and protection. In the deep, skeletons are often reduced or absent. Pressure makes rigid structures unnecessary. Your body is supported by the water around you, and rigid structures are energetically expensive to build and maintain. Take vision. In shallow water, eyes are for seeing colours, details, movement. In the deep, eyes are for detecting faint bioluminescence or silhouettes against dim light. And some species have enormous eyes to gather every photon. Others have lost eyes entirely, reallocating that energy to other senses. Take metabolism. Surface organisms often have fast metabolisms. They grow quickly, reproduce frequently, live short lives. Deep-sea organisms have slow metabolisms. They grow slowly, reproduce rarely, live long lives. The pace of life itself is different. Take feeding strategies. In shallow water, predators often chase prey, using speed and agility. In the deep, where energy is precious, predators ambush or lure, using minimal energy to wait for prey to come to them. The deep ocean is a natural laboratory for evolution. It's been isolated from surface environments for hundreds of millions of years, allowing independent evolutionary trajectories. The organisms there have adapted to conditions that barely exist anywhere else on Earth. High pressure, low temperature, no light, scarce food. And in doing so, they've evolved solutions we don't see elsewhere. Antifreeze proteins, bioluminescence in dozens of independent lineages, symbiosis with chemosynthetic bacteria, ultra-slow metabolisms, extreme longevity, pressure-resistant proteins, gelatinous bodies, enormous mouths, tiny brains. The list goes on. Studying deep-sea life is in many ways like studying alien life. Not because it's unrelated to surface life. It shares the same evolutionary origin, the same genetic code, the same basic biochemistry. But because it's been shaped by such different selective pressures that it looks and functions differently. If we ever discover life on other worlds, life in Europa's ocean, or Enceladus's subsurface sea, it might resemble deep-sea life more than surface life. It might use chemosynthesis, live in darkness, adapt to high pressure, grow slowly, live long. The deep ocean is our template for understanding what life might look like in extreme environments elsewhere. The deep sea isn't another planet, but it's close enough that studying it expands our understanding of what life can be, how it can adapt, where it can exist. It's alien life on Earth. Proof that evolution is creative, flexible, capable of solving problems in ways we wouldn't have imagined. Despite covering most of Earth, the deep ocean receives less funding and attention than space exploration. We've sent more people to space than to the deepest ocean, leaving our own planet's greatest wilderness largely unknown. There's an irony here. We spend billions exploring space, sending probes to distant planets, telescopes to observe distant galaxies, planning missions to Mars and the outer solar system. And these are worthy endeavours, expanding human knowledge, pushing technological boundaries, inspiring wonder. But we spend far less exploring the ocean. NASA's annual budget is roughly $25 billion. NOAA's entire budget, including weather forecasting, fisheries management, coastal protection and ocean research, is around $6 billion, and only a fraction of that goes to deep sea exploration. The result is that we've explored more of the Moon and Mars than we have of our own ocean floor. We have better maps of Venus than of the deep Pacific. We've sent 12 people to the Moon, but only 3 have reached the deepest ocean trench, and 2 of those were in 1960. Why the disparity? Partly it's about inspiration. Space is romantic. It's the final frontier, the great unknown, the realm of stars and possibilities. The ocean is familiar. We see it. We swim in it. We fish from it. It's harder to inspire public imagination about exploring something that feels already known, even if the deep ocean is as alien as any planet. Partly it's about visibility. Space exploration produces dramatic images, planets, nebulae, galaxies. These images are beautiful, shareable, compelling. Deep-sea exploration produces images of strange creatures and dark landscapes, which are fascinating but perhaps less universally appealing. And partly, it's about perceived relevance. Space exploration is tied to national prestige, technological development, defense interests. Ocean exploration is seen as more niche, relevant primarily to marine scientists, without the broader geopolitical or technological implications. But this perception is wrong. The ocean regulates climate, provides food, contains mineral resources, hosts ecosystems we depend on. Understanding it is crucial for managing fisheries, predicting climate change, protecting biodiversity, developing medicines as cereals. The ocean is not just scientifically interesting, it's practically important. And it's our ocean. It's here, on our planet, accessible without leaving Earth's atmosphere. We don't need rockets to explore it, just ships and submersibles. The technology is simpler, the logistics easier, the costs lower. The deep ocean is the largest wilderness on Earth. It covers most of the planet. It's home to more habitat, more volume, at a more biomass than all terrestrial environments combined. And we've explored less than 5% of it. We have a choice. We can continue prioritizing space, looking outward, seeking new worlds among the stars, or we can also look inward, or rather downward, exploring the vast unknown that exists beneath the waves, in the darkness, in the deep. Both are worthy, both expand knowledge, both deserve our attention and resources. The deep ocean is waiting, patient, vast, full of mysteries. Perhaps it's time we paid it the attention it deserves. The deep sea reminds us that Earth still holds profound mysteries, vast, dark frontiers waiting quietly beneath the waves. In exploring the deep, we're not just discovering new species, but new ways of understanding life itself. We've journeyed together through the deep sea, from the boundary where sunlight fades to the deepest trenches, from bioluminescent twilight zones to Hadal abysses, from hydrothermal vents creating life without sunlight to ancient sediments recording climate history. We've met creatures that seem impossible, learned about processes that challenge our understanding, glimpsed ecosystems that operate by different rules, and yet, for all we've covered, we've barely scratched the surface. The deep ocean is so vast, so diverse, so full of unknowns that 100 facts can't capture it. For every fact we've explored, there are 100 more waiting to be discovered. The deep sea is a reminder of how much we don't know. In an age when it feels like everything's been mapped, documented, explained, the deep ocean remains largely mysterious. As we've named a fraction of the species that live there, we've visited a tiny percentage of the seafloor. We've only begun to understand the role the deep plays in global climate, nutrient cycling, biodiversity. But it's also a reminder of resilience, of life's incredible adaptability. In crushing pressure, eternal darkness, near freezing cold, with scarce food and extreme chemical conditions, life thrives. Not just survives, thrives. It's diverse, complex, beautiful in its strangeness. The deep sea teaches us humility. It shows us that our planet still holds frontiers, still contains wonders we haven't imagined. It teaches us that life is more versatile than we thought, that ecosystems can exist independent of sunlight, that evolution is endlessly creative, and perhaps most importantly, it teaches us interconnectedness. The deep is not separate from the surface. What happens at the surface affects the deep, through falling organic matter, through changing chemistry, through warming temperatures, through plastic pollution. And what happens in the deep affects the surface, through carbon storage, through climate regulation, through nutrient cycling. The ocean is one system. Surface and deep, twilight and abyss, photosynthetic and chemosynthetic, all connected, all part of the same whole. As you drift towards sleep, perhaps you can imagine yourself descending through the water column, past the sunlit zone where colours fade, into the twilight where creatures make their own light, through the midnight zone where darkness is complete, down to the abyss where the pressure is immense and life exists at the edge of possibility, and finally, to the trenches, the deepest places on Earth where the planet reaches its maximum depth and life still finds a way. The deep sea is there, always, vast, dark, patient, full of mysteries we've yet to solve, species we've yet to name, stories we've yet to hear. It's been there for hundreds of millions of years. It will be there long after we're gone. But for now, tonight, we've visited it together, explored its wonders, learned its secrets, and perhaps, in learning about the deep, we've learned something about ourselves, about curiosity, about wonder, about the beautiful complexity of the planet we call home. Sleep well. The deep sea will still be there tomorrow, waiting quietly beneath the waves, holding its mysteries, living its slow and patient life in the darkness. The deep sea is more than a habitat. It's a frontier, a laboratory, nay, a library, a wilderness. It's a place where life has found solutions to problems we're only beginning to understand, where time moves differently, where evolution has taken paths we never imagined. We've explored just a fraction of it tonight. 100 facts from millions of possible facts. 100 glimpses into an environment that covers most of our planet, but remains largely unknown. And if these facts have done their job, they've sparked something. Curiosity, wonder, perhaps a sense of how much we still have to learn. The ocean is calling to us in its quiet way, not with urgency or drama, but with patient invitation. There are trenches we haven't explored, species we haven't named, processes we haven't understood, mountains we haven't climbed, underwater mountains far taller than any on land, hidden beneath thousands of meters of water. Perhaps someday we'll answer that call more fully. Perhaps we'll invest in exploring our own ocean with the same enthusiasm we explore space. Perhaps we'll map the seafloor, document the species, understand the ecosystems before we alter or destroy them. Or perhaps the deep sea will remain mysterious, visited occasionally but largely unknown, a reminder that Earth still holds secrets, still contains places beyond our reach, still offers frontiers for future generations to explore. Either way, it's there, the deep sea, vast and dark and full of wonders, right here on our planet, beneath the waves, waiting. Thank you for journeying into the deep with me tonight. May your dreams be as deep and peaceful as the quiet waters of the abyss. And may you wake tomorrow with a renewed sense of wonder for this strange, beautiful, mysterious planet we call home. Good night.